here. It could be helpful.
Yeah, I
And-
just don't.
And
If you could just say, if you get pulled into if you're asked to get pulled into a tech room, they're just wanting to test your PowerPoint and camera and link and all that stuff. What happens a lot of times is Google plays tricks on you and will not let you do something, and then last minute they'll ask you, you need permissions to do this, and that's and then once you create those permissions, you have to actually reboot your computer. So we want to try to avoid that. All right. So I think you guys are good. I think joining in virtually. So if you need anything, just chat me.
Okay.
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 All right.
Thank you. I'm impressed by the food. I brought cookies, but like I was just thinking I'd pass them out at break, but you put like the whole spread out there. So I'm just having my cookies.
Thank you so much.
a lot of it is what was left from yesterday. Nobody touched the sardines yesterday, so.
This is much better than the CLM. They charged $100
Yeah.
and they just gave bread and I don't know,
That's,
dull stuff.
yeah.
Well, there's a lot of sweets in what we have. But
No, this is good.
yeah, thanks for bringing things.
I'll eat it over.
So you're just joining the Google Meet and then presenting that way, and that's what everybody needs to do, I'm assuming. They
That's
present
what
from their own computer.
that's the best thing I've thought of at this point.
Yeah. How'd it go yesterday?
Good. It felt like, typically we give people 10-15 minutes talk. So, we went with 20 minutes, and I guess it doesn't matter how long you give people, they would use that time.
Yeah.
Had we said half an hour, I'm pretty sure they would have found a way to use half an hour. Like, damn, it didn't work as planned.
Just a reminder, country, we have a phone call with Marcus today, 3:30. Okay. I'll probably go home at lunchtime, take that from home.
Okay. Let's see. I need to do two things.
So pretty. Somebody did a better job than I did yesterday.
So the camera in this room keeps on moving,
Yes.
which is very annoying.
Yes.
Even if somebody's breathing, it will start focusing on
So
that
this is
person.
an AI-driven camera, and so it's going to try to follow the noise.
Yeah, yesterday I think somebody was breathing and it just started focusing on them.
Stop breathing.
That's what I did yesterday.
Wait, don't tell me I was the one breathing.
No, it was
sorry.
another who I don't know.
Okay.
And she was doing
Was
nothing,
it,
and
was
then
it
someone,
Kaishwan?
I don't know the name, and then
Yeah.
people were eating, and everybody started focusing on them, which is very, very annoying.
Yep. I'm gonna go grab a coffee.
So there's only tea though out there. Just
Oh, I'll get one for cafe. It's fine.
I should have come here first into the cafeteria.
There's no coffee.
there's no coffee. There's only tea.
Oh, well, but that's all right. Everything seemed to be working okay.
So far.
I don't want to sit here. Is this the?
Mm-hmm.
Oh yeah, I am eating, and it starts focusing on something far away.
Owl is fun.
For people who are coming in person, presenting in person, I had just stand where they were.
Yeah.
But I think it's better if they're not in the back over there. Otherwise, the sound might not be as good, so they can come closer. Otherwise,
Yeah.
I think the mic works, but then we would
But
have
then
made
we
the
can't
slide.
see them.
That too.
I guess the owl
Well, the
Mic.
action one.
rotates too.
The owl should focus on them.
Hello, hello, hello. Is it working?
Mr. Owl.
Well,
I can't. Yeah, the owl doesn't show up here.
Oh, yes, it
There it
does.
is. It's in the upper right corner. Is it you?
Oh.
Or is it Dave?
It's me.
It's,
And what about me now? Hello, hello.
Wave a bit. or something.
it's just to,
Is that,
Maybe
is that
sing a
how
little
you
song.
call people to order is with the ship noise? How, right. Figure out how to get in the side door.
Good morning. Hey. Hi, guys. That was itchy.
Yeah, I think that was-
Nice to meet you.
You know Summer?
Oh,
Summer?
yeah. No, I don't think we haven't met in person, but I saw you in the meeting. Three. Yeah.
So Summer's a postdoc here.
Huh?
Summer's a postdoc here.
Yeah, so I think I saw a talk.
I didn't realize, and it probably.
Pretty intense. Oh, you're doing the work on mountain glaciers. That's really interesting.
Uta was in a car accident a couple of days ago. And she said, Uta
Oh, no.
Hirschfeld was in a car accident. She says, all good. I mean, just a whiplash. She didn't break my spine or such.
Okay. Feels very Uta.
Sorry?
Feels like a very Uta thing to say.
She was in a car accident?
She was rear-ended in the interstate, I think. And she was able to drive home, so she and her vehicle were not too badly hurt, but I had that happen once, and I had, some soreness and stiffness for a while.
So there's, I think that's the act. So does the owl work for the picture up here or?
So that's actually a good question. I wanted to tell everybody.
Okay.
So I was just telling you earlier that the owl camera uses AI technology. So any noise that's happening, it'll try to focus in on that person. So yeah, it could do up here as long as nobody else is talking. Then it's trying to split that up constantly. If you do join in the meeting in the room, make sure you're joining in on companion mode and not, because otherwise it'll create audio loop. And that would be very disturbing.
How do
Okay.
you do companion?
It says
Right.
So
other joining options.
go to a browser. Yeah, it is in one of the, it's in the joining option.
You check, quit out of that.
You can open a browser though and type g.co /
And go
Companion.
join for a second. There's user.
do you need help?
I do, yeah.
So if you want to just log out of that and then go ahead and join. And it'll tell you, whoops, before you join. This is companion.
Did you get the link today?
And that'll allow you to join in without using your camera and microphone. Okay. Now, are you going to speak at some point?
I'm not.
You're not speaking? Okay. So if you are going to speak, you can join regularly, but just make sure that you're muted, your camera, mic, and your system sound is muted. Okay.
All right.
Okay.
So right now I have the camera muted, just because until you get settled, it's just trying to figure out
Yep.
what's happening, and it gets very confusing on the other side. So when you're ready to start, just tap on that button and it should start working for you.
Okay.
You saw what button, Bill?
It's the camera icon.
Oh,
So I've got the sound on now, so they can hear us, but they just can't see us right now.
okay.
All right. And I am monitoring on the backside, so if there's anything that's going on here, just chat me in. I'll be here.
Okay.
Thanks, Paul.
Our meeting makes it look more popular.
Yeah. Actually, I think it was also, had no idea what was gonna happen yesterday in terms of the weather.
Yeah, that's true. Right, a lot of people were not. So, come up.
I have 14 today. And then going down to only about 6 at night.
Satine this morning is shocked
Yeah.
that we have school today. She said it's negative
Yeah, so
25
I
out
think-
there.
Yeah, you for the first.
Celsius.
part, then
Yes.
That's not
Quincy,
nearly
and
as
then
cold
I'm
as
doing
negative 20.
afternoon. He'll be gone by then.
He only works in Celsius,
I
but
don't
negative
know.
25 is the coldest she's ever experienced in her entire life. And she said,
But yes, that was.
you
the
know,
plan,
if
was
none
that
of the
part.
students go into school, they can't have school. And I said, that's a very French way of thinking of things. In America, we say, if it doesn't kill you, it makes you stronger. Exactly. I was like, yeah, sorry.
Incroyable, Daisy Tutio. Or something like that.
She said she will never complain about cold again.
Where in France is she from?
Toulouse.
Okay, yeah, that's on the side. That's a nice place.
It is. They don't do this either.
I guess in companion mode, you can't see the bosses on. Morning, everyone.
Good morning.
How was yesterday for you? With the Boulder hiking? Did you know about it?
I did. I actually saw it on my phone yesterday morning during the meeting, and I was kind of like keeping tabs on it a little bit.
Yeah, Jerry was. She chose not to call me until, unless it turned out to be a real thing.
Yeah, I think when we got it for the break, I saw the headline go back. And
Yeah.
I think even at that point, they knew it was a
Yeah.
hoax, so I wasn't too concerned. But my husband and son hadn't even heard of it this morning. I was talking to Mark about it. I was like, it's so weird. They did so many different high schools across the state.
Yeah.
And there's no like
but you gotta
obvious
notice
rhyme or
that
reason to it. There's hometowns, there's like plains east side. It's like,
If it's too much right now,
Totally
we don't
random.
need to do it, but I just, maybe it's
Just looking up school hours.
create a tech room.
Oh, yeah, I guess.
yeah.
I would say you wasn't.
Like, is there a list?
Yeah, sure. All
Okay,
high school
yeah,
stuff.
and if tomorrow, that's.
And they, I said I was really pretty happy with Boulder took it so seriously. I know it's probably scary for everybody there,
Oh,
but
you
it
can
sounds
see
like
your sheet.
someone's.
Yeah,
one of the
I'll
ones
be,
that took it the most
Gunter won't be
seriously.
here tomorrow,
Oh,
so,
okay.
A lot of the other
yeah,
high schools were
tomorrow,
like,
I'll be
yeah,
training.
it's probably
Okay.
true.
So I was.
But
telling
Boulder
you
was
that
like 100% on top of it.
Okay.
Maybe Boulder would take that stuff seriously.
Exactly.
Tomorrow, and then I can do the remotes.
I find out who did it. They do some real jail time.
At 30. Before they speak.
Okay.
So, we can talk about that. in the morning.
That sounds good. Yeah, I'll see how today goes. and-
Okay. Sounds good.
Okay, thanks.
All right. Good morning, everybody. Can you hear me online? Yes, thumbs up from Heiko. Okay. Great. So good morning. Welcome to the second day of the Landis Working Group session and the first day of the Polar Climate Working Group session. We're going to have this morning a joint session between both working groups. And before we start, I would like to remind everybody of our code of conduct that's displayed here. So please, if you could obey by this conduct, that would be amazing. I was asked to make a few announcements, especially for people here in the room. First, please mute your phone. Don't forget to do that. Second, we have an owl in this room, which is the one who makes it look pretty on the screen and record our voices so that we are heard everywhere. And it is noise sensitive, so the camera is going to try to find the noise. So when you speak, the camera is going to come to you, or if you chew, the camera is going to try to come to you as well.
Apparently breathing as well, so.
So if you could hold your breath for the next hour and a half, that would be great. Thank you. For presenters this morning, if you haven't done so, please send us your slides so that if you have difficulties presenting, we could present for you and advance slides for you. If you feel like you'd like to present yourself and it works, please do so as well and let us know before you start. Let's see, am I forgetting something? So the coaches for this morning session, so it's been are Miriam Busqueno from the Landis Working Group, Marika Holland for the Climate Working Group, and Saisi from also the Polar Climate Working Group, and myself, Kim Kennedy. And we have our liaison, Katie Calder for the Landis Working Group, and Dave Bailey for the Polar Climate Working Group. And I would like to thank again our admin and multimedia team, Kela De Bellis, Teresa Wards, Elizabeth Streklas, Daniel Siena, and Paul Martinez for the support to make this happen. Couldn't be here without them. We have 5 minutes before we start, so if you want a last cup of coffee before we go or buy a break, take a last breather, please do so. And we'll start in about 3 minutes.
I think the only other thing for people that are in person, some of us will be going down to the Southern Sun, I think the Southern Sun, at 4:30. Is that the plan? Or immediately after this meeting, if people want to go down there, and just to socialize. So it's Stout Month. So, you know, if you want a stout, please join us at the Southern Sun. So, and we can coordinate rides down if people don't have a car and want to ride down.
In the remaining time, is there any questions? Online or here? No. So why?
Thanks everyone for coming up in the snow and the really cold weather. It's pretty, it's warming up though. I think it was, what Bill, you said it was -8 when you woke up and -5 when you left to come up the hill. So it's gonna be balmy. I think we're supposed to hit like 19 or something for a high, so. Yeah.
Not very encouraging.
On CPR this morning, they announced a record low in Denver at 6 a.m. It was -11.
It's Canadian.
Like Canada.
Feels a little chilly out there.
This is the worst seat.
Yeah.
Yeah.
Yeah. Right. Hide behind your screen.
Can you tell if it's looking at you?
What?
The camera, can you tell if it's looking at
Yeah, I
you?
can see it. It's
at
looking
the
at me.
top. right corner over there.
Yeah, so it's a little hard to see on the screen, but
I didn't.
you can kind of see what's happening.
Really
For
self-conscious
people
about my hair.
online, is the camera working okay? The in room camera working okay?
Yes, everything's working good.
All reading hearing you.
All right, we're 2 minutes ahead of time. Maybe this will buy us some more time for break later. Let's get started. So our first speaker this morning is going to be Miriam Viscano, and she's going to talk to us about large effects of ocean circulation change on green and ice sheet mass loss in the mid of the road greenhouse gas scenario. Oh, and just so you know, everybody has 20 minutes presentation. It would be great if you can keep it like within 15 minutes. So we'd be 5 minutes for question, and I will give you a 2 minutes mark before the end of your 20 minutes. So not rush you too much. So if you hear me, right, that's what it is about. So Miriam, the floor is yours. If you'd like to present your screen, go ahead.
And you're muted, Miriam.
Sorry, can you see the screen? Is this a yes or a no?
No.
No? Okay, I'll try again. Strange. You are saying another application window. So you are seeing
We're
nothing.
still not
Okay,
able to hear you.
I'm gonna try again. So
No?
no.
Marianne,
Oh,
you'll have to
Can't hear Paul
share
either.
your
We
entire,
can't hear you either, Paul.
you can't hear me in the room?
So
I can
problems
hear
on
you.
our end.
Okay, so can you share the entire window or the entire screen, not just a window?
This is why you start a few minutes early.
Yeah.
That goes out 2 minutes break extra.
Mm,
So just make sure that your application, if you're
Yeah, we're
using
not
like
able to hear
PowerPoint or if you're using PowerPoint, just
Yeah,
have
sure
it
the
up in
camera
the
just goes
It
background.
just did. It's like freaking me out.
Okay. Can you hear me?
I don't see the camera.
Yes, I can hear you. Can everybody
Okay.
hear her in the
I can't
room?
see it either.
Yes. Okay. So this works. When I try to share, it doesn't let me share the full screen, only the PowerPoint, but it doesn't work.
Okay,
I'm trying to turn down the volume and see if
try
it
to
works
stop
okay.
sharing
It worked yesterday.
and then try sharing the entire
yeah.
window. once- Excuse me, I'm sorry, but in the
Speaker,
room,
so-
could we keep the sound down, please?
Sorry.
So just try to share the entire window.
Yeah, sure.
Okay.
Somebody join, I'll be right up there.
So I get two options, entire screen or a window.
Yeah.
So shall I go for entire screen then?
CSM simulation. But it worked last time I tried.
When I try.
You're being recorded.
Okay.
I'm being transparent. You can do that.
Honestly,
It doesn't let me.
So who's joined in this meeting?
You must grant the
You
permission.
gotta join in through companion mode and not through the meeting, because what happens is you create an audio loop and you're sitting right next to that mic.
Oh, but we can't hear a thing.
We can't hear
yeah, we
anything.
can't hear
You
you
can't
guys
hear?
online.
Yeah, I turned down the volume, so.
Okay.
So
I see Miriam's-
can you say some words, Miriam?
Yes, hi.
So she's talking and
Interesting. Okay.
Yeah.
And if I turn on the volume, then.
Excuse me. Can I get past you just real quick? log in. No, he's not.
All right, here, can you?
Wait, we'll give him a second here. Now, can you hear us?
Okay, there we go.
Miriam?
Yes, I can.
So,
I'm not able to share.
Yeah, we can't hear you in the room.
and I could hear you. On my side too. All right, how about now? Can you hear us?
You see the companion mode. You got it.
Can somebody, Miriam, can you talk to us?
Yes, I can talk. Can you hear me?
Okay, now let's talk about what's going on your end. Are you able to share?
No, I am not, but if you want, you can put the slides up.
Do you have this?
I do perfect.
From here, do you know how to enter?
Well, that's only if you're going to share your screen, but you don't need to yet.
Okay.
Are you going to talk us?
No. You will,
So this will just allow you to see whatever's being shared. Yeah. So it's no different than just watching here, but you're just.
Perfect.
Watching.
Thank you.
All right. Sorry about all of that. So the floor is yours.
Okay, thank you very much. So I'm going to present work that I did with a master student, Julia Rutland, building on work from Laura Mungeberg and Raymond Sellefold. And the master thesis is publicly available in the TU Delft repository, and we are working on a paper. Okay, so I'm going to apologize first because I'm using the word moderate scenario. So yeah, it depends on your taste what you call moderate scenario, but this is how I am going to go. Next, please. Okay, so a little bit of background here. So the mass loss rate of the Greenland ice sheet has been accelerating in the last decades. Currently, the contribution is 0.7 millimeters per year. Going to the IPCC report, the CMIP6 models, all of them project weakening of the NAMOC of the North Atlantic Meridional overturning circulation, but there is large uncertainty in the results in the amount of weakening, and no collapse in the models for the first century. In the IPCC report, they point to a knowledge gap regarding the absence of coupling with Greenland ice sheet meltwater. But here, I'm going to go the other side. So the focus is not in how Greenland affects the ocean circulation, but the other way around. So which climatic effect can have a change in the NAMOC on Greenland? Please, next. Okay, so what I'm going to be using here is the couple CESN to CISM. So we have the surface mass balance simulated in CLM, and this is downscaled to the ICEN model. And we don't have direct forcing from the ocean to the outlet glaciers. Well, we should be here with an outlet glacier going into a fjord. So we don't kick Greenland from the ocean, at least directly, but through the atmosphere, yes. And we have the dynamical ice sheet running. Next. Okay, so now going to the scenario, here you have the CO2 concentrations or CO2 equivalent for a number of SSPs. And what I'm going to be using is an idealized scenario, it's 2 times CO2. So just to put it into context of these scenarios, you have this graph. with, I guess you cannot see my pointer, right?
No.
No.
No, not at all. Okay, sorry. So, okay, so I have allowed myself to call 2 times CO2 moderate, and you can see that if you look up to 2100 and beyond, yeah, you can more or less map it to SSP to 4.5, just for some context. And I will be comparing to a 4 times CO2 run as well. Next. Okay, so first climate, next. Okay, so we are running for this 2 times CO2 4,000 years of CESM. Most of this run was performed in the Dutch supercomputer, Subsara. We also extended in the NCAR computer a 4 times CO2 simulation that has been published up to year 350. We extended until full deglaciation. So the Greenland ice sheet is gone after less than 2,000 years. Okay, so first I'm gonna look at global change in temperature for 4 times CO2 and also Arctic and Greenland ice sheet. And by Greenland ice sheet, I mean the dynamical one. So if the area goes down, then I am looking at the temperature over the reduced ice sheet, not the original one. Okay, so if we go, then next. Okay, if we go with 4 times CO2, are we okay here? Okay, yeah. So if we are looking at 4 times CO2, so the orange ones, first, let's focus on the global one. So we see that a stabilization of 4 times CO2 is taking place at the year 140. So during the increase of CO2, we have a rapid warming, and then the warming rate is less. And then if you look at the Arctic warming, it is always larger than the global. So this is the Arctic amplification. And for the Greenland ice sheet, we also see for most of the simulation, we see that the warming is larger. So we are considering here annual means. Please, next. So now we are going to move into the 3 blue lines. And now first we look at the global. And for the global, we have period number 1, that is rapid warming coincidental with increase in CO2. Then we reach 2 times CO2 at year 70. And then we even have a little decrease in for the no, sorry. And then we see a different warming rate, of course. This is period number 2. And then in period number 3, something is happening. So we have extra 2 degrees of warming over that over a century. And then much less rate of warming. Okay, so I'm very curious. I hope you are curious now about this period 3. And now we are going to look at Arctic warming. And there is, for the first 200 years, it is more than the global mean. There are a period of almost 3 centuries where it is less than the global mean. So just hold there. And then it goes above the global mean. And then for Greenland, we even have cooling with respect to pre-industrial. And after the period 3, we see the warming increasing, and it is probably related to the local warming associated with the ice sheet having less elevation. Next. Okay, so now I'm gonna make you very crazy because from year 500 we are gonna couple to the ice sheet model every 5 years. So now I am stretching the 1,000 years of simulation to 3,000 because from year 500 I multiply by 5. Okay, so I'm still putting in blue this period with warming from year 400. And then I am looking at the NAMOC with this stretch time scale. And I see that the NAMOC went down to bottom levels in 2 times CO2 simulation. And during the period of 2 degrees of warming for the global mean, the NAMOC is recovering. So I'm going to be brave and I'm going to claim that there is a connection between the global mean temperature and the recovery of the NAMOC. Next. This is sea ice extent, and in blue is the period of recovery of the NAMOC after year 400. And you can see a response both in the September sea ice extent, color green, and also in the March sea ice extent, also color green. Next. Okay, so by now I'm going to conclude that NAMOC weakening is connected to polar reduction of global warming in a moderated scenario. First question is whether we see this in other simulations with CSM, SSPs. So this is a question for you, not so polar group mainly. And third question, do we see this in other climate models? So I leave it for the end. And a question for the land ice working group, well, no, also for the polar group. So it's so we have coincidental recovery of the NAMOC just at the time that we are switching to 1 to 5. And because there can be potential coupling with meltwater fluxes from Greenland, maybe it is worth to repeat the 1 to 1, a segment of this, an extension of the from year 500. Next. Okay, I want to go to the ice sheet now. So in these 3,000 years, 4 meters of sea level rise. Next. And these are time series for sea level rise rates. This is the color red, and 360 gigatons per year are 1 millimeter per year for reference. So now I'm going to go to the green line. So the mass balance is the difference between the SMB and ice discharge. And if you look at the green line, before the recovery of the NAMOC, we have what looks like a positive, relatively stable SMB. And then from the recovery, SMB goes down. It crosses 0, which is named as a tipping point in the literature. And then we go to negative values. Next. So conclusion, ocean circulation seems to play a large role on the regional climate of Greenland and on the contribution to sea level rise from Greenland. Next. Okay, so now I'm going to go a little bit with more detail on the ice. How many minutes do I have?
You still have 5 minutes.
Okay. This is a comparison of the pattern of the glaciation. So here you have the SMB, how it is evolving. In blue is the ablation area. So this is the year 3000. So by the end, this is our situation. We have an ablation area that is here in the red colors. And this is a comparison with simulation with the same model for the Indian. And I'm just comparing the pattern of the glaciation. So compared with the Amian one, we have less retreat from the north, yeah? Compared to here, the Amian retreat. And also we have more of the southeast retreat in the CO2 case. Next. Okay, for the surface mass balance, this is a scale to the size of the ice sheet. So it is millimeter per year instead of gigatons per year. So everything above 0 accumulate mass on the ice sheet, and what is below, like the melt, I put it as negative. So you see this increase in melt from year 400, and the SMB declining very strongly. For the snowfall, we see two things. Before the recovery, relatively low snowfall, probably in connection with the very weak NAMOC. And then there is quite some amount of increase in snowfall, not very large, but something after year 400 for the snowfall. The refreezing always stays below the total snowfall rates. Next. Okay, so this is how snow is evolving. So we have a decrease in the first century with respect to pre-industrial in snowfall over Greenland, so clearly dominated by the NAMOC case. And next. These are the energy contributors to melt. So melt energy is the black line, and then the solar is the blue, and the long wave net is the orange. And in the first centuries of simulation, the long wave is providing most of the energy, but once we have after some centuries, it's the short wave that dominates the budget via the albedo. Next. Okay, so for the clouds, for the incoming short wave, it is going down in the simulation because of increased cloudiness. Next. The albedo is going down, and so you can see here how the albedo is evolving and the corresponding SMB situation. So you can see how the albedo evolution is really tied to the ablation area expansion. Next. Okay, so conclusion, we can see a lot of detail with this model. This is very great, and we can tie what we are seeing to the global climate under the very same platform. Next. Okay, and here just want to show a couple of figures from a it's a paper that I invite you to consider about the role of climate scientists in the climate crisis. Now questions.
Okay, thank you very much. We have time for a few questions, if any, online or here.
I have a question. So Maren, you showed some of your plots had 4 times CO2 runs on them as well. And it looked like your the AMOC recovered in the 2 times CO2, but didn't recover in the 4 times CO2.
Correct.
Is that the case? And so do you see that, does that have implications for the ice sheet response? Or have you compared those?
Yeah, so it doesn't recover in the 4 times CO2 case. So we cannot make a parallel there. I think what I get from the comparison from 2 times and 4 times CO2. So in both cases, the NAMOC is collapsing, but we don't see too much of an effect on. We cannot see an obvious footprint, let's say, on Greenland because the level of global warming is so high, right? But when we are in an intermediate level of warming, then the control of the NAMOC on the regional climate of Greenland is very obvious. And this is why we see things like the snowfall going down when in many other simulations, the snowfall always goes up because there is more precipitation in a warmer climate in high latitudes.
Okay, thank you.
There's a question from Betty. Go ahead.
So, hi, Maren. Great to
Hi.
see you virtually. Question on, I should know the answer. When the Greenland ice sheet retreats and you expose the bedrock, do you keep that just kind of like bare soil, or do you allow vegetation to eventually grow?
Yes. Okay. So we put a map of vegetation that is static and corresponds to pre-industrial forcing. Yeah. So forcing from CESM, but for pre-industrial, and we did that instead of another climate because the vegetation was not evolving for other regions along the simulation. So we thought, okay, we keep it fixed. But yes, there is vegetation being allowed to appear. Yes.
Right, it's time to move on to our next speaker. Who's going to be Michele Petrini. He's going to talk to us about response of the Greenland ice sheet to temperature overshoot scenarios. Are you able to share your screen, Michele?
I will try. Let me just. Okay, I think it's working. Can you see my screen?
Yeah.
Oh,
Yes.
yeah.
Great.
Okay, that's good. Now full screen also.
Yeah. Yes. Perfect.
That's perfect then. Okay, good. Can I start?
Yes, please.
Okay. Good morning, everyone. So in this talk, I'm going to show some preliminary results from simulations of the Greenland ice sheet with the community ice sheet model season. First, with different overshoot scenarios that have been run using the Norwegian Earth System model NORIAS-M2. So this study is part of a research project called IMPOSE. So I'm gonna first to give you an overview of the project and introduce the specific aim of this study. And then I'll quickly go through some, the main simulation setup, in particular as concerns the surface mass balance forcing. And I'll then show you the results, so the response of the Greenland ice sheet to the overshoot scenarios. And I will also focus on the impact of the isolated impact of the SMB height feedback on this response. And then I'll just conclude and sketch the future and ongoing work. So first, the IMPOSE project. The PI is Jørg Swinger from Norse, and it is funded by the Norwegian Research Council. And this project looks at the reversibility of different components of the Earth system after temperature overshoot triggered by CO2 emission and subsequent removal. And to do so, Swinger et al. Ran these idealized 400 years long overshoot simulations with NORIAS-M at 2-degree atmospheric and land resolution. And in these simulations, CO2 emissions into the atmosphere are first increased and then decreased. Some results of these simulations have been published already, suggesting that most of the Earth system components are indeed reversible after an overshoot. And another interesting result recently published in Nature Communication is suggesting that CO2 removal can amplify the temporary northern hemisphere cooling due to the AMOC decline, leading to a temporary undershoot in the overshoot simulations. And you can see, for instance, in here, in these curves, the undershoot. And in this video that is playing in background, you can see the evolution of the air temperature for one of the overshoot runs, specifically the green curve here. And in the right panel, you can see the anomaly through PI control of temperature. And you can really see how the temporary cooling due to AMOC decline is affecting not only North Atlantic area, but also Greenland itself, which leads to the main questions that we try to answer in our study. That is how the Greenland ice sheet will respond to these overshoot scenarios, especially in terms of sea level contribution, reversibility, and also to what extent this temporary northern hemisphere cooling can help the ice sheet to stabilize or regrow. And to answer this, we use CESM, and we force it with surface mass balance, SMB, calculated in NORIAS-M. We don't use all the runs that you see here, just I want to highlight the main runs that we are considering. So we have the reference run, the 1500, where basically 1500 of petagram carbon emission are introduced in the first 100 years. That's the yellow line here. and then there are zero emission afterwards. And then the B2500, this is high forcing, the red curve in the plot, where so same as before, but with the 2500 emission. And then from this red line, from this run, there are two overshoot scenario branches. So the green and blue curves in the plot. In the first, we call it a short overshoot run. We remove 1,000 petagram carbon immediately after the emission, so immediately at year 100. Whereas in the second long overshoot, there is a 100 years delay. About the simulation setup, so how do we foresee them with the NORI-SM surface mass balance? We use a specific setting that is available in NORI-SM, but also in CSM, in CESM, which is called T-COMSET, where the ICID model is run within the Earth System Model architecture, with the only active component other than the ICID component being the land model, CLM, which is kept in data mode. And this is possible because in our forcing NORI-SM simulations, but really in any other NORI-SM or CESM run with an ICID domain, the surface air temperature in CLM is downscaled at multiple virtual elevation classes between 0 and 3,000 meters, using a fixed lapse rate of 6 Kelvin per kilometer. The SMB over the Greenland ICID is then calculated and saved at each virtual elevation class using an energy balance scheme. Then in our CSM run, during runtime, the SMB at multiple elevation classes is downscaled to the 4 kilometer ICID model grid. And this means that when the ICID topography changes in CSM and will lay in a different elevation class, the SMB will change accordingly. And in this way, we can explicitly account for the SMB height feedback. Now, let's get to the results. First of all, you can see in this plot here, the Greenland ice volume evolution for all the runs. On the right, you have the time series for integrated SMB, ice discharge, and mass balance. And you can see in all the panels that for each color, there are two curves. That's because each NORI-SM forcing run has two ensemble members. So for each forcing, we run two different CSM simulations. And for the reference run, so plus 1,500 petagram carbon emission, we have a sea level rise contribution of 3 centimeters, which is double then for the 2,000 petagram carbon emission. And when we get to the maximum, so 2,500 emission, we get to 12.5 centimeters after 400 years of sea level rise contribution. And in both the overshoot runs, so the green and the blue curves here, there are some about a 50 years delay before the ICID stabilize, and then it stabilizes, and the overall sea level rise at the end of the run, however, is slightly higher than in the reference run. So we have 4.5 centimeters in the short overshoot run, so that's 1.5 centimeters more, and 6 centimeters in the long overshoot. So it's basically fully reversible, but with some loss, basically, in terms of sea level rise. And you can see now for all the scenarios in these maps where the mass loss occurs. And for the reference run, primarily in the southwest, also in the northwest. Yeah, sure.
Please, we can hear some noise. Mute yourself.
Yeah, I can hear noise too.
The speaker. Thank you.
I'm sorry, but there was something going on.
Should I mute myself?
Not you, Michele. Whoever is not.
Yeah, okay.
The speaker.
Doesn't make sense. Yeah, okay, sorry. So the mass loss, as I was saying, primarily in the southwest for the reference run. Then for the two overshoot runs, there is also some loss at slightly higher at the western and northern margins. And in the eastern margin, the mass loss occurs only in the very high forcing B2500 scenario. And now in these two panels on the right, you can see the thickness difference at the end of the runs between overshoot and the reference. And for the short overshoot run, the excess mass loss is relatively low and focus on portions of the western and northern margins. Whereas for the long overshoot, the excess mass loss extends to the whole southwestern portion, the western margin, and is higher at the northern margins. Now, the very last slide, I'll show you the impact of these of the SMB height feedback. We, in fact, repeated all the runs without updating the SMB for the surface topography change. And while the upper panel is a bit crowded, but basically contains all the runs, and no SMB height feedback is are the dashed lines, and the solid are just the run that we look at before. However, for just to make it easier, in the bottom panel, you can see the contribution of the SMB height feedbacks in terms of sea level rise at the end throughout the run. And basically for the reference and the overshoot runs, the SMB height feedback accounts for around 50% of the total mass loss, whereas this contribution is slightly lower in percentage for the high forcing run, slightly less than 50%. Now, just to conclude, I'm going to conclude here. So in the overshoot runs, we have a stabilization of the ice sheet retreat, ice mass loss about 50 years after the beginning of the CO2 removal. And there is stabilization, but there is a higher sea level contribution for the short overshoot, 1.5 times higher, and long overshoot, 2 times higher compared to the reference run. And the SMB height feedback accounts for around 50% of the overall mass loss, slightly less in the high forcing run. Now, there is some ongoing and future work. So, of course, we want to extend all the runs, maybe for 1,000 or 2,000 years, just to check if there are some long-term trajectories that we do not see in 400 years. Also include and assess the impact of ocean forcing at the marine outlet. And I have a small spoiler. Using an ISMIP 6 type ocean forcing in the high forcing run, B2500, we have 45% more mass loss. We don't know yet for the overshoot runs. Also, another thing that we want to check, how about we stretch the forcing over time in overshoot runs? Is the final point going to be the same, or there is some runaway retreat at some point? And it seems that the final point is not always the same, but we really need to check better this. I'm going to leave it now for questions. Thank you for the attention.
Thank you. And thank you for bringing us back on track, time-wise. There's plenty of time for questions. No questions? Well, I will have one then. Do you plan on doing a similar run but with topography updating?
What do you mean with topography updating?
So you run a TCOM set, and then so you don't have the CAM topography, the data of season on the atmospheric component.
Oh yeah, okay.
Is this something you guys want to look at?
I'm not sure about this because I mean for the Earth system model part, pretty much all the simulation have been run, and I think there is not much computing time left. So that's for sure an interesting thing to do, but I'm not sure that fits in this project at least.
Okay.
So I have one question on the third point in the conclusion, that the SMB height feedback was 50% of the mass loss, but why would it be less in the high forcing run? I'm just curious as to what you think the underlying mechanism is, or why that is.
Yeah, that's actually a very good point. I don't have an answer for. We need still to analyze a bit more careful. But one thing that I could say is that probably, considering that the forcing is very high, there is more loss before you get the elevation class switch somehow. That would be one possible explanation, but I'm not even fully convinced about that. So we have to check better this.
I'm assuming that the model itself isn't, sorry, someone else's.
Finish your question.
Okay, what do you think would happen if you had lateral flow? I'm assuming that the model does not have lateral flow implemented of meltwater.
Yeah, okay. You mean that, I mean, like meltwater that reached the bottom of the ice, or just surface runoff?
I'm thinking about meltwater, which rather than, having the bucket model would go downstream. So, I mean, what I'm just positing here is that the SMB height feedback would actually be accelerated if
Yeah.
lateral flow were included. Okay.
Yeah, that could be. That could be. Yeah.
Betty, go ahead.
So great talk. So have you considered testing the sensitivity to the lapse rate that you use to downscale, as it may be not constant when you think about summer versus winter over the Greenland ice sheet?
Yeah, that would be really something we would like to do. But to do that, we need to go one step further and then run CLM2, because the downscaling is done there. And so there is no way in a T-comp set, so season active only, to change this lapse rate. So that's something that is really worth investigating, but we probably should open to some sort of a data atmosphere and then land ICIT coupled run. So something like IG. I mean, it's not technically it's possible, but I'm not sure how hard. We don't have for sure Kappa history files for CLM. I don't know if we can run that in anomaly mode. That's something we will for sure look after. We will try to do that, but at this time, yeah, I'm not really sure it's doable for these specific runs.
Time for one last question, if anybody has one. If not, thank you so much, Michele, and we're going to move to the next speaker.
Thank you. Let me stop sharing.
Perfect. So our next speaker is Ziki Yin, and he's going to talk to us about high resolution fully coupled simulation of the Greenland ice sheet in a future strong warming scenario. Do you have your slides, or do you need me to present for you?
I think I can.
Yeah, we're almost there. Try to, yeah, where is it? Yeah, there you go.
Okay.
Yeah, go ahead.
Okay. Hi, everyone. My name is Ziki Yin. I'm a PhD student at CEO Boulder, and thanks for providing this opportunity for me to present here, and also thanks to all my collaborators. And today I'm going to present some current results of this ongoing work. So first, some backgrounds. So the left figure shows the elevation of the Greenland ice sheet, and we can notice that the ice sheet margins have a steeper topographic gradients, and also there are also the ablation zones at the margins that are usually at a scale of tens of kilometers that are not very well represented, resolved in 1 to 2 degree climate models. And the right figure shows an example of research by Adam Harrington, and this is the annual precipitation basis compared to RECMO results, and they are results from different CSM2 simulations using like different horizontal resolution grade, and we can see that for lower resolution there are too much precipitation basis in the ice sheet interior because the topography is not well resolved and is too smooth to let too much moisture to penetrate into the ice sheet interior. So we need the fine spatial resolution to resolve narrow ablation zones and also the topographic gradients along the ice sheet margins. And also we are curious about the interactions and feedbacks between the ice sheet and the other components of the Earth system. So we also need a coupled framework to model these interactions and feedbacks. So that lead to our this work. We use fully coupled CSM2 with interactive gradient ice sheet using CISM, and also we are employing variable resolution grid for the atmosphere and land component. So this the red figure shows a 1 degree spectral element grade of CSM2, and based on this, we developed this variable resolution grade called Arctic grade, and it has 1/4 degree resolution over the Arctic region and 1 degree resolution elsewhere. And based on the work that I showed in the former slide, that's using AMIC scale simulations, the Arctic resolution simulation is 10 times more expensive than a 1 degree resolution run. So we use this variable resolution grid for atmosphere and land, and for the SG model, we have a resolution of 4 kilometers, and the ocean model is POP2 and has 1 degree resolution, and this is the first time the variable resolution grid is coupled to the ocean model. And also there are 32 vertical levels for the atmosphere. So by using this configuration, we have a regional high resolution over the Arctic, and which covers the Greenland ice sheet. And also compared to a regional climate model, we have a unified and coupled model infrastructure that allows two-way interactions between the region that we are interested about and also the rest of the globe. And also compared to a global high-resolution simulation, we have this strategy can reduce the computational cost. And we are going to compare our results with the CIMIP-6 1 degree workhorse CESM2 run, for example, like the Montreal 2020 that I think is mentioned in Miriam's talk. It uses the same configuration, but using the 1 degree resolution for the atmosphere and that. So we first run a pre-industrial control simulation for 180 years. It is branch off from the last slide of the WWG, the coupled CISM spin-up simulation. And at the end of our pack control, the Greenland ice sheet is near equilibrium state. And then from the end of the pack control, we started this idealized scenario that has a 1% per year increase of the CO2 concentration in the atmosphere for 140 years until it reaches 4 times the pre-industrial value, and then it's held fixed for another 210 years. These two blue shaded regions indicates the 2 period that we are using for the analyzing our results. So the first one represents that covers from year 131 to 150, represents the CO2 stabilization period, and the other one represents the end of our simulation. The bottom panel shows the near surface air temperature for evolution for globe, for Arctic, and also for Greenland ice sheet. So we found a 5K temperature increase for the global average temperature by the CO2 stabilization period, and 8.8K temperature increase at the end of the simulation. We also found that the Arctic amplification for the CO2 increasing period, our simulation is 1.8, and Greenland amplification is smaller, is 1.1, because Greenland actually is a terrestrial region that has perennial snow cover. And we also look at the transient climate response for our Arctic run, and also the finite volume 1 degree run in Montreal's paper. And we found a lower TCR, slightly lower TCR in our simulation. So then we can look at the evolution of the mass balance terms. And in this plot, the black line shows the evolution of the Greenland ice sheet mass balance evolution. We found 53 millimeters sea level rise accumulative sea level rise contribution by the year 150 and 831 millimeter at the end of contribution to sea level rise at the end of the simulation. And despite this linear warming during the first 140 years, we found this acceleration of the mass loss of Greenland ice sheet at around year 100. And it's also clear that the yellow line here, which is the evolution of the surface mass balance, dominates the mass loss trend. And then we can look at the difference, the evolution of the different surface mass balance terms. So in this plot, the black line is the surface mass balance, and it's clear that it's dominated by the trend of the surface mass balance is dominated by the right line, which is the surface melting trend. It also has an acceleration of the melting around after 100 years. And then from the energy perspective, we can look at the surface energy balance, which is showing this equation to analyze like which energy term provides most of the additional melting energy for this accelerated melting. So similar to what Miriam has already said, that about during like the first 150 years, the long wave radiation provides most of the melting energy, and then we see the increase of this net solar radiation's contribution.
Yeah,
Oh.
last year.
Okay, 12.
Yeah,
Weird.
trend also companion.
Yeah, it says you've left the meeting.
Yeah, it picked them
Yeah.
up for some reason. I don't know what happened there. So do you share screen? Yeah. And then go back out to the window where your presentation. Yeah. There.
Okay. Yeah. So we see the increase of the contribution from net solar radiation, and it becomes the largest contributor to this additional melting energy afterwards. And this is because what we call the S albedo feedback is triggered. So we can look at this evolution of the ablation area. So as the Greenland ice sheet shrinks, the ablation area continues to expand, and also the expansion accelerates at the same time period. And it's clear. Also, we can see it from these maps. So this map shows the albedo and surface mass balance of Greenland ice sheet, and the three columns represents pre-industrial condition, the CO2 sterilization period, and the end of our simulation. For the surface mass balance map, we can see the expansion of this ablation area in red, and we can then actually calculate the difference of the two periods compared to the pre-industrial condition, and we see the decrease of the surface albedo, especially around the ice sheet margins, and that this expansion of the ablation area expands more bare ice that's a lower surface albedo, and it further amplifying the surface melting. And also, this could be partly explained by the shape of the ice sheet. It's a parallel at the shape of the ice sheet, because as the temperature warms, as the temperature level rises, it favors faster expansion of the ablation area as it approaches the higher pattern. And also have results of the ice sheet thickness and ice sheet surface velocity. So we calculate the difference compared to the pre-industrial condition. We see excessive ice sheet thinning around the ablation areas. And for the ice sheet interior, there are actually some thickening because of the enhanced snowfall due to the enhanced hydrological cycle there. So we have thickening in the interior of the ice sheet and thinning at the ablation areas. And then in this transaction zone, the surface slope becomes steeper, and it drives faster ice flows that can be seen in the velocity difference plot that's shown in the blue color. And then we look at some major outlet glacier flow lines. So here I select four different major outlet glaciers in 4 different basins. And this flow line plots shows their surface mass balance evolution, the velocity, and also its elevation change. And the color, so the time goes from the dark blue to dark red, and we see heterogeneous response of these different outlet glaciers. So for the Humboldt Glacier in the northern basin, it retreats the earliest, and it becomes almost land terminating after at the end of our simulation. But for the Helton Glacier in the southeast basin, it doesn't retreat during our simulation. That could be because of it's more fast flowing, and also it receives more precipitation in the southern basin. But we have to notice that in the current configuration, the forcing from the warm ocean water to the glacier is not included. So that could lead to some differences compared to reality. And the last slide shows the ongoing simulation that we are running, and also that the simulation we are comparing to. So the pink and purple line shows the Arctic run that we are running, we run now, and the green line shows the Mount F09 simulation, and the light blue line is a new the new F09 simulation we are running, because so these 3 circles shows the starting point of this 3 simulation, starting point of the 1% CO2 increasing period of these 3 simulations. And we see because the Arctic run has the initial ice volume of the Arctic run is higher than the Mount simulation, and that is part of this. It's because the Mount simulation uses there is artificially elevated drag, and also some also measures that transform some cold rain directly to the surface runoff to reduce the precipitation basis over the Greenland ice sheet. So, but we don't have this measures activated in our Arctic run, so we run this new F09 simulation to better compare with the lower resolution runs. And so we plan to compare our simulation to both of these runs that have a lower initial ice volume, and also the other one has a higher initial ice volume. So if there are differences of the response of the ice sheet, then we can say it's the impact of the resolution. So the conclusion is similar to the modular simulation that we found that the Greenland ice sheet mass loss accelerates after 100 years. Is caused by the rapidly increasing surface melt as the glacier area expands and associated albedo feedback is triggered. And we also see the two-way interaction between surface balance and ice dynamics is very important for modeling the evolution of the Greenland ice sheet and also for specific outlier glaciers. So for our next steps, we will compare with these the 1 degree resolution runs to explore the impact of this enhanced resolution. And also we're going to include other interactions and feedbacks like the AMO and the effects of the elevation of the ice sheet on the atmospheric circulation. And there are also plans to integrate with machine learning methods to, for example, find the tipping point of the time series, and also maybe using causality model to analyze the cause of the mass loss. Thanks.
Thank you. We have time for a few questions.
I had a really quick, just
Yeah.
clarifying question. So your polar amplification, your Arctic amplification was 1.8.
Yeah.
Which is low compared to other CESM runs that I've looked at. So I was just wondering how you calculated that amplification number. What's your Arctic domain that you're averaging over and things like that?
The domain I use is the area above 70 degree.
So it's 70 to 90 degrees north.
Yeah, yeah.
And the average of that relative to the global mean.
Yes,
Okay.
to the temperature increase of the global.
Okay, yeah, because that number's low compared to like CESM 1 or CESM 2. So that's interesting whether it's the resolution.
Yeah.
Resolution dependence, or anyway, that might be.
Yeah.
It'd be interesting to look into that further. At least maybe.
Yeah.
Not necessarily for you, but I think that's an interesting question. Why the Arctic amplification is weak in that run relative to other runs.
Yeah.
So, thanks.
Miriam?
Thank you very much for this presentation. From the comparison with the 1 degree resolution by Laura Mungenfer, what do you conclude? Where do you have the differences, or what is the gain of the high resolution?
So currently, I only look at the evolution of the difference, like the mass balance evolution and surface mass balance evolution, and we have so in our simulation we have a smaller, slower mass loss than the 1 degree resolution run. But I think part of this is because we have a larger initial ice volume, and so we want to compare it to the new 1 degree run to make sure what's the impact of the resolution.
Yeah, I was just going to make a side comment there. I know Adam came to me to try to help tune that variable resolution run in terms of the ice and everything. So I definitely will be interested in looking at that comparison of the two runs. So because it was a bit of a challenge. We sort of only had one shot at the variable resolution run because of the cost of it. So
It's like what the mean sea ice.
Yeah,
Something
yeah.
like that.
Yeah.
Really interesting talk.
Yeah.
Thanks, Mia.
All right, let's move on to our next and final speaker from this first morning session, Chloe Wicker, who is going to talk to us about improved bare ice albedo over the Greenland ice sheet using physically based bare ice albedo radiative transfer methods.
Hey, let's see if my screen sharing works.
Seems to be working.
Okay, can you see my screen?
Yes.
Yes.
Great. Grab window. Okay, does it look good?
Yeah.
Great, thank you. Okay, thank you so much for having me. I am Chloe. I'm a graduate student working with Mark Flanner at the University of Michigan and Charlie Zender at the University of California, Irvine. And I'm working on improving the bare ice albedo over the Greenland ice sheet using physically based radiative transfer methods. So here is a quick overview of my talk. We'll go through sort of some of my motivations and then get into the work I have done previously, what I'm working on now, and the last couple things I hope to wrap up before finishing my PhD. Okay, so our motivation is current model representation of bare ice albedo. So we know bare ice albedo has a lot of variability, as we can see here. It varies a lot with latitude and time, and as the snow melts, we see just a lot of variability over the ice sheet. However, within Earth system models, the bare ice albedo is parameterized to be constant. So, for example, in the E3SM Earth system model in ELM, the albedo is parameterized to be 0.6 in the visible and 0.4 in the near IR. And then in the community Earth system model in CTSM, the albedo is an adjustable constant ranging from 0.5 to 0.8 in the visible and 0.3 to 0.5 in the near IR. So my work is looking to adjust that. And so I have chosen to look at the Greenland ice sheet specifically because it's the largest cryospheric contributor to sea level rise. And the majority, as you can see here, and then the majority of that ice loss comes from surface mass balance, as we have heard in previous talks. And as we see on this plot here, where the blue is surface mass, and then the red is discharge. So the mass loss of the surface is modulated by the albedo, which declines as our winter snowpack melts off, and significant surface melt has been attributed to that bare ice exposure. And so here we just sort of have a visual of the 2014 melt season, where we can see that winter snowpack melting off and revealing our dark, dirty bare ice beneath it. So now moving on to how my work is going to sort of adjust the bare ice albedo parameterization. So I added on to the snow, ice, and aerosol radiative transfer method that uses the microphysical properties of snow to calculate the albedo. I extended that to also be able to calculate the albedo over bare ice. So essentially, this is a schematic of what the Snicker model does. It simulates snow layers as snow grains inside of an air medium, and then a Fresnel layer, and then it simulates ice as a solid ice medium with air bubbles included, and that Fresnel layer is to account for the changing index of refraction between the two. So this is sort of the offline model I developed, and then just a ice core to show what we're trying to represent. And so this model can calculate the albedo for multi-layer cryospheric columns, but it does need the physical properties of the snow and ice, such as the density and air bubble or snow grain radius. This model also includes the influence of different biotic and abiotic light-absorbing constituents. The abiotic constituents include things like dust and black carbon species, and then the biotic include both snow and glacier algae. So this is just sort of a little result from this model where the dashed lines are the dashed lines are the measurement and the solid lines are the model. And we can see that the model reproduces measured albedo quite well. So if you want more information about this, it was published last year. And so now what I have done since then is I've taken that radiative transfer model over bare ice and incorporated it into the E3SM land model. So the E3SM land model already used Snicker to represent snow, and I added the bare ice capabilities. However, I did mention that we needed the physical properties of the bare ice. So what we did is we used MODIS, albedo, and reflectance products to sort of categorize and understand the spatial and temporal patterns in albedo and constrain the physical properties of bare ice for 2000 to 2021. And so we used the MODIS reflectance products to determine when and where bare ice is exposed. That has been done pretty routinely in the literature. And then I used the near infrared part of the spectrum to determine the physical properties of the ice, such as the specific surface area, density, and air bubble radius. And then we used the visible part of the spectrum to determine the impact of light absorbing impurities. So from those methods, we get our bare ice density map that varies spatially and temporally over the ice sheet. Same for our air bubble effective radius and a black carbon concentration that is used to sort of be a catch-all for any impurity content. And so we use those as input into our Snicker-informed E3SM. So the preliminary results from this work include, so here are our spatial and temporal results. We have our measurement for bare ice albedo scheme is much more realistic than the previous albedo scheme. Here is like the E3SM old constant albedo bare ice scheme. This is our MODIS bare ice albedo, and this is our new Snicker-informed bare ice albedo. So you can see we see much more agreement with measurements. And then if we want to just quickly look at the differences, these three are the plots we were looking at in the previous slide. And then here we have the difference between our new model and the MODIS data. And then here we have the difference between the new model and the old model. And so the default albedo scheme is too high in the ablation zone here where we see, here. It's too high in the ablation zone, but too low along the inner edge of the ice sheet. And so when we compare our new model versus the MODIS data, we see it's highly similar and we see accuracy within about 2%. But then when we compare it to the old E3SM, we see differences up to about 30% in an albedo. And so then just looking at some preliminary results of seasonal trends. So for the years 2000, 2002, which is what this data is from, this is a simulation over just those 2 years, we see a minimum albedo in June. But when we look at the long-term MODIS data that we have, we see that the albedo actually gets much lower and then actually reaches a minimum in August. So it will be interesting to see once we're done with these full-term simulations how the sort of spatial and temporal albedo changes. And then sort of looking at the impact of the changing albedo scheme on surface mass balance. We see increased surface melt along the ablation zone where the albedo is lower, which will be here because this is a difference plot. This is the default E3SM ice melt, and this is our new Snicker method ice melt, and then here's the difference. So along the edge of the ablation zone, we see increased melt in our model, but decreased melt along the inner ablation zone, and that is because we see lower albedo along the terminal edge. And so this is just a preliminary 1-year simulation, but in that simulation, we see a net increase in surface mass melt relative to our constant albedo parameterization. So these results are particularly interesting considering they were only for 1 year. So it will be even more interesting to see how it looks after our full 20-year simulation informed by our MODIS data. And so now my next steps will be to look at glacier algae on the ice sheet. So I'm going to use satellite data to quantify the spatial and temporal patterns of glacier algae along the ice sheet, like was done here in this 2020 study, where they categorized the spatial and temporal algal abundance over the southwest ablation zone of the ice sheet. And so I'd like to use that to then implement those optical properties within the Snicker ADV4 in E3SM to categorize the spatial, to categorize both the impact on albedo and the total radiative forcing impact due to glacier algae. And the reason we want to do this is because significant surface melt has been attributed to glacier algae growth, and it's been shown to drop local ice albedo by anywhere from 3 to 43%. And so some preliminary steps that have been taken towards this is glacier algae is already an option in our offline SNCR model, and some of our collaborators have used it to compare to their in situ measurements. And so this would be here, we have the field measurement in black and then the simulation in gray, and we can see that the SNCR model is able to reproduce that drop in albedo caused by glacier algae quite well. So it'll be interesting to see how the what the drop in albedo is at the ice sheet scale. And so in conclusion, this work improves our ability to model bare ice albedo over the Greenland ice sheet. We see improved spatial and temporal varying bare ice albedo, and it currently only applies to the Greenland ice sheet land simulations for the years 2000 to 2021. However, these methods can be extended over different regions or used to calculate climatologies for historical or future runs. And then my next steps are to perform the simulation over the full time period we have data and quantify glacier algae impact. And that's it. I can take any questions.
And we are backtrack on time. Thank you. So there are a few questions in the room. Please go ahead.
Okay. So I have a question about MODIS, basically the resolution of MODIS versus the resolution of the things that might affect albedo. So I'm thinking about this for glacial algae in particular. So I was curious about that there was some it did really well at the margins, but then towards the interior it was had like a little bit more difficulty. Is it possible that a higher resolution product for infrared might actually resolve a lot of that?
Okay. Just to make sure I know what you're talking about, let me share my slides again. So you're talking about these different spots?
Yes.
Okay, so you're saying it has a little more trouble along the inside edge versus the outside?
Yeah, well, and I guess what I was wondering is that if that was in some part because of the resolution of MODIS, like within those regions, the resolution of MODIS not capturing the internal variability of albedo.
I think that potentially could be part of it, but I think another potential cause is that the way we categorized where MODIS had bare ice was just essentially if the near IR albedo falls below a 0.6 threshold. And then we applied an elevation mask. So it was like nothing above, I forget what the exact elevation was. So I think my guess as to why it's not performing as well is because there is some like not actually bare ice contaminants in there. So I think that is likely more the reason we're not seeing it as well matching in the higher elevation regions. Because the MODIS resolution is quite high, at least compared to the model resolution. But I'm sure, I mean, it definitely couldn't hurt to improve the resolution of our parameterizations.
Yeah, thanks.
Yeah.
Thanks, Chloe. Great talk. As you know, we've felt, I would say, nervous about our constant bare ice albedo in CESM for a long time, or at least I have. So it's great to see this. Is just a practical question: is there a path and a time frame for getting this work into CTSM and eventually CESM3? So something we could test as we start testing CESM3.
Yeah, I think that would be great to implement this into CESM. That was originally actually my plan, but then E3SM already had the more like the newer version of SNCR in it, and so it cut out a lot of work for me to do, so that quickly became the path of least resistance. But I think this work is definitely transferable. I know the two models are very similar, and I don't have any short-term goals of putting it in there, but I'm almost done with my PhD, so we can sort of see what happens after that.
Okay. All right. To make sure that this happens, is there some way we could facilitate that?
Yes, of course.
We'll talk. Thanks.
Okay.
Any other questions? Yeah, go ahead.
Yeah, great talk, and just sort of a clarification. So I guess in this work, are you limited only to the time period where you have the MODIS data? Because if I understood right, you're actually using the MODIS data to inform the inherent optical properties. And so I'm wondering, is there a pathway to actually trying to get those inherent optical properties from tracers in the model itself?
Yes, so I would love to be able to get the things like the density and air bubble radius from the model itself, but that doesn't currently evolve in our ice sheet model. So we have to get them externally. And so, yeah, temporarily MODIS seemed like the best solution because we have decent resolution and we can use the near IR to get these properties. I'd say short term, you could do something like developing a climatology from the data we have currently and then applying that towards simulations outside of this 2021 run. But long term, it would be great to sort of use tracers within the model to calculate those things instead of needing outside measurements.
Miriam?
I'm wondering what do you recommend for once the ablation area? So if we have an expansion of the ablation area, so then what should we put there in the place? Because for these places we don't have MODIS at the moment. So yeah, so how do you plan for a Century simulation into the future?
Yeah, that is a great question and something I have been sort of thinking about as well. I would say, again, sort of preliminarily, I am thinking about maybe developing some sort of like regional albedo averages. Like if we look here, we have ice sheet wide albedo averages that are actually quite high, but sorry, they're like around 0.7. If the font is too small. But I think we could do something maybe in the meantime, like prescribing regional albedos based on what they are historically. But then, like I said, with the previous question, it would be great to get something like an evolving ice density that we could use to actually calculate that.
So you do have black carbon in the inner treatment of albedo, if I understood correctly. Is there the possibility of coupling that with the atmosphere so you have actual kind of black carbon deposition?
Yeah, theoretically. Right now, we are kind of using that black carbon as like a sort of like filler equivalent black carbon, because when we use the near IR bands to figure out what the I think I might have an extra slide on this to figure out what the optical properties of the ice are, it actually quite overestimates the visible albedo. So here is our visible albedo just using those near IR ice properties, not accounting for any sort of impurity or like crustal surface. And so that black carbon is sort of filling that role right now. I think it's definitely something that could be coupled to the atmosphere, but I think that would maybe potentially lead to uncertainties in our albedo because it might not actually be enough black carbon to fully categorize or fully capture that reduction in albedo due to like any sorts of impurities like glacier algae dust or even like rough crustal melt ponds, that type of thing. So the answer is yes, but I guess.
Okay, thanks.
Any more questions? If not, thank you again. I would like to thank all of the speakers again from this morning. And we're going to take a half-an-hour break where we convene at 11. And feel free to talk online if you want to. We will leave the link on. And yes, see you in half an hour. For people that are in here, we have tea outside. We don't have coffee. If you want coffee, we need to go to the cafeteria. Sorry about that.
And in the cafeteria, you actually do have to pay for coffee. So yes, we might get in trouble if all of us take a cup without paying.
Yeah,
you
you
should
should
probably-
probably.
Times that hard.
Times that hard. Podium if you want.
Times are hard, but you got chocolate, so they're not that hard.
Okay. Because the idea is to
owl
I mean, that would be one way to make it happen. And
So if she were to win the ASP next year. Possibly a shorter time.
Right.
Oh, you're not going to BBC at all?
Yeah.
Okay, well, so my son is a freshman.
yeah, I think that's probably the first place to start. I mean, I don't really know, you know, I mean, I know it's happening on the CI side a bit in terms of how things are being shared. And it's all been done through the site, right? I have no idea in terms of developments, if there's what the possibilities are. But I think talking to Mark and Chloe is probably the, because maybe it's very straightforward to transfer for it. I don't know. I'm not sure how different the models are.
Thanks for taking notes.
So, yeah.
That's very helpful.
But it would be cool to get in, right? And it would be nice to get in for CESM 3.
No one else did that. You're the first person.
We do have the aerosol deposition on the sea ice for the albedo, in terms of dust and black carbon. So, and then it feeds into the rate of transfer. So that.
Who's the CTSM person who's most closely
did get access to those granules.
connected
So
to
the
that?
next time I'm in the lab, like I think I'll go tomorrow, I can start on that.
I don't know. I'd ask the land guys.
Ask Will.
Yeah, probably ask Will and maybe Dave. But
Yep.
start with Will since he's the
Yep.
co-chair.
Yep.
And Dave has his hands full with
Hey,
other things.
How you
I
doing?
heard you were in an accident.
Yes, I'm in crashing. But I wanted to come and see you guys in 3 dimensions.
Yay! How are you? I mean, are
Much
you
better
okay?
than yesterday. I
Okay.
finally went to the ER because he didn't get an appointment. But yeah, so I didn't break anything. Because I was afraid, like my head was just sort of blowing up yesterday. It travels down my spine. I'm like, shit, I work in academia. I want to work 20 more years.
Did you have a concussion?
They said it can't be a bad concussion.
Yeah.
But I was afraid I heard cracked my spine or something because it was like hurting in some spot. Anyways, I'm going down at 70 and the traffic slows down near Georgetown and this sportsy looking black car with flashing lights. I think it's all my fault that we're going slow and I drive a Tacoma normally, right? And so I have no business in the left lane, but the right lane is packed with big trucks like it typically is, and all the traffic in front of me suddenly stops.
Yeah.
But the tailgating guy did not stop. But I mean, you could look down the entire hill and see everyone stop.
Right.
He thought it's my fault. And
He thought it was your fault for stopping.
well, it was my fault. The first,
Getting away with his car.
yeah, and getting away like in the beginning that I was the one who's slow and I should get out of the way so he could zap past at 80 miles per hour. And then everyone stops and
Yeah.
yeah.
Also, have you dealt with the insurance yet? Like-
No, because this guy pulled off to like there's this marginal standing lane.
Yeah.
And I'm thinking, and people are like, no, it's stopping left and right. I'm thinking, okay, it's downhill as long as my truck rolls, I'm gonna roll off of I-70. I call 911, I called State Patrol an hour and a half, no one came.
Oh.
And I mean, it was 3 in the afternoon.
So the guy didn't stop.
The guy pulled his car off on I-70,
Okay.
quickly through the trucks, and I wasn't sure. I wanted to wait for a sizable gap, right?
Right.
I don't want more people to crash into me because
Yeah.
that's what makes the big carambolages.
Right.
So yeah, I'm pulled, but it's only like if it's half a mile, it was far. So I just thought, hey, I have a better time waiting for the police. You know, they don't always come if I'm in front of the visitor center.
Yeah.
So I called 911. They said, what if it happened on I-70? We're going to send you State Patrol. And then an hour later, well, we dispatched the state patrol from Littleton then. And they have to deal with all the traffics in between. Well, yes, the government at work for you.
Yeah.
And I mean, it was getting cold, the snowstorm was moving in. And my son came out. He's 19, but he works for Border Emergency. So he has this kind of attitude. And we just bought a brand new, well, a 2016 F-250. So he's like, I'm coming. No questions asked, Mama. I'm on my way to you. So he came up, he checked after the first chalk ride, like I'm squeaking. I said, no, I don't want to know.
Yeah.
I tend to keep it together. It was not a soft crash. But the track was okay because it hits the track bed. It transmits the force rather directly.
Right.
But, but
What happened to the other guy's car?
he probably told it.
Good.
Well, I mean, he probably crumbled his front because they
Right.
pulled to the other side, right? But I thought if I call the police, all I have to say is the other car's parked like 500 meters up, up the ramp, and the ramp there is kind of iffy, and everyone's like sort of antsy. So I didn't want to stand there and wait for more people to crash. Yeah, so it was scary because they patrolling. Finally, we said, hey, so we're going. Then I was told behind and saying like, hey, you're going to drive behind me. So I'm just sort of staying in the right lane all the way. Then there's this truck, this little Ford behind me pulls out. You can see it wants to say, hey, Mama, hey, left, blocking all the traffic for me. So anyways,
I'd say I love it when our children start taking care of us. I think that's
right,
awesome.
but I mean,
And
I
when
have
you're
to
only
say,
19 and taking care of you, that's a good, done well. But your sons. Yeah.
I actually have my son's phone number wherever I have to give emergency phone numbers because my husband talks like he had another cancer scare, so he called him, he's fine. I'm like, hey, I'm in a crash. All right, yeah, also hopefully taking care of you. I'm gonna go to church. Well, sure. Yeah.
Well, I'm glad you're okay. I mean,
Yeah,
and hopefully there's no.
I wanted to just change my go to sleep section and just use the self-service. It's ridiculous.
Yeah, it is.
So like, I just
Can't
sent
do
you my
anything.
phone
So now,
and it's not accepting it.
Yeah.
Yeah.
Sorry. I go through this.
If I go to sleep, then I have to relog into
no,
Oh, so it's going to sleep.
and then it's kicking me out. And then I gotta go.
You gotta log in and then you gotta come back into the meeting.
Yeah.
That's great.
But anyways, yeah, he took a year off from school. I mean, didn't go straight. But I mean, his friends go to school in open major because their parents a lot, and then they just change the major. So I'm not sure. I just want to work. The first thing that happened was
Well, nice job. Really clear, like well motivated presentation. It's fun to see. I know that like I see you every day and you don't want to see that way, but it's really fun to see. What? No, I biked and then I took the shuttle. So is it online? Apparently there's an app. So I was talking to people who told me there's an app. So. Oh. I also, I'm gonna take a photo outside. Yeah. When I searched. And then it's like a PDF. It'll show the PDF, and then I think the one for this one is over. And it'll update it, and then you can see. But I think there's an app, so that they'll know that I actually. Yeah.
Yeah, I think that. Yeah. Yeah.
Well, a few technical challenges, but overall, this looks pretty good.
Yeah. Yeah, I'm downloading some of the talks just.
Just in case, yeah. No, that's a good idea.
Yeah, Gunter hosted like 3, maybe 4 yesterday that people couldn't get their screen sharing to go. It's really odd. I think it's something to do with like the plugin. Sometimes.
Yeah, yeah.
I don't know. Yeah.
Yeah, that's actually a good point because, you know, I use the Google Chrome browser so that generally all the Google apps work together in the Google Chrome browser, but not all the time. I did not realize that you used the specified albedo on the ice sheet.
Yeah, I guess I kind of was, well, I guess you don't for the snow, right? You've got Snicker working for the snow. So it's just the bare ice.
Oh, it's just the bare ice part of it.
Right.
Got it. Okay. Okay.
But that's different than what we do, but we do just assume that our inherent optical properties for the bare ice are kind of constant, like we don't have, I mean, we do a ponding on the ice and we have aerosol deposition on the ice.
Right.
Black carbon. And
Yeah, but again,
the
the
ice
point-
albedo one of those things that you guys tune for the different grid
well, we
sizes
don't tune the albedo per se. We tune like snow grain radius, the sort of mean radius,
Okay.
and then that sets a dry snow albedo, and then it still evolves as the temperature evolves and as the
Oh, okay.
Yeah.
Sigrid just gave me a tip. I have to log on to the meeting differently.
Yeah.
Not like to join the meeting, I have to join it because I can't.
yeah. You have to do a companion mode.
Yeah, but I can't click on it. It doesn't work.
What?
Press my email.
Yeah. Go back in and
And
join
then
the meeting.
Join the meeting, but I have to join in companion. Oh, joining option. YouTube meeting. I just put it.
Right.
So that's what I didn't want.
Okay.
Okay.
Yeah.
I didn't even see that.
Yeah, I know. Well, that's the thing. Like they want us to use this companion mode, but it's really not obvious. It's very tricky.
It's completely not obvious.
Yeah. It's super confusing.
I need to mute.
So,
Companion mode, you're muted
Oh,
automatically.
yeah, you're muted and you're muted and your camera's off. So it's already taken care of. And so your audio and your video go through this thing. So when you're speaking, you can try to look over towards the owl, but anyway, the other thing is like that I was thinking, because Snicker's like this multi-scattering sort of computation. And so the idea is that the albedo is a calculated value. So you have a short wave that comes in, hits the surface, and then it goes through the multi-scattering algorithm. And then at the end, it figures out the net absorbed short wave, and that's your albedo. So I guess I'm confused by where the albedo comes in here with Snicker.
Well, I guess it's gonna give you what what your shortwave if their ice interface is. Well, yeah, I don't know how they
I don't know.
absorb their shortwave. I guess they just assume everything that lower than the snow is absorbed in the ice.
Maybe. I don't know.
So it's on the.
Mark, are you there? You want to tell us?
Or Chloe.
Or Chloe or Charlie? Okay.
They're not there.
I'm here.
Okay, so how is the albedo used with Snicker then? Because I thought that it computes the shortwave incoming, and then there's the multi-scattering, and at the end of the day, you get an absorbed shortwave and an albedo resulting from that. Or am I misunderstanding something about the way that Snicker works?
Well, generally, the atmosphere provides the incoming shortwave.
Yeah.
And it only uses 2 bands, which is a major fail, but we all do it.
Oh, yeah, fair enough.
And then Snicker splits it into 5, 1 visible, 4 near infrared, just to get better capture the spectral signature of snow.
Yeah.
And what Chloe described uses those bands and that methodology, but the additional, and so Snicker runs its own 2-stream model. Okay, I don't know if you knew that. Okay, so what Chloe has done is she has bolted onto the bottom of the 2-stream boundary condition a whole new set of vertical layers.
So Bill just mentioned.
Okay. That are ice with air bubbles, and in between the existing, the one that's
I know that there's
existing snow layers and the ice layers is a Fresnel layer for the index of refraction effects. Okay, but it's still the 2-stream code, and so the communication with the atmosphere happens via the same way, and the bare ice fraction gets weighted in. The albedo from the bare ice fraction gets weighted in with snow cover fraction, and that whole thing gets transmitted back to the atmosphere. Now, for the bare ice albedo, it doesn't apply underneath the snow, but actually it can run and does run everywhere. And I think Chloe turns it off if there's too much snow, meaning not very much snow. And so the bare ice is really running on its own. It's only the 2-stream solver is just really solving the bare ice in the regions where that albedo is used.
Solar.
Yeah, if you look at the owl, he can see you.
Hi, Charlie.
Hi, disembodied voice. Good to hear you.
Somehow the camera's not on. The camera's not on.
Christine?
Nice to see you.
Talk to her.
Christine?
That's pretty good presentation, getting post doc offer out of it.
I'm not sure if I met her yet.
Otherwise, it'd probably be like.
Yeah, that's probably true. That's probably true.
Yeah, she seems, actually, she reminds me a lot of Mark Planner. Who's your advisor.
Yeah, well. That's Charles.
That's Charlie's under. Anyway. Mark was a student of Charlie, and a lot of stuff was developed by Mark. So just one of those people that just surviving quietly, goes to work every day. At the end of a couple of years, has produced a whole lot of stuff.
So, what's your deal today? You have to get to.
He writes about the world more than me sometimes.
Sorry, I'm looking.
Yeah, I've lost my
I
case.
technically have a meeting.
I've lived in the US. over
Okay,
half
with
my
you.
life now.
I'm gonna leave it till.
The first 3 years of it was in
Yes,
Fairbanks.
I just need to
so-
That
And have a
So, yeah.
still had the credit.
there, so you have 2 o'clock, right?
Yeah.
Okay, so are you okay with?
It was the most awkward one, but it was a lot of model to talk to yesterday. So
So Uta, are you
So are you
presenting?
okay
As a
with
student?
leaving around?
Okay.
Or
Well,
like
I
after
thought
this
about
session? because I think we-
asking about it, but I know we can get this.
But, they're gonna be meeting at
It sounds like they're, so like the last time we started talking about this, there was a lot of uncertainty about the teacher.
Okay, sounds good.
It sounds like
Yeah.
they are sort of like.
I was just basically gonna go right after.
It's interesting that he seems to have built it.
It's fine. Right? Yeah, actually, it's a pretty impressive attendance in person. Yeah.
Because we had in,
Yeah.
May summer.
Unless you have the right.
Right.
So-
My
Right.
problem is that I don't have this one, so.
Yeah.
I'm gonna have to
It's not
wait.
gonna be too quiet.
I just,
Okay.
trouble
Nice.
picturing.
Yeah, yeah.
Okay, the word is spreading.
Yeah.
CSM
Yeah.
workflow. I mean, it would be fine for post-processing.
Right, I had
System history
some
processing afterwards, but it's
Oh,
really
yeah.
not for the system CSM.
So
Stuff that a lot
wonder-
of times we do want to look at.
He
the
probably has
CSM
other-
and things along those lines. I don't know if it's something that
So-
we can
But anyway.
use and integrate into the post-processing framework that we have. Because it doesn't like he's, the whole engineering tools on phase. So call it from other places.
No, I was
Yeah.
sitting right
And then
here.
the dedication, the digital, I've been desperate for something.
And
Oh, yeah.
Software. So that when I'm reviewing code, I can actually make sure that it's fit for better, not just it's not.
Yeah.
It says, this was.
Okay. Yeah, that would actually be interesting.
So if you'd be,
Well, I would have snapped.
if you'd be willing.
That's it. Yeah, well, we did it here.
You got some time. What are you laughing?
Oh, I'm just wondering how it's going to sound out the way, so you can.
Yes. I understand what you're saying. Yeah. I just, the quality is much better.
Oh, this one, this is-
Yeah.
Yeah.
Well, maybe in the short term, we'll be able to kind of patch things together.
So Johnny, you got in? Okay.
You could become someone who more so like me.
Oh,
I
okay.
suggest things.
Yeah. If you hang up and then you join.
Yeah, you hang up and then you rejoin. Yeah. There's an option.
All right, so I believe that
See,
Hansi
it's not obvious.
is going to be chairing this next session.
Yes, hello. Here I am.
Great, hi Hansi.
Hi. Hi, everyone.
You are here in person, but
Yeah, me too.
Here.
But I'm still here. And so I am happy to chair this afternoon's, or not this afternoon, this late morning's session on land ice plus polar climate. So I'd like to introduce our first speaker, who is Daniel Topol, who will be telling us about large-scale wind-driven Greenland melt influences on sea level rise projection uncertainty. So great.
Hi,
And the
everyone.
screen sharing worked and everything. Amazing. Thank you,
You can hear
Daniel.
me
Take it
and
away.
See the plus, right?
Yes, we can see it. Yeah.
Great.
Lovely.
So welcome everybody. Thanks for joining today's session. In this presentation, I'm going to speak about part of my PhD thesis. I'm currently a PhD candidate in Hungary, and I've been working on this topic for about 2 years now. With I listed some co-authors here who I acknowledge during this talk. So at first, let's take an outline of today's talk. I'm going to show some discrepancies first between connections of Greenland surface conditions and atmospheric circulation changes in observations compared with CMIP6 simulations. Then, to better quantify their relatively low sensitivity compared to observations, a circulation nudging is conducted with the CSM2 fully coupled model, including its active CSM CISM ice sheet model. We will see how large-scale circulation can actually contribute to enhancing surface melt and sea level rise through Greenland, and also assess some possibilities why climate models have trouble replicating observed connections between the atmosphere and ice sheets. So just to begin with, in this cartoon, I summarize the most important drivers and processes of Greenland surface changes. In recent decades, a high pressure system is getting more and more prevalent over Baffin Bay, which is also termed as blocking. So blocking is getting more and more enhanced over this region. It contributes to enhanced surface melt via regulating interactions between components of the energy balance, primarily long wave and short wave radiations. And dynamically, there's a diabatic descent and low level warming, and low level warm advection as well inside the anticyclone. And in addition, some ocean circulation processes also play a role, upwelling Atlantic waters, influencing the land terminating in the glaciers. So in a very recent work, we rethought the so-called Greenland blocking index to also account for large-scale circulation, because in this way we can quantify the sensitivity of the ice sheet to atmospheric circulation while taking into consideration large-scale atmospheric circulation, including tropical forcing. So first, compute the stream function from the global wind field, for example, at 500 hectopascal. Then spatial average the time varying stream function field over the ice sheet to get an index time series that we will call the Greenland stream function index, aka the GSI. And similarly, we calculate the surface temperature index over land points of the ice sheet. And then we can statistically remove the GSI from the surface temperature index via linear regression. The last step is to compare the raw trends in the surface temperature over the satellite area with the residual trends from that the GSI had been removed. So this method is used to estimate the sensitivity of the ice sheet to atmospheric forcing, actually large-scale atmospheric forcing. So in this first plot, I show the raw and the residual trends against each other in a scatter plot to better visualize their ratio. On the y-axis, I show the surface temperature trend, and then the x-axis, I show the trend that I obtain after having removed the GSI from surface temperature, so the residual SAT trend. The large red markers refer to 3 reanalysis products, and their mean is indicated with the diamond marker. The colorful markers, each of them are 29 individual simulations from CMIP6. The calculations are done separately for each model, so we would expect the models to spread around the reanalysis values. However, the models show relatively less contribution from the GSI to explain surface warming. In the upper x-axis, actually, the ratio of the raw and the residual surface temperature trends can be read, that are shown as percentage of the contribution from atmospheric forcing relative to the total trend. So the 45-degree line here indicates 0 contribution from atmospheric forcing. That's when the raw and the residual trends are the same. Therefore, nothing changes once we remove the GSI from surface temperature. In the mean of the reanalysis, the atmospheric forcing about 40% using annual mean data, but reaches up to 65% in the summer. And none of the models, or not even ensemble members from several large ensembles we checked, actually capture this magnitude of the observed contribution from the atmosphere. So we would expect the similar ratio. So here I just include these 2 numbers. So we would expect similar ratios of the raw and the residual warming in the models if they had the correct sensitivity to atmospheric circulation. And the fact that models and reanalysis are off suggests that models could simulate warming processes at least partially for wrong reasons. This is something known in the community. However, its impacts are left to be explored in further detail. So what we do is conduct wind nudging simulations with the CSM2, including its active ice sheet model, to assess the purely atmospheric forcing driven surface mass balance changes since the satellite era, since 1979. Although external forcing is kept constant in these simulations, we do not rule out the possibility that some of the wind changes are forced by CO2 in nature, because those are already in the winds that we prescribed in the model. But let's not focus on the internal versus forced details a bit now, because the sensitivity metric I just showed in the previous plot is irrespective of whether the observed wind changes are actually forced or internal. So in these plots on the right, I show the linear trend of the Greenland surface mass balance in the MAR regional climate model, boundary force by ERA5, and in our 4-member wind nudging simulations with the CISM2, where the CISM have nudging wind. And it's a 4-member means average, what is seen on this plot. So below, I show the SMB anomaly time series relative to the 1979-2020 mean in both the MAR with pink and in the CISM nudged ensemble mean with black and the individual simulations with gray. Since our nudging run captures about 2/3 of the spatial average SMB trend, also in the upper panels, note that the color codes are accordingly adjusted just to better visualize the trend patterns that are very similar. So if models simulated warming for the same reasons as observed, we would see the marker spread around the reanalysis again. So just to remind why we do this again. So these modeling results support that we use the observed GSI to remove its effect from the total mass balance time series 2, actually from the satellite observations. So here, in a recent paper, we concluded that the mass loss acceleration between 1990 and 2012 was about 45% driven by atmospheric forcing. And this is a conservative lower bound estimate, because before the regression model, the underlying trends, secular trends, are removed from both the mass balance time series and from the GSI2. So in this plot, the pink line shows the multiple satellite source derivative mass balance time series collected by the INBI team, and the blue is the residual mass balance after removing the gray, which is the GSI. So in this paper, I cited on the right corner, we also look at ocean temperatures in nudging runs, which also respond to wind forcing for the upper few hundred meters. And we are planning to connect these to how glaciers respond to this ocean warming, especially the ocean terminating glaciers, obviously. But with that, we can further use the CISM2 because of its high resolution and active interactions with the CSM2. So next, I would like to show some of our early results from searching from an underlying mechanism why models would show less circulation changes in the Arctic compared to the observed contribution from the atmosphere. So this is a simple correlation map between the GSI in summer and the global sea surface temperatures. We know that tropical forcing, tropical SSTs influence extratropical climate, and that tropical convergence anomalies are sources to Russell wave dispersion. So we think that SST variability might be key. So that's why I show here the SST variability in ERSST version 5, which is kind of observation, and in SIMPX models, 29 models, each model, and then averaged. So on the right, the ANSO-related 2 to 8 year variability is shown. In particular, I apply a 2 to 8 year bandpass filter, and then the filtered variances ratio is plotted to the total variance. So that's the ratio of the filter variance to the total variance. Civ6 models show a very similar picture to the observation. However, if I redo the same filtering, but selecting lower frequencies, the 8 to 40 year band, then the variance ratio is much smaller in SIMP6 than in ERSST, especially over that red box that I highlighted. Since models project relatively uniform SST gradient in the tropics in response to greenhouse forcing, or at least some of them, the lack of lower frequency variability could explain the differences between Greenland's sensitivity to the atmosphere in models and the observation. So that SST is key. We know, and it would be nice to conclude with adding some plots with the CSM2 pacemaker, because if the SST is indeed forcing, then we would expect to see a better representation of the Greenland surface to atmospheric connections. So that's why I included these runs as the next step, or at least the last step, actually. So this is the same sensitivity plot to the one I showed for CIMIP6, but now for the summer, and using surface air temperature over Greenland. And I calculate the GSI in each of the members separately, and then remove it from the surface temperature index in various CSM2 experiments. So in the 100-member large ensemble, split it to two 50 members according to CIMIP6 or the biomass burning emissions forcings, as with the blue and the black dots, and the smaller markers refer to each of the ensemble members. And then also I include with yellow the CSM TOGA, Tropical Ocean Global Atmosphere, AMIP type run, and the CSM2 pacemaker simulation where SSTs are prescribed. And you see that, and I mentioned earlier how the summer sensitivity bias is even more pronounced in the model. Now you can see, and however, the CSM2 pacemaker runs show remarkable improvements in terms of capturing the circulation-driven warming over the ice sheet, which signifies that tropical variability may be key to explain the differences seen. So our results basically underlie that when assessing the ice sheet sensitivity to CO2 forcing or other external forcing, we need to take into account that models underestimate the atmospheric component. Whether the atmospheric response is forced or internal is still highly uncertain, but we will definitely do more in this direction because potentially important consequence would be to be able to narrow down the projection uncertainties around sea level rise, at least from Greenland. And if you'd like to know more, I linked here our recent paper, and I'm open for any questions.
Awesome. Thanks, Daniel. Questions for Daniel?
There's one in the room, Hansi, so.
Oh, great.
Just to clarify, did I get that right? That you think the solution to explaining melt and mass loss in Greenland lies in tropical winds? Or did I understand this wrong?
As far as I think I understood the question, but could you repeat once more? It was very not very loud.
Could you speak to it?
Oh, okay. I'm trying to speak to the
Yeah.
speaker, which is now okay.
Oh, the speaker is here actually. You're fine when you
Yes,
see
you're
it.
fine there. I think if you just sit there.
Okay, here.
Yeah.
So just to clarify, you're finding that the atmospheric effects in the tropics play a big part in melting in the Greenland ice sheet. Is that right? Or did I understand you wrong?
So the local ice sheet atmosphere connections might depend on better resolving tropical SST variability because of the TAL connections or the tropical extratropical response.
Right. Okay. Thanks.
Yeah, so related to that, the pacemaker experiments, they do better. But I was just curious, I mean, there still looks like there's some stuff to explain in terms of, that connection between that particular sort of atmospheric circulation pattern and that just not being in models. Why do you think that is? What do you think that extra stuff in there is?
Yeah, that's I think $1 million question here. So that could easily be a forced response bias in the models, which could include that models somehow don't reproduce these connections, or as I mentioned, that the low frequency SST variability is yet to be better understood in the tropics, given the short observational record.
That the Greenland stream function index, has there been much written about that and sort of the mechanisms by which it can drive sort of Greenland surface mass balance changes?
Yeah, the paper I linked, we wrote about it.
The 2022 paper?
Yeah. So it was published in November.
Okay, great. I'll take a look at that.
Okay.
Okay, thank you.
Thank you.
I think we have time for a couple questions, or we can move on. Okay. Oh, Any questions? No. Okay. Thank you so much, Daniel. And we will move on now to our next speaker, who is Christine Shields, who will be talking about identifying high latitude atmospheric rivers with machine learning. Yay! And her screen sharing works as well.
I think we're set. Cool.
Yeah, it looks great. Thank you.
Alrighty, so thanks for giving me the opportunity to speak to you guys today. This is going to be a little bit different than what we've already been talking about. Before I sort of launch into everything, I wanted to take time to thank my collaborators, because without them, I would not be able to do this today, because I'm not really a machine learning person. I'm more of an atmospheric scientist. So I got a lot of help from Tegan King, Katie Dagon, Sol Kim, and Annette Greiner. So this is the basic outline. The first part, I just sort of want to get everyone on the same page as to what high latitude atmospheric rivers actually are. And then hopefully I will convince you as to why we need polar specific detectors. And so one of the things we do in the atmospheric river world is we to try to identify them in grid data sets, we have these things called atmospheric river detection tools. And they tend to be sort of global. A lot of them tend to be global, and so I want to convince you that we need ones that are very specific to high latitudes in order to capture these things correctly. And then tell you that, then we'll switch over to the machine learning part. We're saying this is an option. And full disclosure, this is really just very preliminary. We just started this project, so I don't really have actual science results, but I do want to sort of step you through what we're doing so far and where we are on our project. Okay, so what is an atmospheric river? They've been in the news a lot, so I think maybe a lot of people probably know what they are, but let's just sort of explain what they are. There are these synoptic scale features, weather features, sort of filamentary in nature. You can see this animation I grabbed off of a NOAA website, where the blues are total precipitable water. So this is just, there's a moisture stream, and what's happening with the atmospheric river is that it's transporting moisture from lower latitudes to higher latitudes. So these are examples of something we call the Pineapple Express. So you can see the Hawaii is dotted there. So that's why it's sort of called Hawaii Pineapple Express, because it's moving moisture from the Hawaiian region into the mid latitudes. And these things tend to, we can call them drought busters. We can go from, a region like in California having major drought to not necessarily being in drought anymore, with just a series of atmospheric rivers, which recently happened in this past January. There was a bunch of atmospheric rivers that actually hit the west coast of North America, and many regions in California were brought out of a drought as a result of this series of atmospheric rivers. They can, and as you probably saw in the news, they also can cause a lot of flooding. So for polar, the impacts are more things along along the lines of impacts to sea ice and impacts to the surface mass balance. So here are some examples of high latitude atmospheric rivers. The one on the left happened over Antarctica last year. This was in conjunction with the extreme heat wave that Antarctica experienced. I think don't see on the ice sheet there what above 0 Celsius, so above freezing, and so there was an atmospheric river that was happening concurrently with that heat wave, and so that tends to happen over in Antarctica. Sometimes you get these blocking events and you get atmospheric rivers, and that's a nice picture from the satellite that shows you that moisture stream. On the ones on the right are Arctic atmospheric rivers. The one with a little animation at the top, I'm showing you actually it's a tropical to extratropical to high latitude. It started out, this was I think September of last year with Hurricane Fiona. You can see that hurricane signature. And then it transitions into an extratropical cyclone, and then that moisture stream continues into the tip of Greenland and then continues further. That's a great example of a high impact atmospheric river. And then the one on the bottom right is one that is impacting the west coast of Alaska there. where this particular atmospheric river happened a few years ago, and it broke the 24-hour rainfall record for Nome. So these are just sort of the beasts that we're talking about. All right. So one of the things in atmospheric river science, in terms of uncertainty in atmospheric rivers, is how we detect them. And so I'm part of a project called ARTNet, which is the Atmospheric River Tracking Method Intercomparison Project. And this is different ways we can actually detect and define atmospheric rivers in these gridded data sets, which I sort of alluded to earlier. So all those different colored contours are the different detectors, different atmospheric river detection tools, the acronym that you can see if there is ARDT, in case I had that spattered somewhere else in the presentation, that's what that is. So there's a lot of different ways that we can detect them, and a lot of these things are threshold based. So if the geometry looks a certain way and the integrated vapor transport or the moisture stream is a certain amount, then we have an atmospheric river. But these different detectors have different ways of doing things, and typically for a global atmospheric river detector, they tend to be sort of designed for mid-latitudes. And so you have the zonal and the meridional components of the wind are equally weighted. So one of my arguments is that for regional, specifically for Antarctica or Arctic, you actually need to weight the meridional component a little bit more if you actually want to capture atmospheric rivers into the high latitude regions. Yeah, so I think that's all I wanted to say about this slide. So this is just another example of uncertainty in terms of the climatology. So I have 3 different locations around Antarctica that I'm pointing to, and these are the normalized climatology of atmospheric river frequency. And I'm looking at both the MERA2 and the ERA5 data sets here. So the gray and the black are Antarctic specific detectors. So these ones were detected or were developed by Jonathan Willey. And so that has a very different climatological signature compared to the global ones, which are the green and the blue. The green is just all the global detectors that are in the ARTNet database, and the blue ones are a subset of those that actually are global, but they try to allow for polar events by lowering thresholds or changing geometry in some way. But you can see the global, even though there's polar constraints in the global detectors, they're quite similar, the blues and the greens, but they're very different from the grays. So there is quite a bit of uncertainty here. So what is right and what is wrong? I don't think there's a case that's right or a case that's wrong. It's more about what science question you are asking and what region you're looking at. So this is a way of looking at it in terms of atmospheric river frequency. As I call these heat maps, where the heat map is just simply the number of atmospheric rivers that are occurring at a particular time and place, plotted up in a spatial way. So what we're looking at here is the difference between the regional detectors and the global detectors. So the oranges and the warmer colors are pulling out where the Antarctic or the Arctic specific ARDT are actually capturing more atmospheric rivers and more events than the global ones. And so you can see in terms of the high latitudes over Antarctica and over Greenland, you actually, if you're using these specific ones that are meridionally based, you're going to capture more atmospheric rivers onto the ice sheet. But if you're looking at the storm track, for example, like in Greenland, the North Atlantic, the global ones actually capture more atmospheric rivers. So you really need to choose your detector depending on what your science question is and where you're looking at. That's sort of the point of this whole exercise. All right, so this is my last little motivational slide in terms of convincing you why we need both atmospheric river high latitude specific detectors and why we want to do machine learning. These are a variety of the different ARTNet detectors, and we're looking at the air frequency around the different longitudes of Antarctica. And you can see the vast majority of these really only capture the atmospheric rivers in this Antarctic Peninsula area. Here we go. trying to get my mouse. I don't know if anyone can see it. Maybe not. So it's basically just capturing over the Antarctic Peninsula, most of these global ones. And this is because these are designed for mid-latitudes, or they're equally weighting the meridional and the zonal components. And so you're just capturing what's in the storm track around the Southern Ocean. So where is the machine learning one in this? The machine learning one is in the upper right-hand corner, and here's a bigger picture of it. This was our one contribution to the ArtNet database from our machine learning group, and this was the ClimateNet. For those of you who know a little bit about the machine learning world, probably have heard of ClimateNet. And this is what it comes up with for both the MERA and the reanalysis too. It's not necessarily encouraging, but this is really just because the training data was based with mid-latitude training data. So your machine learning is really only as good as your training data. So the idea we have here is to go back to the drawing board and go back and create more training data. Laughing at the little dogs and cats and stuff. They're very cute. So yeah, so the idea is to get better training data for high latitude. So this is sort of, I grabbed this, I think, from Karthik's paper. This is the paper there, Pravat and Kazanov et al. This was in Geoscientific Model Development a couple of years ago. It explains the process. And so essentially what it's using is it's basically creating this instance segmentation masks to identify what an atmospheric river looks like. In this case, we're identifying dogs, cats, and ducks. But what they did in this paper is they identified both tropical cyclones and atmospheric rivers, but for mid-latitudes. So we're going to go back and make these draw masks and outlines for atmospheric rivers, but just for the high latitudes over Antarctica and Arctic. So this is sort of the red circle I have over human labeling. This is the very first step. So we need to go back and we need to actually go conduct what we're calling labeling campaigns to create masks that are appropriate for high latitude atmospheric rivers. And so this is where Saul and Annette came in. They basically have this wonderful climate contouring labeling tool to create the masks. And so it's a website, you go in and you draw the atmospheric rivers in these around Antarctica or that are going into the Arctic. And you draw it and then it goes into this server, and then we save it, and then we eventually use those masks to train the data. So I'm going to talk a little bit about how this tool works, just in terms of like how we do the hand labeling. So there's a number of variables that we can look at when we're doing the hand labeling. Integrated vapor transport, IVT, is a very common metric or variable that we use for atmospheric rivers. This is basically combines moisture and wind and integrated throughout the atmosphere. Integrated water vapor is another one. This is simply the integrated water throughout the atmosphere. So that's another common way to identify atmospheric rivers, particularly in satellite data. Sea level pressure and winds are other ones that you can also use. And all these channels were available in this tool to create these masks. One of the things we did specific to for the high latitudes and different from the earlier labeling campaigns for ClimateNet in the mid latitudes was to disallow anything that didn't hit 60 north or 60 south. So we already have all the masks and the training data that we want for anything that's mid latitude. So we don't really need to add to that database. What we really need is we really need masks that are atmospheric rivers that actually get into the Arctic or get onto Antarctica. And so I put those little, brown circles around where we, when we conducted these labeling campaigns, said, okay, if the atmospheric river doesn't reach 60 north or 60 south, then we're not going to include it. And these are just sort of some examples of what that looks like. All right, so what's the labeling campaign, you ask? So what labeling campaign is like, I have a bunch of you sitting here right now, and I give you the website, and then I So, then you can, using your, your computer, you draw little outlines around the different atmospheric rivers, and then you're satisfied with your image, and then you hit go, and then it goes magically into a server. And so it really is just sort of this crowdsourced idea of trying to get as many people to draw masks, or connect the dots or whatever for atmospheric rivers as possible. So I conducted four different labeling campaigns specifically for this. First one was at CU last summer. We also did an informal one at the Polar AMS in Wisconsin last year. The biggest one where I got the most labels was at the IARC, and that's an International Atmospheric River Conference, and that was in Santiago, Chile this last October. And then I had random labeling where, on board, and then I go to the contouring website and I draw some atmospheric rivers to add to the suite of masks that we had. So overall, we have 301 Antarctic masks because we started on Antarctica before we did Arctic. We only have 92 at this point, which I'm fairly certain we'll need more. But right now, what we're doing is we went through a quality control process where we tossed out things that clearly weren't atmospheric rivers and try to correct mistakes. And those are the people that helped me with the quality control. And now that we're done with that we're actually doing the process of starting the training. And this is what Tegan is doing right now. She's actually, as we speak, remapping, doing this first step, remapping everything onto the appropriate polar coordinate polar coordinate system, sorry. And so we can actually start the training process. We're starting with TMQ, which is the total mass of specific humidity. That's the same thing as integrated water vapor. I'm sort of using those interchangeably. The data that we're using and that we trained and created the masks on is CAM5 data at 1/4 degree. And then we're separating out different pools of training data versus testing data and validation. And then Tegan uses this weights and balances tool to do the training. So that's happening now. So this is a really busy slide, and I don't expect everyone to get out of it, but I did want to include it. This is something that Katie gave me to show you the enormous amount of work that actually goes into any type of machine learning process. So if you're a machine learner or learnee, I'm not sure what the right expression is, you know that it's like a data, you've heard this many times, it's a data hungry type of process, and it's very iterative. And so really we're just here up on this very first part for these polar atmospheric river training, where we've gotten the tool, we've gotten the masks, and now we're in the training process. But eventually, once we have our data trained, we'll go to where we actually want to do our science. So this is an example of what Katie's done already for the global atmospheric rivers using CSM13 high resolution. This is the IHESP simulations. And so there's a whole ton of processing that has to happen with that data. And then we land in this box where we're using the masks and the training data, and we're using the CSM data. And then we finally, this is our detector box right here. So this is our tool. And then out pops out what we consider atmospheric rivers. And so this is Katie's image that she just a snapshot of a random time where this is what, these were the atmospheric rivers that were detected. And the blue bobs for this case she also did tropical cyclones. So those are the tropical cyclones that were detected. And then you can go on and actually start to do science with it. So this bottom one, the global map with the blues is basically atmospheric river frequency. And then this final box over here, she's just looking at precipitation along the West Coast. So eventually we will get here, but right now we're really at this very beginning step. Okay, so to summarize, global ARTTs are not necessarily appropriate for Antarctica and Arctic. I didn't put Arctic there, sorry. Hopefully I've convinced you that we really need high latitude specific detectors. Machine learning is one way to avoid these pitfalls that we have that are associated with classic thresholding techniques. And this becomes particularly important when we go into climate change, when the background moisture is just going to increase because of Clausius-Clapeyron. So how we define an atmospheric river under climate change is a big science question. So the global machine learning RDTs are trained with data designed to capture the appropriate atmospheric rivers, and then we're using this climate tool to create our masks, and we are running these through the CGNet framework, which is sort of a smaller version of the ClimateNet deep learning tools to eventually come up with an ARDT that's appropriate for high latitudes. And if anyone is interested in helping me create training data, because I'm pretty sure I'm going to need more Arctic data, just please get a hold of me, and then we can join the project. So thanks.
Cool.
Awesome. Thank you, Christine. So let's open up to questions, please. Tree.
This is more of a comment than a question, but just if you're into Tetris or Candy Crush, I highly recommend doing this. That's all.
It's a fun tool, just saying.
So if you want a hint on how to make more training data,
yeah.
So I do work with neural networks. You cannot train the CNN. I mean, sure, you do need hundreds of training data, but you need hundreds of thousands of training data for a deep learning network, which is a convolutional neural network, to work. So you want to apply a few tricks, like make a simple neural network that helps you mass generate more training data out of the man-made training data sets, thereby to do that leap from the hundreds to the 100,000s. I mean, sure, you need the community to help, but you don't want to make tens of thousands of training data, but you cannot constrain the neural network appropriately. Then I had a thought about, why do you actually need different ones for Antarctica? So I thought you might want to segment down like little chops, chop down your Arctic rivers. Use a local reprojection into something that's rectangular meter-based coordinate system like UTM or polar stereographic, depending on where you are. Then feed those data to initiate the nodes of your neural network. That may be enough to be able to exhaust the patterns of the low latitude neural atmospheric rivers to provide a database, because a lot of it depends on shape, on the gradient and all this. And so the main hiccup is probably, like you said, it overgrades latitude versus longitude as the projection goes harder, because then at 70 degrees it's like 1 to 3. So if you reproject all these things locally, you make choppy tools. So we have a tool which we have developed for NSF, Office of Advanced Cyber Infrastructure, but the student working on it hasn't given out his thesis yet. But otherwise, we are committed to making this a community project, like we have to. That's how it's funded. So it's more like a library tool, and it allows to handle projections and imagery, and sort of, it has a lot of the utility functions. It still needs all those good folks who have provided you the input.
So let's talk later.
So there's sort of a few thoughts to accelerate the thing.
Awesome. Yeah, thank you.
That's why it detects African elephant and pizza so well, because there are so many examples of it.
Cool.
Great, thank you. I just have a quick question.
Oh, Dave has a question.
Oh, okay, great. So many questions. Okay.
This is a naive question. I mean, in terms of low latitude versus high latitude, I mean, does the elevation of the atmospheric river matter here? And then the water phase, does the water phase change too?
Yeah,
so
absolutely.
are those both counted for?
Yeah, so what typically one of the atmospheric rivers it occurs in the boundary layer. So like if we're just looking at the sea level, we're looking maybe at surface to 700 millibar. And like for the west coast of the US, for example, what causes the rain is the fact that you have the orography there as the lifting mechanism. The North Atlantic ARs have that are more attached to the extratropical cyclones. The lifting mechanism is actually the warm conveyor belt. So there's less need for the topography for those types of atmospheric rivers. For Antarctica, you do have the major topography there, so that it is a piece of it. And so one of the students I work with at CU just actually published a paper where she's looking at the different, the temperature of the atmospheric river as you go up, you know, in the, you know, the atmosphere, whatever. So yeah, those are all definitely components. So one of the things that's unique to the high latitude, or what the algorithm that we're using right now, that's threshold based but Antarctic specific. It actually the geometry is more important than, let's say, the moisture, because you know when you get these like cold and relatively dry environments, sometimes the moisture threshold isn't necessarily the best way to define or to find the outline of the atmospheric river. Did that answer your question? Okay.
Yeah. Yeah, can I just piggyback on what
Yeah.
you said? In the heat maps that you showed the difference between the like high latitude AR detection tools versus the global one, you got a big improvement over Antarctica and Greenland, but over the Central Arctic, it seemed minimal. I don't know, I couldn't really see the colors that well. Does it link to the topography and the fact that over these high sheet and the fact that you have this kind of orographic length, it really improves when you have these high latitude specific ones?
Yeah, I think the for that one, maybe I should share my screen again. There. This guy, yeah. So yeah, so the I mean the Arctic here, I think that's just a function of like, you know, that's not a real thing right here. But I think we're over the Greenland for sure is the fact that it's a meridional specific.
Right.
We also get a little bit more over like the Siberia area. There's also a type of atmospheric river called the Siberian areas, which are gravitous moisture from a state of permafrost, which is not well understood at this point, but it is a thing that people are looking at. But I think like you know, there's the incidence of atmospheric rivers actually making it this far north, or there's not that many of them. So the statistics, I think, are probably not well understood in general. So you have, I mean, there's really two different I would say types of atmospheric rivers. Ones that are definitely connected to extratropical cyclones, and these are the ones that are more in the storm track, and the global ones will get those fun. And then you have these ones that are more meridional focused, and those are the ones that are actually where the atmospheric river would actually interact with the topography onto Greenland, and then use that as you squeeze every bit of moisture out and then precipitate. There was a big atmospheric river event over Greenland at the top of the ice sheet a couple of years ago, and I can't remember the paper off the top of my head, but it was raining up there, and that was a very warm event. So there was affecting both moisture and warm temperatures. And if you ask me later, I'll look up the paper and I can give you. But yeah, but that was a pretty famous, for atmospheric river famous, you know, relatively famous event that happened ever. Did that answer your question?
Yeah.
Okay, great. Thank you, Christine. I'm gonna just to stay on time. It sounds like there's a lot of discussion that is going to continue about this. So please feel free, but let's move on to the next talk, which is the last one before lunch. So Ute Hertzfeld will be speaking about sea ice cover in the new Arctic using ISAT.
So it works. Okay, sounds good. So Gunther will push the slides forward. My apologies, this is like my HU talk. Someone crashed into me on I-70 a couple of days ago, so I could not put new slides into this talk. So you're just going to hear the HU talk, and I explain you other things as we use these slides as a tablet. Gunther, it's a PDF. You should be able to make this like this central slide, fill the entire screen. It's just sort of there is few full screen. Yeah, very good. Okay. All right. So the talk is about the transformation of the Arctic sea ice cover in the new Arctic, but it's based mostly on insights from ISA2 data, which where we made a new algorithm which actually allowed us to detect melt ponds. And now we have an Arctic-wide melt pond database, actually. So hopefully that's of relevance. Like it's big enough so you could model off of it. It's not just limited to sort of some one-off examples. And of course, anyone in this, the talks co-authored by so many people because the ISA2 project also flew the Arctic Summer Sea Ice campaign this summer. So a lot of the people, Nathan Kurtz, Tom Newman, Rachel, Marco, and so forth, are the people who have collected the data out of Thule. All right, next slide. So of course, in this community, we don't really need this first slide. The Arctic sea ice has been reported to reach historic lows, right? And we see the transition to a seasonal rather than a perennial sea ice cover sort of happening. And then the key process is melt ponding. So the predictions based on the models, as you all know better than me, diverge. But so the key thing we're looking at here is the individual melt ponds are all very small. So they're tiny surface signatures, but there is hundreds and hundreds of thousands of them. So now we've made a tool that allows us to use very many small surface signatures of a large-scale process. And then we can map that out and get maps of where ponds occur and learn about changes in melt pond processes. Okay, next. So here's some examples. So for those of you who are not familiar with ISAT2, it's what's called a photon counting micropole sensor. And it sends home individual dots, where every dot is a return from a single photon. If you look outside, it's bright tons of photons. And so it doesn't record all the photons, only the ones in 532, which is green light, which is the frequency of the sensor. But then that's why you see in all the figures, you see all these dots. Those are the ISA2 RLO3 project 3 data product recorded photons. And then we see the ponds, but on the official ISA2 product, which contains sort of freeboard and surface height and a bunch of other things about the sea ice, it does not label two surfaces. It decides on one surface. And why is this so? Well, before launch, people didn't know that actually ISA2 would have this capability to go through water or through slush and show two distinguishable surfaces. So this is actually an example made by Ellen Buckley using a handmade algorithm where she sort of finds ponds by hand, and then it's semi-automatic to calculate where the top and the bottom would be. You see the green is the reported product. So now we're putting a CSDR pond detector onto the official CS products next. Okay, so here is sort of the idea. You see the Arctic multi-year sea ice zone, where a lot of the ridging, where the old ice is left, where melting and ice formation is really complex. And then in the slide below that, you see the data we have so far processed on the NASA cloud, which is called ADAPT. And it found, in this example, I think, 100,000 ponds, 10,000 ponds, tons of ponds anyways. And so on the right is an example on how we are finding ponds automatically, because we can't afford to have people find ponds individually. I mean, Ellen found like 500 through bunches of tracks and validated them all. So her data set serves as a validation of the pond algorithm. And we have written a new algorithm called the density dimension for bifurcating sea ice reflectors called DDA bifurcate sea ice, and it will automatically move along complex ice and decide, hey, there are two surfaces, and then follow two surfaces, map out the pond depth, and keep on moving and put the two surfaces together. And then we ran that over oodles and oodles of data for a whole summer. Next. Okay, so this is sort of all, I mean, we record the talk, so you can look this up. This is just specs of the sensor. It has a long track spacing of data, which is 70 centimeters potentially under clear sky atmospheric conditions, right? So if there's too many clouds, then no data, of course, and we throw out the cloudy data. So you see that you have a really high resolution database, so we can then produce ponds which are 15 meters minimum in diameter, or I mean where diameter is of drag floods. Okay, next. what's all this good stuff? So the algorithm is the official algorithm for atmospheric data products. So I made various ones of these density dimension algorithms. I think I talked about them before. The new one is the bifurcate sea ice, and we did actually submit a paper on it. The difference is, if you look at big melt ponds like in the ice sheets, you have a pretty robust mathematical problem. You have deep ponds, hundreds of meters long, if not kilometers long. So you have a lot of data to decide, do I have a pond or not? The sea ice is really small, and you don't have much of a depth resolution, and you have complex ice or refreezing ice and all this stuff. And I think that talks by Melinda Webster and Mosaic and how complex the sea ice actually is when you look at it. So it's a way more ill-posed mathematical problem to find and get all these ponds right. The DDA is, since you just had a talk about neural networks, it uses core mathematics of a neural network to actually do the determination between signal and noise, and it uses the activation function of a neural network to do the data aggregation. But it's not a neural network, it's an auto-adaptive algorithm. So once set, it runs way faster over like terabytes a day, which is what ISA2 collects. So it can keep up with data collection. And so you sort of use some parts of knowing it's intelligent, but then you want it to adapt to daylight, night, apparent surface reflectance and all that, and just keep on checking. So it's not a neural network. A neural network wouldn't be fast enough to be an operational algorithm, because you want to implement this, like the ISA2 project will implement this thing as the new operational algorithm for sea ice. So there should be a melt pond component sometime. So, okay. Next. So here are some examples. If you sort of want to know how it works, you see the recorded photons in the upper left, which is all the dots. And you kind of see what the surface is, but you don't see the details. And then you separate into noise and signal, and you calculate what I call the density field using a radial basis function. And then the green plot is kind of hard to understand because you make density in additional dimension. That's where the auto-adaptive threshold function runs. And then you have a ground follower, which makes you points. Next. Okay, so now we compare. So we use the handmade data that Ellen Buckley has made and compare, and it looks good. Next. So her pond algorithm only works for ponds. Ours works like everywhere, and then it makes ponds. Okay, so here are some examples, just so you don't think we have like 3 examples where it works, and Twilin has made more examples and nice plots for the paper, but she has actually class now, so else she could give the talk. Next. Okay, next slide. So yeah, here are some more. So you see the overall density, like the absolute density indicated by the colors, can totally change, as can the contrast between background photons above the ice and below the ice in the water, and so the algorithm handles most of these situations reasonably well. Next, we should get to the campaign. There is a bit of a problem with saturation, so you can get artifacts a certain distance just below the surface. Next. What's this here? These are some comparisons. Oh yeah, so the question is now you want to make sure you actually have observations of the sea ice during summer melt conditions. So that's why the ISA2 project flew the summer sea ice campaign. And there should be a slide of more of the ice. Next. Yeah, so here are some tracks or flight paths out of Thule. And they flew Elvis, which is a camera, and also a 1064, which is twice 532. The red white swath imaging laser altimeter system, operated by Brian Blair and Michelle Houghton, and then an instrument made by Chiroptera, which is a bicolor instrument. It uses near infrared and green, and it's operated by Kutamis of the University of Texas. So you want to look at the reflections in 2 different bands and have imagery in addition, so you can actually see, is this a pond or is it just sort of ice transforming and becoming puddly and whatnot. Next. So then here are some first examples showing, for instance, Elvis imagery. There's tons of these images. Elvis has to fly at high altitude, while Chiroptera has to fly at low altitude. And then the right is William's first crack at looking at the Chiroptera data in the two bands. It's a sensor which has never been used over sea ice. It's been used for ponds and puddles in sort of in Florida, where you have murky water. You have totally different reflecting conditions than on the sea ice. So that makes it sort of non-trivial. All the data is open source, open science. So if anyone else wishes to hack at them, you totally can. It's sort of NASA's move to open science, right? Once they can't give it to the PI. So there are 4 PIs selected to analyze the data, and myself, our group, for analyzing the data and making the algorithm. But so they have to release the data. They can't just give them to me. Okay, so if you guys want to, you can. Right, next. So here is some example of actually a glacier project. I have the Arctic, and we will fly some ice front observations in this realm between glacier ice, ice carving, sea ice forming, so you can get a transition of all the different ice types, because that creates a challenge for any type of automated algorithm. You don't want to really rely on masks. So far, the ISA2 products rely on masks, but the world changes. It's a change detection satellite. So as something like a surge glacier pushes out into the Arctic, the front changes really fast where it is, and then you have carved ice blocks, you have sea ice forming in the front, and you see like in the middle, the sea ice is just refrozen, breaking up. So you have these really complex environments. So part of the algorithm challenge is to make sure this is, you like really know what you have before you feed it into any kind of a model. So that's what we are providing to do. Next, is that it? Yeah, here is how we, a bit on how we collect the feed data. So, I mean, we charter a helicopter, go to Svalbard and put out GPSs, and we fly a laser in the camera and so forth. And underfly ISA2 tracks. So we can get within like 10 meters of the observation tracks to make sure that actually if we see a pond, it's a pond and so forth. We haven't been able to go because of COVID. So hopefully we go this year. Svalbard has stayed COVID-free, so I guess they did the right thing, locking everyone out. So no, they didn't. They didn't even let Norwegians in. They opened for cruise ships again this summer, but no one was able to say, huh?
I will say that it's not COVID.
You go on the cruise ship.
No, but I went this summer and I got COVID.
Well, too bad. Like, what my fault, I didn't go. Okay, anyways. All right, so then next, let's see what else we have. So here are some of the analysis. It in essence shows like the ISA2 track, the predicted ISA2 track, the actual one, and our flight tracks. And you can see how close we can get. This is obviously over crevasses, not over sea ice, but it's the same method. So we can get really good validation data in the sense of repeatability. We have a whole paper on the geodesy. So you can read that if you want to know. But we need these kinds of things over sea ice to make sure that we capture the sea ice specific features in the automated sea ice processing algorithm. Next. So now I was going to speak, and I'll just say this a bit about the paper that Ellen Buckley and us just got out. She used the entire the database with the tens of thousands of ponds to look at changes in the melt evolution of the ponds on the sea ice. And so I was actually planning to put these slides into my talk last night, but it wouldn't recompile, too bad for me. So it's because I made, anyways, it's a LaTeX hack. So I do know how to hack it. I just didn't have a couple of hours in text. But so you should, Ellen just published the preprint of the paper in the cryosphere, and it's done after AGU, so that's why the slides are not in there. But you can actually see the amazing detail that you find now in how the ponds grow bigger, then they go deeper, and then they start to shrink, and then they drain, and all this you can actually pull out of a database of tens of thousands of observed ponds. So it's kind of rather interesting that way. So anything you'd actually want to learn about the sea ice processes is in this new paper by Ellen, and Linda Webster's on it, and Chiney, of course, was the advisor. So you can see the types of processes, and then maybe someone wants to feed this into modeling or not. Okay, I think that's it. Do you have questions? Yes.
So I'm really happy to see this operationalized for sea ice, that it's actually not just one region, but all over the place. It's great. Has that been done for land ice? I mean,
no, we want the community
why not?
to say, why? Because we need community support. So I have the algorithm. The CS community has been really, really active in saying, we want such an operational algorithm. The low-level product doesn't cut it.
Just to add that, I mean, just to add to that, I've been.
Well, I have the algorithm.
I know.
It's just not
like-
operational.
Okay,
So
they should
we
be
are
operational.
the project will now use DDA bifurcate for sea ice to make the meltpoint product. If there are people in land ice who would like to have high resolution crevasses of the Greenland ice sheet.
Yes. Okay.
It's possible. Like, I mean, I have the algorithm.
It actually seems kind of strange because land ice is an easier problem than.
It's an easier problem because it actually uses DDA ice 1, not DDA ice 2, not bifurcate. So it is a harder problem to make the sea ice code.
Yeah. Okay.
Anyways, we are actually running DDA ice 1 for all of Greenland on the NASA cloud. So it does work. It runs fast enough to, I don't know. So it takes less than a tenth of the time it takes to collect all the data of the Greenland ice sheet, and Antarctica is more than 9 times as big. I haven't done Antarctica, but that kind of tells you it will be fast enough. But we're only running on the cloud. So if you run on the high-end computers, that dollar takes.
Yeah.
But we have, like, the NASA cloud is the single cloud that NASA investigators don't have to pay through the nose for using that type of computer access. Like, you guys are at NCAR and you can all use the NCAR computers. Fine, but they are sort of there for modeling. So you need to find a computational resource without paying thousands of dollars on Amazon. So I'm running on Adapt because I should. But yes, I would love to provide the algorithm to the project. I don't want to run it myself, right? So I don't think if I put the algorithm on open source, anyone wants to step out and run it operationally, because there is a difference. You want dollars to do it and the data to just sort of be there.
That's correct. This is a software engineer's job.
No, I mean, also we found, even if you go from the land ice detection problem, like we have it all working for Jakobshavn, we have it for Nightgreen. Now you run all the data, all of a sudden, boom, you see these artifacts. You have like 1,000-meter errors. What is this? Well, this is from some kind of test track they did, and there is a flag called whatnot, which of course you don't see if you don't run all the data. All of a sudden, hey, it can look like it jumps in the cloud, but it's an instrument error, and you see all sorts of errors, like 4 different kinds, which weren't there before. So now we hacked all those errors out. So it's a difference between, hey, this is a piece of code, you run it. It's not. All sorts of shit happens, which you don't like personally want to deal with, right? So, other questions? Oh, there are more questions. Yes.
Sorry.
So my question goes a bit beyond the pure data product, but maybe an application that you might be aware of. Has someone tried to track individual points, or let's say ice, at different time steps, so that you could see the evolution of individual pond development? So, but then CI's motion product to combine it with.
So those are all, yes, cool questions, but they're all different like types of products. So Ellen has looked at the pond evolution. Okay, so she sort of looks at the ponds in. You have repeat tracks, so you can look at how individual ponds form, but ISA2 only repeats every 90 days. So you want to look a bit at the statistics. So that's Ellen Buckley's PhD, or not all of it. Anyway, so she wrote her PhD looking at pond evolution. We have looked at crevasse evolution in our book, because I'm a glaciologist more than a CS person. Okay. And then the velocity products, I think Mark Judy is still making this old velocity, the same velocity product he's made for Jim Maslany for a long time. So the advantage of that is you have sort of a continuous product. And I think they track motion of ice flows based on, I forgot what satellite data. So you can like get information on how pieces of ice move if you want to track, because it's important, of course, the ice moves, right? So the same pond is not going to be here. Whereas the glacier ice moves 20 meters a day, but roughly it's not like moving in hours out of your field of view. There were more people with more questions, and lunch is right after. Yes.
My question is complementary to Vida's question about, have you thought about creating category to try to study the meltdowns based on the area, the depth, the perimeter, so we can like compare with other meltdown data products, different resolution, and see this kind of time evolution too.
Maybe I should show this slide, which didn't make it into I can show you the slide. So it shows dependence on depth and size of melt ponds and how the depth evolution changes and like how like they get wider and then they get deeper and so forth. So exactly that is sort of in the melt pond evolution paper. But you want to take a statistical approach, right? Only if you are in the field, you can look at individual ponds and not for very long. So Melinda Webster has a talk this afternoon, maybe she'll speak about that, I don't know. But she goes to the field and stands around the melt puddles, which is not what we do.
I think I've been in the field perhaps with Melinda's.
What's your name? I should say, everyone should say their name.
Sorry, I'm Radiance from the University of Colorado, and I was on Mosaic, and I've been working with Melinda.
Well, so then you'll see the melt ponds more than I do. I only think about it.
That's why I'm curious to compare what meltdown data we have with the results of the algorithm. Because we have very like high resolution, very small footprint.
I think what Mosaic did not really get under attack. So anyways, we should talk in the break. I propose to coordinate, especially with the University of Alaska, to actually fly exactly over that, but it was out of range. Because yes, I agree, we should have airborne, satellite, and people in the field all in the same track. That is not kind of totally easy to accomplish. And then some sea ice scientists think it's too dangerous to go where the track is. They rather go where they want to go, and so forth. But yeah, I'm all for it. I mean, if it's a glacier project, I design where we go and where we put the tracks and where the tracks are best based on my NSF project and where they are best on ISA 2, and I can coordinate all this. But sure, I mean, happy to talk. There was one more person. What's your name? You've asked 3 questions, not second.
Sorry, I'm David Ncar now, and yeah, I was wondering. So you listed the depth resolution was 20 centimeters, but what is actually the minimum depth of a pond you can resolve? And then on a related question, how do you think the algorithm will perform as you get outside of the thickest iced area where you have the deepest ponds?
Oh, it'll be doing great there because you have more data and so forth. But if you have bigger ponds, it's easier. So the smallest resolution is in the paper, it's close to like 20 or 40 centimeter. You have to look it up.
Okay, and that's also the minimum. So you could resolve a 20 centimeter thick pond.
Well, if you have 20 centimeter classes, you have to have one class where you have the top, and then you have to have a class for the bottom, right? So if you actually bin it, it has to do with step size. Now the actual algorithm paper has way more parameters than I just sort of summarized. So I'm happy to point you to the paper, and there's a table with all the specs on how many points we need to do what on. So maybe you should look at the paper in IEEE, which has like a full table of all the constraints and parameters and stuff. Also to the benefit of people who don't want to know all the constraints and parameters.
Awesome. Thank you so much, Ute. Of course, everyone knows where to find Ute, so please ask her more questions and talk to her about this awesome work. And thank you to all of our presenters from this morning. And it is now lunchtime and we are late. So You know, I'm sure that's on everyone's mind. So I guess if you come back late, I guess that's okay. Maybe if you're 5 minutes late or something, maybe we'll start 5 minutes after. How's that? Is that okay, Marika?
That sounds good. I think we have 10 minutes for welcome and we probably don't need 10 minutes for welcome. So,
Okay, great. Yes.
so 5 minutes past the hour sounds good.
Okay, awesome. Thank
Okay.
you all.
Thanks, Hansi.
Thanks, Hansi. Are you coming in summer or do you not know?
So for anyone that doesn't know, there's a cafeteria. Probably everybody knows where the cafeteria is. Correct? If not, we're all going there, so just follow me. Yeah. Yeah, I mean, there's, so we have been earlier in Ron Mosaic, so David was. Lisa was in the bright sweater and Raven, they were all. They all been doing work for Mosaic. Yeah, well, and they were online too. Yeah, so I mean, at least. Yeah, and I think that might be everyone in the. Yeah. Yeah, and Melinda's first been doing. But like Radiance is doing. Yeah, no, I know.
She is. Here I am.
Yeah, that's what I'm saying. I know, so much fun, right?
I don't think so. So
Yeah. Yeah, so there's. Are you guys taking off? I mean, there was the workshop last week. It was at CU. Yeah.
Done.
I think I've been.
Just gonna mute the camera.
German. Is that?
Oh no.
That's a lot of numbers.
Oh, yeah, it's the ATOX, the treaty.
I think has the data searching after comparing, I think, 10 different detection products.
What?
But yeah, it was a bit too late
Oh,
for me.
because
like,
they're
I wanted to
land
finish
eyes?
the comparison, but
Yeah.
I think if we were here, I would suggest.
What's that? Oh, we're just thinking, because I was gonna sit closer or gonna move closer to the microphone for my presentation.
Yeah, absolutely.
But we were trying to figure out
Like, I
if
did
tree was coming back.
Oh, yeah, I don't know if tree is coming back.
You can probably just tell her your reasoning for why you moved her there.
You could probably, she's pretty reasonable.
She seemed like a pretty reasonable human, so whenever I interacted with her.
Yeah, it's just interesting because I think the,
Interesting.
yeah, I imagine most of what you're comparing to, like,
Yeah, I don't know.
they're different animals fundamentally.
Actually, I also want to draw
Passive, active, modus.
collect those and.
Altimeter. Correct.
Okay.
Yeah, those are the different satellites. So, yeah, no, but completely. I said she would be still a really interesting addition.
Yeah.
Yeah.
Different way to.
Yeah. They should, like I saw it with the altimeter, with the Kaiser data too, that it's like, if you compare these long-term measurements with those large spatial averages, with a property that is just very distinct in space, you should be saying wrong or something.
Yeah.
But hard to compare.
Good.
Oh. That's right. So Melinda, are you there?
Join.
Melinda Webster. Oh, it says Melinda
Okay.
Webster has left the meeting at the bottom.
Because she's presenting for
I was
Ed
thinking
as our first talk. So.
She's the first talk.
I didn't think that. Yeah, Patricia, I think Jonah wants to swap with
Wait,
you.
no, but aren't you presenting today as well? No.
Hi,
No.
David, can you hear me?
I sat in the
Oh,
chair.
yeah,
Empty.
Ed,
Do you
you're
want it?
welcome.
Pretty sure you were not present.
We're just gonna switch around.
I'm not trying to, I just was trying to.
I thought Melinda was presenting for you.
That was the original plan, because I was gonna be gone without internet access, but I'm not gone. So I'm presenting my talk.
Very nice.
Hi, Ed.
Hi everyone.
So I think we're exactly 5 minutes past the hour, and that's when I said we'd get started. So yeah, now we're kind of entering just the Polar Climate Working Group part of the meeting. So our joint session with the Land Ice Working Group is done. So if you need to talk to a land ice scientist, you have to go find them in their offices, but they're around. So I guess just before we get started, so I just wanted to note that for people that are here in person, anybody that didn't hear this previously, we are going to go down to Southern Sun when the meeting ends for a little happy hour. So please join us. And, you know, if you have family members that would like to join us as well, that's great. So, yeah. And Ed, we're sorry you can't join us because that would have been nice. But maybe in June, some people can come for the. So, yeah. So our first talk is from Ed Blanchard-Wrigglesworth. And I think Ed's going to be talking about a variety of things he's told me. So I'll let you take it away. And I think hopefully you can share your screen.
Okay, see if this works. Can you see this?
Yes. Looks
Is
great.
that a yes?
Yes.
Okay, cool. Sorry, the audio's like a little cut off, but I hope you can also hear me. So as Marika said, on the on the agenda, I was slated to talk about a record Arctic cyclone in January, and I've been also working on some other events that I want to share. And basically, it's kind of under the umbrella of looking back at 2022, which was a pretty interesting year in the polar regions for extremes. And I've highlighted on the left kind of three of these extremes, of the three main ones. And so we had a record Arctic cyclone in January, then record low Antarctic sea ice in February, and then right after that, a record heat wave in East Antarctica. And I've been doing some work on all of these three aspects, and today I'll be talking about the Arctic cyclone and the Antarctic heat wave. And I want to acknowledge my co-authors that are all listed there. And also, I also always want to thank Polar Climate Working Group, especially Marika Hansi and Dave Bailey for all your leadership and support and help. And some of the computing we've done, it has been with Polar Climate Working Group resources. So I'm being a little bit ambitious talking about two things here, but hopefully it works out. And so I'll get right into it. So this is the starting with the Arctic cyclone. This is the synoptic situation just over a year ago at the end of January. I remember I was in my office looking at weather maps of the Arctic, as one does, and I saw this huge storm on the 24th of January. And if you look at the labels, and sort of the last one I think is 936 millibars, and we eventually found out this was 932 millibars, which, if you have much experience looking at synoptic maps of the Arctic, that kind of catches your attention right away. And we found that this was a new record, especially north of 80 degrees. The previous record was 938 millibars, and this is looking at era 5, right? So since 79 onwards. It was also a record if you look from north of 70 north. So it's a remarkable event. It is, as you might expect, with a very deep cyclone. It was very windy, as you might be able to tell from the very tightly closed sea level pressure contours there. And it made really big waves in the ocean. So here I'm showing, I should also mention, but I think you could probably tell, that this was over just east of Svalbard, over the kind of European side of the Arctic. Okay, so here I'm showing in shading, that is the significant wave height. The blue arrows is the direction of the ocean waves. Magenta is the sea ice edge. So, I'm just showing waves over open ocean. And we basically found that accompanying the very strong winds, there was a huge ocean swell, big waves. Most of these waves, if you look at the Barents and the Kara seas, you see those blue arrows sort of pointing into the sea ice pack, right? The kind of they're sort of going towards the east, northeast, north. So the big waves going into the sea ice pack. And we also found that right near the center there was sustained 100-kilometer-an-hour winds, again estimated by era 5. So we looked at ISAT-2 to see if we could find waves in the ice pack. And this is where that Chris Horvath's led, that we can use the altimeter to look at the surface height, and we can detect waves. And indeed, we found a transect from the satellite the day before, but this huge swell, because the storm lasted a few days, and so we had big waves for a few days. And the previous day, we found this transect here, just kind of just to the east of Svalbard, so right around where the center of the cyclone kind of went over. And this figure on the bottom right here, that shows the surface height along that red transect, kind of, and as you go from left to right in this figure, you're going from south to north along this transect, right? And basically we could see 2-meter high waves in sea ice here, and you can see the attenuation of the waves as you go into the ice pack, but this probably had a pretty big impact, these waves. Okay, so what happened to the sea ice? Well, it got decimated. This are maps of sea ice concentration before and after the storm. So January 21st before the storm, and then January 27th after the storm in the two left panels. If you take the difference between the two, on the top right, you can see a lot of blue and a lot of sea ice loss. And even with your naked eye, comparing the two panels on the left, you can see kind of these two main areas of sea ice loss, one along the main sea ice edge, just like north of Nova Zemlya. But then there was this whole area of open water, or that ocean that opened between Svalbard and Franz Josef, this kind of northern open tongue, right? And that's pretty unusual for like end of January. And the other thing too is that even in the lap turf, we see some opening by the 27th by the 27th of January. That's probably just the strong winds pushing the sea ice away from that coastline. Okay, so now I'm going to talk about how we forecast this event. Oh, sorry, before I go on to that, this was also the biggest weekly loss of sea ice area in this region, right? So I've calculated sea ice area in the dashed black box, which is most of the Barents, Karen, West Laptev. And this is where, if you look pan-Arctic, this is the main region that drives sea ice variability. We had almost 500,000 square kilometers of sea ice loss between these two dates, if you integrate that map. And if you compare with all the other 6-day changes in the satellite era, you get this histogram, and we basically smashed the previous record, right, for weekly sea ice loss. This histogram is centered it's just slightly positive, the sort of the center of the distribution, and that's because climatologically we're still, the sea ice edge is still advancing at the end of January, but we can have periods of sea ice loss, but this was truly remarkable. So we have a situation that a record cyclone produced a record loss in sea ice at these sort of synoptic timescales. Now I'm going to discuss a little bit how well we did in forecasting this, and we use the ECMWF high resolution forecast for a number of reasons. One, it's the highest skill atmospheric weather model in the forecast in the world, and it also has a sea ice model coupled to it, so it also produces forecast of sea ice, not just of atmospheric variables. What I show you here are forecasts of sea level pressure in contours and surface wind speeds in shading. And these are forecasts of the 24th of January at 12 UTC, so right at the peak of the cyclone. And the target, to remind you, is here on the right? And what I'm showing on the left, these 9 panels are the 8-day to 0-day lead forecast, right? So 8-day is at the top left, and you kind of going in time 7, 6, 5, 4, 3, 2 days up to your your lead times decreasing. And I basically, if visually you kind of take sort of bird eye picture, and you see that your bottom 6 panels look a lot like the right panel, that is when you quantify the skill scores. That is exactly what you get. And basically, this was a very good forecast, up to 5-day lead times. But even the longer lead times, like 8, 7, 6-day lead times at that top row, it was still getting a really deep low somewhere in the vicinity, right? You can see that the exact location of the center kind of deviates from one day's forecast to the next at these longer term forecasts, but they're still really deep low. So I would argue that this is a very good atmospheric forecast of the Arctic cyclone. So now let's see how the sea ice does. And these are the forecast of sea ice concentration initialized on 21st of January. Top left, this is the 6-day forecast of the 27th of January in the middle panel, and then the forecast difference between the two. And these are the same times as those observed fields I showed earlier. And I'll just put that panel there again so that you can compare directly. And basically, yes, the forecast had some loss of sea ice. You can see a few areas in blue here, like especially around Nova Zemlya. But overall, the forecast really underdid the observed loss in sea ice, and especially this northern area of sea ice loss between northern Svalbard and Franz Josef. It never simulates like if you look at the 27th of January, it still has a sea ice concentration, pretty high sea ice concentration in that region. And then when you look at the sea ice area forecast, so integrating the sea ice concentration again in the box, in black are the observations, and the sort of blue teal time series are the forecasts initialized. from January 14th up to the 24th. And you can see that, yes, they sort of get a little bit of the event, but it's about half, right? They forecast about half, like a third to half of the total sea ice area loss. Okay, so a summary of this first part is that this record low cyclone took place in January of last year. It resulted in a weekly loss of sea ice, and it also had some super strong wind speeds. And I haven't shown this, but it actually wasn't that warm. So we believe that there's some more analysis in the paper, but we believe most of that loss in sea ice was due to the dynamics, at least not a direct thermodynamic impact from the atmosphere. And the storm was well predicted, but the large loss in sea ice was not. So, then you might start thinking, well, why did if the forecast model has the right atmosphere, why is it not getting the right sea ice response? And we think this is probably both due to biases in the sea ice initial conditions, like maybe too thick sea ice, especially in that northern region, or missing physics, because there's no wave sea ice interaction, right? And I mentioned that we had these huge waves. So these waves are going into the sea ice pack, they're breaking up the ice, smaller flows, but they're also mixing the upper ocean, right? So if you get melting from below in observations, which might be quite significant, the model's not going to simulate that. And you can, we published this a few months ago in JGR Atmospheres. And please email me if you have more questions. On to the second part. This is, I know Christine mentioned this earlier this morning in the atmospheric rivers talk. So there was an amazing event last March, and this got a bit of media attention. And what I show on the bottom left here is a time series of hourly air temperatures from Dome C, or what's also known as Concordia. Concordia Dome C is a station, a French-Italian station over East Antarctica, in a kind of right in the middle of the East Antarctic Dome. It's about 10,000 feet up, so it's at the top of the ridge, right? So right at the top of the ice cap. You can there's many ways you can analyze this event, but your eye will see two things. One, the anomaly is massive from climatology, and the other thing is that this event was almost the warmest event of any time of the year. This happened in March 18th. That's the autumn equinox. The sun's almost gone down. The climatology is 30 degrees colder than in summer, but it's still pretty much as warm as the record summer days here. This is slightly kind of on the top left, I show you the daily mean temperatures from Dome C, again highlighting that. Top right is the hourly temperature. In blue is 2022, and in gray is the all previous years from the station here. This is 96 onwards, and it beat the previous record for March by like 18 degrees, right? So any way you want to look at this event, it was absolutely remarkable. Again, if you bottom left is the daily anomalies, so that's almost getting to 40 degrees for this event, which beat the biggest previous anomaly in the middle of winter by almost 10 degrees. And the middle of winter has a lot more variability than this time of the year. We looked at the radio SARs, bottom right. So basically in gray and black, that's a climatology, and in gray, all single radio SAR from March from Dome C. And then the colors are the event. So in blue, previous to the heat wave, and then as you get the warmer colors, that's a heat wave with the red, the 18th of March, highlighted here, the full sounding in pressure on the y-axis. And you can see it wasn't just the surface temperature, it was the full troposphere was pretty much record warm, but quite interestingly too, the tropopause climbed really high up, and the stratosphere was record cold. So the whole atmospheric column was like in this extremely anomalous state. So if we look at the atmospheric circulation, here what I'm showing are the 500 geopotential heights in the contours and the surface temperature anomalies in the shading. And these are daily maps from 14th of March, top left, to 19th of March, bottom right. So prior to the event, surface temperatures were actually a little bit below climatology. And on the 15th or even the 14th, you can see that the Z500, there's this bridge that starts to build along East Antarctica, kind of around 120 degrees east, just to the south of Australia, there on the bottom right of the panels. And then by the 16th of March on the top right, you really start to see this kind of omega ridge that sort of peaks on the 17th of March and the 18th. The other thing I wanted to mention is that the temperature anomalies, you can see just kind of build up sort of in situ, right? Like over East Antarctica, these kind of, this sort of bright red area. It wasn't a temperature anomaly that got, say, advected from somewhere else. It mostly built up in situ as a result of the atmospheric circulation. And if you look at the backtracks, these are 4-day backtracks using the NOAA high split model. And on the panel on the left, this is backtracking from March 17th. And the panel on the right is from March 18th. And this is, if you like, picking Dong C as the origin of the backtrack. And 3 different heights, like 2,000, 3,000, 4,000 meters above ground level. So a pretty good chunk of the troposphere or the middle troposphere. And basically, what happens is that we brought air from Southeast Australia in 4 days, right into the middle of Antarctica. So yeah, it's going to get warm if you do that. So it's a pretty just kind of a remarkable event. How well do climate models do in simulating an event like this? So on the left, I show again the figure from the daily mean temperatures at Dong C, and in red highlighting 2022 in the event. And on the right is a figure using CSM lens. This is the same year, like 79 to 2022. So the historic plus the RCP, stitching both runs together from CSM lens, looking at 35 ensemble members, and basically get 1,500 years. And if maybe with the naked eye, see, I don't really see an equivalent event, right, of like getting this heat wave kind of around March that is as hot as the hottest days in summer. You do see some extreme events, right, but maybe not, arguably not as strong as what we've seen. So this might lead you to asking, well, why is that? Are there biases in large scale circulation, cloud physics, phase, boundary layer physics, radiation, right? There's many reasons why this might be the case. I guess you could also argue that maybe it's a 1 in 10,000 year event and 1,500 years isn't enough. But one way we've approached this question is nudging the model, where it's also called a storyline approach, where we've taken the model and we've nudged it to the observed winds. And I know Daniel Topal had simulations where you use the model and you nudge the observed winds. And so that's what we've done. And this is what we get on the right figure. So the red time series on the right is when we take CSM lens in 2022 and we nudge it to the observed winds. And we do a pretty good job at simulating the observed event. Maybe not quite as strong as the observed anomaly, but it's, I'd say it's 80 to 90% of the way there. So I think this is a good, I would argue that this shows that specific circulation pattern, CSM lens, the free running ensemble, has struggles to simulate something that extreme. Okay, and then the final slide, we've also thought about, okay, how can we think about climate change and the impact on the heat wave? So what we've done is we've done the same set of experiments, but we've applied the nudging under different forcing, right? So we go in CSM lens, we use a 1925 initial condition and forcing from 1922, I think it is, so exactly 100 years ago, and we just give it the winds of 2022. And that is the time series in black on the left. And then the blue time series is the one on the 2020s forcing. And the red time series is doing the same in the 2090s, right? You see the 3 distributions, very similar, but they're offset. And they're offset by amounts of warming, as you'd expect. And the difference between them is shown on the right. And you can see that in the blue is the difference between the 2020s and 1920s, and it's about 2 degrees Kelvin. In dashed, that is the local climate change at that grid point for March, right? So you might ask, okay, is it just global warming, like the global difference in warming, or is it more local? And this would be, well, your better guess would be local. But what's interesting is that if you look at the red time series, which is your 2090s minus 1920s, it's you get a little extra, especially at the second half of the heat wave, the cooling. So that grid point has 6 degrees of climate change, of warming, but this event warms by a bit more, right? So there seems to be a non-linearity. I know that was a lot, so I'm going to leave the conclusions here, and hopefully there's time for a couple of minutes. And we are hopefully going to submit this for publication pretty soon. Thank you.
Thanks. So questions for Ed? So Lorenzo?
Okay.
Okay, Dave?
So, Ed, is this also a resolution thing? I mean, I'm thinking of the Antarctic dome sea thing, like, you know, just capturing these sort of extreme events at 1 degree in the atmosphere. Yeah.
Yeah, that's a great question and something I've thought about. But I think because of the geography of East Antarctica, of the ice cap, where it's such a like smooth topography, such a little gradient in steepness, and the fact that your grid, as you know, like the grid cells in the atmospheric grid, you know, as you get closer to the poles, you have slightly better resolution, right? And the size of the heat wave, the footprint, I think resolution plays a pretty minor role, right? We're not talking about, say, an extreme event at the bottom of a valley in the Rockies, you know, where you have a bit of cold air pooling, right? And the fact that when you nudge the winds, which are mostly large scale winds, the model does so well. I think that shows that resolution, I think, plays a pretty minor role.
Lorenzo?
Yes, I have. Do you have a sense, you showed this for the Antarctic case, do you have a sense what CSM can do for the Arctic cyclones? So how distant we are?
Yeah, and I have some figures, but I don't think I have time to show them. But yeah, we're looking at that too. Because in these simulations, we actually nudge the winds poleward of 45 in both hemispheres. So I get a twofer. And so I'm like, yeah, we actually simulate that cyclone really well. We get it down to 939 millibars in CSM, which is a little more than observations, but ERA 5 is 25, like quarter of a degree, and you know CSM is a bit bigger. So I bet if you smooth out ERA 5 to CSM, it might, you know, the very center might be a little higher, but it does a really good job. So we're looking at how the sea ice responds when you apply or when you have like a cyclone like in the real world.
I think David?
Yeah, really, really interesting talk. I guess I'm wondering about what does sea ice loss mean in your first example? Like if the ice gets really busted up and you have sort of like flooded, for example, do you count that as a loss or?
So, yeah, no, it's a great question. And so we looked at, so what I've shown here is mostly sea ice concentration or sea ice area, which is just the integral of the sea ice concentration. And this is as estimated with a passive microwave, you know, the famous, I can't remember which bootstrap we used or the bootstrap on NASA team, but you know, the passive microwave data set, and they consistently show, you know, these losses. We also looked at thickness using the SMOS satellite, which is good at looking at thin ice. So it's not good for most of the central ice pack, but if you're looking at the sea ice edge, and that satellite or those estimates also show a really big thinning in the ice pack.
Yeah, I guess I just wonder, like, are all you seeing is the fact that seawater is getting up on top of the ice?
I doubt it. I doubt it because we also looked at Chris Horvath sent me these images of satellite, not MODIS, because I don't think that's visible at that time of the year up there. Maybe a SAR satellite imagery, and you could totally see that region, that northern region, that open between Svalbard and Franz Josef, was really open ocean. Like it truly, it wasn't just flooded sea ice. So yeah, there is, you know, there is a question of observational uncertainty in these like very extreme conditions. But I think the big picture, to first order, these were real changes and like losses in sea ice.
Thanks.
Okay, we're going to take one more quick question. Louisa, did you have one?
My question went in the same direction, and you answered it by telling the different sources you looked at.
Okay. And then we don't eat into your topic. So
I can put mine in the chat.
What's that?
I can put mine in the chat.
Oh, okay.
That will help.
Yeah, I mean, okay, if you can ask it, I'm okay with us if we
Okay.
shift a little late, yeah.
No, I just was curious if you had looked at moisture transport at all. I mean, some of the, I've looked at into this a little bit, and some of the things that we found were that some of the moisture sources were actually tropical, like from a remnants of a tropical cyclone. So I'm just curious, like I'm really interested in that backward trajectory model that you did, and if you've looked at moisture transport and taken it further back.
Yeah, that's a very good question. I haven't like I think I did look at the 5-day backtracks, but the extra day didn't really give me much more information. What we have done is that we've calculated the heat fluxes, the atmospheric heat fluxes into East Antarctica, like the meridional fluxes across like 65 degrees south, right? So just at the coastline. And I'm doing this with a graduate student here at the UW, and those were record high, record meridional heat fluxes, but they were also record high in the dry. So he looked at both the dry static and the moist static energy, and yeah, both elements of the heat flux were like record high. So I think the moisture contributed. But I don't think it was like only because of the moisture, right? And interestingly, I've looked at the relative humidity profiles at Dome C, and you do see a moistening of the atmospheric column, but it doesn't saturate at any point. Like you get moistures of like 80 or 90%. So I don't know how much cloud cover actually got to Dome C, although I did look at NASA Worldview, and you do see some like high clouds. So I'm sure for the coastline and near the coastline, the atmospheric river, a lot of precipitation, but on top of the plateau, I don't know that it's such a clear signal of the moisture like being like a big contribution.
Great, thanks, Ed. Really, really interesting stuff. I'm glad you stuffed both topics in. So,
Well, thanks for letting me go off script a little.
Yeah. So next up we have Louisa van Albedel. So, and hopefully I didn't butcher your last name.
That's great.
Yeah. And it looks like you're able to share your screen. So.
Great. Yes. Okay. Awesome. Yeah. Thanks. For all of who don't know me, I'm Luisa van Albedel. I'm working at the Alfred Wegener Institute, and I'm kind of a remainer of the Mosaic conference that took place last week. And I'm very happy that I can, interact a bit with you and engage with you, because I'm actually more from the observational side, but I'm very happy to be here. And I'm going to take you on this ship now that is, displayed here. It's Polarstern, and it is. It is an image that was taken during Mosaic, this large observational campaign that took place 2019 and 20. And the project that I'm going to present you has actually, I have really a personal connection to it, because when we went on Polarstern, we had to get through the ice back north, and we got stuck at a certain point in very high ice pressure, and there was no way to go further north. Actually, we were drifting south again while we were ramming the whole time with the ship. And at that time, we were looking for leads. These are those structures that you can see here nicely on the image. So somehow a way to get a bit faster through the ice. And at that time, I was trying to help the bridge to find those leads with different satellite images, but also actually model output. And I realized that all the products that we had at hand were not really helping us. They had either the wrong spatial resolution or the wrong temporal resolution, or they were just really hard to interpret. And that's why when I was back home, I wanted to give it another try and to come up with a satellite product for lead fractions that could also help in such situations, but also answer many science questions that are related to leads. Just to give you one more quick overview of Mosaic, this is a schematic view of sea ice, how we try to see it during Mosaic. So there are really a lot of different processes. You all are very aware of them, and we really try to measure more or less everything, but only at one particular spot. And so if anyone is interested of you in any kind of particular measurements, I think I have at least quite good overview of the sea ice part, and I'm also happy to facilitate, any contact if you need that to figure out, because the mosaic road might sometimes be a bit frightening for outsiders at the beginning. But let's look a bit at the leads in more detail. So they are really hotspots for exchange, I would say, because in the winter ice pack, the leads are the only place where there is any exchange between ocean and atmosphere. And that's why a lot is happening around them. And this is also the reason why we thought that it would be very important to look at bit in detail at lead fractions. And since leads are normally very narrow but extend over hundreds of kilometers length, satellites are actually the best approach to detect them and analyze them on larger scales. And the approach that I was now using to work on those lead fractions is not to detect their presence, but to detect their formation. So one way is that when we have sequential images of SAR satellites, so SAR is synthetic aperture radar, and this is active microwave of the frequency, so you can imagine that you get somehow an image that is just reflecting the microwave properties of the sea ice. And if you have sequential images of those, you can see also the change, and you might be able to detect a change in the velocity. And whenever there is divergent ice motion, so when the ice flows move apart from each other, there will be a lead forming. And this property of the leads was the one that I was hunting for. And how this could be done is shown here as for an example from November 1st. So this is a SAR image, and you see all those different backscatter changes that are just reflecting the sea ice properties. And this is about 50 kilometers in scale, this radius, the circle here. And on the other day, on the 2nd of November, there were 2 leads opening, and I've highlighted them here in red so you see them a bit better. There was one lead was about 250 meters wide, and then a second one, a larger one, 350 meter wide. And my aim was now to detect the location and also the widths of those leads with those satellite images. The first step is to calculate a velocity field. So we just take those images, run them with a pattern matching algorithm that detects how particular features of the sea ice were that are visible on both images. And with this, we end up with such a velocity field. And the color code is here the zonal velocity. And just by looking at the bluish and greenish colors, you can see already that there was a change in the velocity gradient. And this gradient, if you take now the spatial derivatives of this velocity field and you add them up, you can calculate divergence. And this last plot shows you now the divergence field. I have already removed the very small pixels, so you can only see already the filtered values. And the filtered red dots align actually quite well with the location of this second lead. I just zoom in again for you so you can see it a bit better. So with the divergence fields, we can actually detect quite well the location of this larger lead. And for the smaller lead, there are at least a few pixels. Not all of them, but at least a few. So this was actually quite great because we had this very close matchup between what we saw on the SAR image and then what we could calculate. And I also estimated that the widths of the leads from the divergence fields matched quite well what we could measure manually in the SAR images. Of course, there are still some issues. It's not yet done, but for example, we have still noise, or at least pixels that we think that are noise. So those are random pixels here in the SAR image with high divergence values that are not associated with somehow an opening in the ice. And then the second thing is this product in this raw state only resolves the new openings. So if the lead were opened the day before, we wouldn't be able to resolve it because we only see differences with the divergence. And I tried to tackle those two issues. First, let's have a look at the noise. to reduce noise, you can always filter by adding additional knowledge that you have about the leads. And this is exactly what an algorithm developed by Niels Hutter is doing. So this algorithm considers only those pixels as a lead that are having a really strong gradient in the deformation. That is one particular feature of the lead. And then second, also the elongated shape. And that's how it actually removes all the dots that were previously in those yellow circles. So they're all gone. Unfortunately, what is also gone are the pixels along the smaller lead. So this product with this filtered, with the LKF derived lead fractions, this one is kind of a clean lead fraction product without the noise, but it obviously also misses some of the less distinct leads. I also wanted to show you how to tackle the second issue that is related to the fact that it only resolves the new lead fractions. And this is here an example from the 27th of March. It was a highly dynamic phase, and you can see just following those black lines that there were a lot of different leads. Of course, I tried again whether the divergence is able to capture those leads. And first of all, I calculated divergence for the 26th to the 27th of March. And those are now the violet colors here. And you can see that it explains some of the leads, but not all of them. And the assumption was that probably those other leads were formed the previous days. That's why I had a look at the divergence between the 25th and the 26th of March, and drift corrected this divergence fields to the 27th. And indeed, considering those older leads now, also can already explain a few more of those leads. And then, of course, not all leads are yet explained, so I went one step further back, and now you can, for example, see that also the blue, the lead system that is encircled here in blue shows also up. So those leads are already 2 days old, or 2.5 days old. And just by going forth and back, you can also see that some of the colors are on top of each other. So this means that those leads were activated again the day after. And then just to show you a last example, so I also then had looked at a time step even further back, and now I would say we can almost explain all the leads that are there. So those leads had now a lifetime of about 4 days, and they were partly activated again. And this now gives us actually a quite complete story of the leads, and for example, also how much new ice could form in between them, and whether they were activated or closed again or opened again. Yes, so you might now wonder what we could do with such a product now with a time series of lead fractions. So just try to come up with some ideas. So my original interest was to actually look a bit into the ice mass balance of sea ice and to quantify the contribution of new ice that is actually forming in those leads. And there are other studies that suggest that this is actually about 30%, what is quite substantial. And that's why I think that it would be really worth to come up with also more Arctic-wide estimates of the evaluation of the CS mass balance, and then eventually, hopefully, also compare that to maybe some of the CS mass balance in models, and to see whether that is similar or not. And then also a good those lead fractions, and also, of course, the ridges, what are kind of the counterparts of that, might be useful to evaluate a bit the ice mechanics. So we have then a temporal and a spatial distribution of those kinematic kinetic features, leads and ridges, and also, for example, their intersection angles. And they have been, there is currently also a study out in the Cryosphere discussions which shows that we can derive quite important properties of the ice mechanics from those intersection angles of leads and ridges based on this product. Yeah, and then of course a broader just a broader scale, those lead fractions can help us to estimate the heat exchange between ocean and atmosphere on different temporal and spatial scales. And what is also quite interesting then for more the other parts of the climate and ecosystem is that they serve as sources for aerosols that can then exchange again, then interact again with the cloud formation processes. Okay, let's quickly sum that up. So the lead fractions from divergence indicate actually quite reliable the location and the widths of also really small leads. And when we combine them and put them into a sequence, we can track their temporal evolution and produce kind of a time series of reoccurring leads. And then, as I showed, currently I'm working with 2 different products that are depending on the level of the noise removal. And I hope that that there are several applications for deeper process understanding around the leads now for observations and models. Thank you. So, questions?
Do you have a sense how quickly these leads refreeze after they open up? And if would you still call them leads when they are refrozen?
Yes. Yeah, it's a big discussion. What is a lead? And what for my product, I'm showing really the dynamical aspect. So whenever there is opening, and then you, like what I've also done, you can apply a thermodynamic model to see how the conditions were and how quickly that refroze. So I'm not going to keep a record of thicker leads if you want. So, I mean, you could do by using like the different time steps and running like them in parallel with the thermodynamic model, and then you could see that maybe the leads, the green leads here, refroze to a thickness of 10 centimeters during the first day, but then they were maybe actually closing, and then all those new ice was crashed together to form a ridge, and then the other day, maybe on the 25th, they reopened again, and then you would have again open water. So I think like with this rather high resolution product, you can come up actually with a quite good history of this new ice production in the leads.
You have the height measurements of the leads on the ISA2 product at 10. Okay, and it'll give you, it actually puts out leads. It's a product just for leads. That gives you the height measurement of the top of the sea ice and then the ocean surface or whatever actual altimetry you get in the gap. And so forth. And of course you could, I mean, you can probably improve your product by going off of just the spectral value. Because the leads are often darker unless they refreeze. So maybe if you, I mean, divergence is sort of neater.
Yes, so this is like, yeah, exactly. I also compared my results to any classification. So was that the direction you were going with the backscatter value that I had?
If you want to call it a classification, but sure, you can just use the spectral value.
Yes, but I intentionally not looked at the backscatter values, because then we start this discussion whether is this still a lead, is it a free frozen lead, are there any frost flowers on the lead, because are there any waves on the lead, because this all changed the backscatter value of a lead. And by just using this dynamic information, I can at least be sure that there was at a certain point during the formation process open water. David?
Yeah, always cool to see this work. So you're showing divergence. What about convergence and shear?
So of course, like convergence is gonna close up my lead, and also that form maybe a ridge or something similar. So convergence is of course available as well, and for coming up with something like a time series of the lead, I'm gonna also include that to see whether they were closing or not. I've started to work with the divergence and the leads because they're just easier to recognize on psi images, while ridges are always a bit more tricky to at least visually identify. But it would be very cool to combine it with, for example, ISA2 measurements of ridges. if we have any overlaps to see whether we can come up with a similar approach for the ridges. Shear, yeah, of course, also a big topic. For you will always have also a little bit of opening along shear zones, and but since this is done often a much smaller resolution, I have here concentrated now for now on the divergence, because I can also see that in the SAR images. And yeah, but yeah, there are also openings along shear, and you could kind of come up with a proxy to probably kind of calculate also the amount of openings that is related to shear.
I mean, you see the shear components where the leads sort of offset, but I think as long as I mean, it's just a matrix size. As long as you have the divergent component be large enough, that stands out. Like this little one and the blue one, it's definitely having a large shear component and so forth.
Here.
But then she also has to have an image at the right time when it opens. So the time series factor for this space plays a role.
So I want to make sure people online can ask questions too. So if there's any questions from people online. Okay, I think there's a lot more questions, but maybe we can chat with Louisa at the break here, since most of those questions are in the room. Is that okay? Thanks, Dave. All right, so let's move on to the next talk. So Radiance Calmer, and hopefully Radiance, you can just share your screen. Perfect. Looks like you can share your screen. So, yeah.
Thank you. So these results are also from the Mosaic expedition, but this time during summertime. And this presentation is going to put together different data set about albedo and also introduce some results from melt ponds. So measurements presented here are from the ISFS flux station and radiation station at MedCity. So basically hemispherical sensor at 2 meters above the surface. And then you have the albedo line. So someone walking with pyranometers along the 200-meter line. The helix, which is a drone that could be flown low above the surface or flying along a grid pattern or even doing profiles. And then the beluga balloon, so profile up to 1 kilometer, and the helicopter flights covering basically the entire scene of the mosaic flow. So to put in perspective those different data sets from a scale question, multiple flow, we are going to have satellite images, and then on the scale of the mosaic flow, sorry, it didn't work. Why it's not, okay.
Is it not advancing?
Yeah, no. Okay.
Okay, good. So, from the scale perspective, at the size of multiple flows, we are going to be able to see from satellite images, and then the scale of the mosaic flow, helicopter flight and satellite image, and then inflow, the drone measurements, balloon measurements, and albedo lines, and then the point measurements, so a very small footprint, the radiation station and the sled. But as we put together these different measurements, we also realize that as we go lower in footprint, we also, great, okay, not working.
Can you, does that work, the arrow at the bottom?
No.
Yeah, did it grant continuous time?
But it's not,
but it's staying on the slide.
Arrows down at the bottom, is that?
That's what I have done.
Going there. Huh. I don't know.
I think it's the way I'm sharing my screen.
Or are you sharing the whole window or just?
The whole window.
Oh.
It should work.
Maybe you can select just sharing.
Does the spacebar work?
Yeah.
This is
This is the only
Technology.
Yeah, I see kind of like two options.
I don't have it anywhere.
Before that it had all the individual slides on the side, so if you would go back and forth, because you were able to advance that way, that's probably fastest. Why not Slick? It works.
Yeah. Yeah.
So now if you click on three, you'll see three, and if you say, if you click on three on the left side, that's what you did before, and it showed us the next one. And now you click on this thing, it showed us the.
There you go. Nice. Now it's working.
Great.
Not going to. Sorry about that. Yeah, so it was a question of the time, because we have a continuous time series when we have point-based measurements. But for the summertime, we have only 3 satellite images and 3 helicopter flights. And then bringing the conversation from the modeling side is how to link these observations with the size of the grid cell. And I feel like most of the time you are using satellite product, but I hope with this presentation introducing other kind of observation that will give you some insights about processes. And somehow we have started this conversation during the Mosaic workshop with Marika, and I've learned a lot already, and I hope to keep going in this direction, learning more from the modeling community, and maybe trying to address some questions with like bridging these observations with the model. So how this data set could help to better represent the internal processes, or how we can use the model to fill the gaps, because you have seen we have only 3 satellite images at large scale because of cloud, because of like multiple questions. So could like model be used to have this continuity? And then of course the big question about albedo feedback. And I also realized during the Mosaic conference that melt pond was a big topic in the discussion when we speak about summertime. And there are a lot of melt pond data set that are different resolutions. So that could also be investigated along the albedo question.
It's done working.
I'm going to use this. So you have the drift of a Polish dam and the period I'm focusing on in the summertime. So you can see that we are very close to the marginal ice zone. So it was a very, a lot of melt ponds. Nice one. I'm gonna stay like that. So first, before introducing the results of these different measurements, I would like to introduce the footprint of each sensor. So here you have the Mosaic flow, you have the Polish dam here, and then this tiny blue dot corresponds to the footprint of the radiation station. And then there was the flux station over the first year ice represented by the second blue dot. When you walk along the albedo line, you are going to cover a larger footprint represented by these lines. But keep in mind that it's a weighted average of albedo over the footprint. So what is directly underneath the sensor is going to have more weight than what is at the periphery of the footprint. So now looking at the helix flight, you have what we call the hovering flight, so at very low altitude above the surface. So it's going to be this small footprint, and then a grid flight is going to cover a larger area of the flow. And when you fly higher in altitude along the profile, then you see that the footprint at 100 meters is already like outside of the Mosaic flow. And introducing now the beluga balloon footprint at 200 meters, you can see that it's like larger than the mosaic flow. But once again, this is a weighted average over the sensor footprint. So it's not going to equally wave the albedo over this large surface, but it's the cosine response. So now that you have in mind the different footprint depending on the measurement type, we can look at the time series. And this is the continuous time series for the radiation station and the ASFS sled. And we can see like clear sky day and then the slow decrease of albedo along the, like from the end of June to end of July, when the mosaic flow actually broke up. So we reached the marginal eye zone and there were no more flow to work on. Now, adding the distribution from the albedo line. So the distributions are represented by the median value and the 25th and 75th percentiles, with lower value at the beginning of the end of July, beginning of June, and then reaching again this high value of albedo above snow and bare ice. And now looking at the helix hovering flight, we can separate the different feature of the surface, saying, okay, now we are going to fly about snow, bright snow. So we have this high albedo close to 0.8. And then now we can like focus on the melt pond, and the albedo is much lower, usually lower than around between 0.4 and 0.2. And then this diamond-shaped markers represent the open ocean, so even lower value of albedo. When we look into the grid flights, so the marker, the size of the marker give you roughly a size of the area covered during the flight. And as we increase the footprint compared to the albedo line or the sled data, we can see that the median albedo value is much lower. And because we are averaging over a larger footprint. And now introducing so all these previous data were from the hemispherical sensor. And now the helicopter data is actually a pixel-based albedo product calibrated with the albedo line. And we can see that the median value is between bright snow and then melt pond, but the black line actually covered the entire range of albedo along the mosaic flow. So up to like open ocean. So the second part of this presentation is to actually now look into the profiles. So when we look at hemispherical sensors, the helix was flown starting above a melt pond and then reaching 50 meters altitude and then going down above the same surface, moving to a different type of surface, in this case, snow, bare ice, and then again, gaining altitude and then going back down. So we can clearly see this kind of profile changing with altitude as we increase the footprint of the sensor. The profile from the beluga balloon is not corrected for the position of the sensor, but we still see that we are within the same range of value. And we were not collocated spatially, but within the same area. And it was this area. So the second year ice, you can see the polar stand here. Med City was around here, the beluga balloon over there. And the idea of using the satellite image is to actually trying to reproduce this profile obtained from the hemispherical sensors. So we selected 6 points, and we calculated with the cosine function the profile of albedo, so increasing the footprint as we go higher and higher up to 50 meters. And we are able to reproduce the shape of the profile. So the idea was, okay, we looked into the same part of the flow. What is happening now if we start above a large melt pond or a brighter surface? And on the left, the profiles that you see are started above different melt pond with different sizes. And you can see that we are reaching this kind of what we call the aggregate scale of albedo at different altitude, depending on the surface type the profile is started above. And to give you an idea, the circles drawn on the right correspond to the aggregate scale of albedo. So a footprint smaller than this circle around, for example, this big pond, Mystery Lake, would be dependent on Mystery Lake. And then if you have a footprint larger than this circle, then you have reached this like value of albedo corresponding to the aggregate scale. So this is just a preliminary study. The idea would be to have like more statistical results looking at each pixel of the image and see what kind of profiles and what kind of like footprint at the aggregate scale of albedo we can obtain. But to bring back again the melt pond in the discussions, this actually compared different type of measurements to get melt pond fraction over the mosaic flow, and they are collocated in time for this from the satellite scene, the mosaic flow, and the transect data. So the transect data was actually a sound walking all along the mosaic flow. And you can see that depending on the area you investigate, melt pond fraction is going to be very different. So again, there is this question of scale when investigating albedo, and we have a similar result when we look into melt pond fraction to really define what we are looking at, what area we study. So I hope I convinced you that it's very important to make sure you understand the scale and the vertical variability of albedo, particularly when comparing surface-based measurements and satellite product. And I'm curious to hear your perspective from when you use the model. What do you think about this question of scale? And what we would like to do with the Mosaic community is to focus on case studies where we have all this product of albedo. And something that was also brought several times in the discussion was working toward a surface energy budget with this information of albedo, how we can like improve this kind of study. So this is how we are going to work, but I'm curious to hear your thoughts on this question of scale. Thank you.
So questions or comments for Radiance?
Never mind.
Lorenzo?
So in the modeling side, I think we have a lot of complications, like we take into account melt ponds on different ice thicknesses and on level ice and ridge ice. So we have a very, maybe too complicated system. Do you see any evidence that melt ponds are preferentially accumulating of thicknesses on ice of different thickness, or is your experience that looking just at the average albedo is enough?
For the ice thickness and the depth of the pond, that would be a question for the Mosaic community. I don't have measurements on that, I think. And maybe Melinda Webster can give you more insight. But that's also, maybe you're ready. Yes, everything is linked. And it's this question of how to make this link, how you relate these different measurements. And but definitively, I'm going to look into that because this seems to be very important.
So Melinda, if you want to unmute yourself and chime in. So unfortunately, we're not hearing you, Melinda. I don't know if you. Well, while we're waiting on that, I think, did you have a question?
Yeah, so I was going to say, we find that it's not so much, I mean, there is a cap to the depth of a melt pond, which it has to be smaller than the thickness of the sea ice. But what matters a lot is actually the deformation type and the morphology more than the absolute thickness, which leads to preferential melting. So certain types of slanted fault blocks tend to have a little pond on their side and so forth. So that then leads to the complication of formation of melt ponds on level ice and formation of melt ponds on ridged ice. And I think that's something that was in the sea ice model early on, right? Sort of when there were
Sorry, I
thickness
was trying to
categories.
figure out Melinda's issues.
I think back when Elizabeth worked on Ridge, she had these thickness categories, but you can also have like slanted blocks, which are rare in the model then. So if you have a fault block, it tends to melt like on its side. It sort of focuses radiative heat a bit on the side, whereas if it's flat. But then there's also materials in normal. I don't know anything about materials, I guess they do. I only know about height. And of course, I mean, I've been on the Polarstern for months, so I have seen sea ice long before I was a sea ice scientist. And so I would go for walks in the forest, which is around the ship many months of sort of sea ice, non-scientific observations.
So Melinda, we can see your comment in the chat. Do you want to try unmuting and you can speak out loud?
We can see you're unmuted,
Huh.
but we can't hear you.
Well, this is going to be a problem because you're presenting next, so.
But I mean, the
So-
comment makes sense, right?
Oh,
If there's
yeah,
thick sea ice,
yeah.
you can have deeper ponds, while if you don't have thick ice, not deep ponds to be had, you get it breaks the ones.
Right, that's the thing. Yeah, but I think Lorenzo's point was about, you know, do the ponds tend to aggregate more on the level ice versus the ridged ice?
Right, that's
And,
more the more.
you know, that's what the
Exactly, right.
parameterization is that we have in the model. So, you know, I mean, there is a more sophisticated topographic scheme, which supposedly has water running downhill, but we haven't tried investigating that.
But so you have a parameterization of morphology now. Okay, cool.
Yeah.
So I think, so we're supposed to break now. So, so why don't we take, did someone else have a question?
Yeah, I had a question.
Oh, go for it.
Is that okay?
Yeah.
I was gonna ask, I think it's really cool that you can see the scale of variability, and I'm wondering if you have observations how that changes seasonally, and if you would connect that to, is that scale of variability larger as melt ponds form, or kind of like how does that evolve and how is that related to the distribution of surface types on the flow?
Yes, that's a very good question. And you can expect the profile changing, for example, before the melt, when you don't have any melt ponds. So it's going to be very like uniform on the like bright snow. And they also have data from the refreezing season, and putting together before melting season and refreezing season that would give this kind of time variability. We are not there yet. We are still learning about each other data set for the season we are working on, but that's a general interest in the community. So at one point it will come together for sure.
You have apparent surface reflectance relates to albedo, and you have to a point, right? And so then you have apparent surface reflectance on ADL09 for ISO2, which is the atmospheric data product. So it provides you directly with observation and ASR. It's not the same, but it's there, right? And it's global. And so, yeah, someone can dive into this, map it out over sea ice, compared to whatever observations you have then. provide a spread in a temporal context, while you're of course missing the really fine scale, right? But anyways, there is context to be had. There's tons of stuff to be done.
So I think with that, why don't we take the conversation to the break? And Dave and I might sit in here and try to help Melinda get set up, since Melinda is supposed to give our next talk. And so since we're a little bit late going to break, why don't we meet at 35 minutes past the hour? So just 5 minutes extra for break. So,
fantastic. I'm gonna go outside, enjoy the beautiful
Beautiful.
outdoors.
It's cold, but it's, so, Melinda, if you look in your audio settings and the Google.
Your profile's going up.
Yeah.
It seems like even when they've asked you to, not
Can you hear me?
Oh,
Okay.
not the virtual ones. but
Okay.
that.
Thanks. Enjoy your break.
Yeah.
It looks like even
it's also
even pretty high up, you
Good
still
morning.
have like a 0.1 difference in albedo. How high do you have to go for that to be like 0.01? Or does it ever get there? No. Okay, why doesn't it get there?
It looks like it's working good. I would say that we are not going high enough.
Okay.
And also, you also have visibility condition that, for example, I have a higher profile, but this is actually the fog blowing in. So,
maybe
and
that was in
I think
Okay.
it's kind of like temporal variability and our limitation at high temperature side is making conditions difficult to reach this same
Okay.
So I don't think we will get to something lower than 0.05 difference when we go in.
Gotcha.
But again, the problem that we have is this is our best profile, and then we have like 6 other profiles that are just like not very useful.
Yeah.
So that's the problem with observation.
Yeah.
We don't have statistics.
Because this is leads right
Yeah.
on like.
Yeah, measuring albedo better than
Was like over on the other side.
5%.
Yeah.
No, we had the same issue even on the ground-based measurements. The leveling of the sensor
Maybe Martinez. I actually.
gets you. That's
Well,
much it.
You can ask, I would ask, maybe they, I don't, maybe they tried, but I mean, I would like, that's gotta be, that has to be it. I mean, that's ridiculous. Because it's just, that's discouraging.
It's discouraging, and it's also distracting.
Exactly. And that's what I know.
Yes.
We could talk.
I need some more water. Was that refund?
Yeah. So hopefully there's stuff in there.
My cheek gets like much warm and I have to dump it out.
Yeah, I just need to add another small bag.
Define what the early characteristics of the activations are. Each of the activations gives different information about what is being represented. Also provides information about what that means.
Right.
So you're going to talk about that sometime. You have to do it.
Yes, I would be very happy to because I already think that for assimilation and that's this is what I'm trying to how to like put the observations we have in the right format for that would be used.
Any kind of observation, quantifications or.
All we're gonna have is one variable in that. So just sort of that idea of
So how would you
sort of that closing at a scale. I mean,
Because, sorry,
that's what there's kind of an.
observation has been has been
Scale.
in terms of key sensor, but it seems different.
It can be different. We can start with that.
That would be something.
But in addition to the sensor
Translate that.
uncertainty that we have, there's also some uncertainty about what it's representing. Is it representing a trend point, like your visions were one person standing on the ice, or is it representing that area that you're showing?
Right.
And that uncertainty is typically added to uncertainty in the context of doing that estimation. Interface with some kind of context. And all that variety of instruments that you have, that can provide representations for each of the instruments.
So for example, if we have an area, value and standard deviation distribution implemented.
Or we would use the standard deviation as we are getting to distribution. That's something I want to try to understand.
In that sense. So as long as you do
In values, the values really the distribution that provide. So that's why the question of like one number at the same slash outcome.
Some of us, the data they can do is one number from grid box. Much.
Yeah. And I should have that.
It's still valuable. It's great to figure out.
And ideally, be really nice.
I can contact
The run. R&D at station. We've been using that data. Of course, column, but it's really nice to update it. You know. Yeah, yeah. Yeah, 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 yeah. Oh, that would be awesome. Yeah. Yeah. I mean, no, man, we can't really use our. Well, I mean,
yes.
Yeah, simply run the narrow.
Based on the case study, because so if you take 3 days, then we have the maximum observations. So in your case, it should be more interesting to do this kind of case study prior to the data set, or having one number for every day of the month, but having only one.
Yeah.
Data simulation started with knowledge of physical systems. And it's great to start whatever observations are available. Some of that together, they do simulation to massage our state systems or something. Very dense observations. Then you're going to establish your consent to carefully. That's been not so much to develop. Actually, well, it's actually. The thing about the demonstration, it takes a lot of innovation, but it can spread that information. Give you information where you don't have information. So it's great to use both kinds.
I have an idea. What would
All right.
So Melinda, do you want to try sharing your slides?
Yes, and can you hear me?
Yes.
Yeah, we can hear you.
Cool.
Yeah.
All right, so we're.
I know. Cowgirl.
You, if you
What's
wave at that.
Cowgirl.
Where do I have to?
Cowgirl. I know, so I said yeehaw.
No, but you said cowboy.
I corrected
This
myself.
little-
Oh, okay.
The recipe actually does say cowboy cookies.
Oh, but you
But
made that.
Yeah.
Can you wave at Linda from here? Do you see us wave?
Yes.
Yeah.
Okay, very cool.
All right. So I think, so we have,
The top can rotate is what I'm saying, the camera.
yeah, so we're gonna reconvene for the last session of the day. And Melinda Webster is joining us remotely. So it looks like she can show her slides and we can hear her. So awesome. So Melinda, if you want to just go ahead and take it away.
Well, thank you so much. I sure wish I could be there, but yeah, thanks for the opportunity to still present from afar. And this presentation is about the variability in melt ponds, and this was spurred from some really fun conversations with Marika Holland, Chris Polishinsky, and Hannah Chapman Dutton. Okay, so there's been a lot of cool talks about melt ponds so far, but I want to reiterate that they're super cool. They're also important for many reasons. One of the key ones being that they help or they control what's happening with the surface albedo of Arctic sea ice during the summertime. So it's important to know how much of an area they cover, but it's also important to know when they're present. And this presentation is about that short-lived variability in the presence of melt ponds. And this can be due to melt pond drainage. So when the ice gets so warm, it becomes permeable and the meltwater can drain or flush through. Or it could be due to refreezing events. And that's what I'm focused on for today's talk. And to describe what refreezing is, this is what happens when it's getting cold enough that you can form a little lid of ice on top of the melt ponds. And on top of that, you can accumulate some snow. And that gives an albedo boost. And depending on how long that lasts, it can be important, or maybe it's not so important. Maybe it's very short-lived and reopens into an open melt pond with warmer temperatures. And for you mosaic remnants left over from last week's conference, this is a repeat of last week's talk, but I have some new stuff in it too, so hopefully you won't be bored. So yeah, to give you an example of what this looks like from observations, we had two examples of this from mosaic, and one of my favorite ones was from the late spring period. This is an image, a satellite image from late May. This is the mosaic flow. This is where the ship ended up parking at. And the star is where a lot of chocolate was eaten at Picnic Ridge. But the reason I'm showing this is it's about a kilometer distance between the star and the ship, just to give you an idea of what the scale is. And if you can see, there's some low-level clouds obscuring this, but there are melt ponds present on the second-year area of the flow and the first-year area of the flow. And within the same satellite image, where it's not obscured by clouds, you can see more extensive ponding all around. And not long after this image was collected, there was a freezing and snowfall event, and that's what's shown on the right here. And this lasted quite a while. We got back to the flow in mid-June, and during our initial surveys, the melt pond coverage was less than 5%. And looking at MODIS imagery between the period of May 28th, June 6th, and June 17th, there wasn't a lot of ponding during that time. So this was a pretty long-lasting refrozen pond event. This is what I want to talk about today. But I do want to emphasize that I think there are different flavors of refrozen pond events. Some are very short-lived, and these are some cool examples that Don Perovich shared with me from Sheba, where you can see the skim of ice lids on top of the melt ponds, and we saw similar things on Mosaic. But this happened overnight, and by mid-afternoon, these had completely melted away and had reopened into open melt ponds. So I'm wondering about this, these different types of refrozen events, and maybe that has something to do with the state of the ice in the melt ponds before refreezing takes place. So if it's early season, maybe the ice is cold and the melt ponds are shallow and they have a relatively lower heat capacity and can freeze more easily versus midsummer when the ponds are deeper and the ice is warmer. Anyway, I want to explore this problem, and to do this, I'm using models and observations to tackle some science questions. And these science questions are very basic because refrozen melt ponds aren't something that's really been looked at. So there's a lot we don't know. This is ripe for your feedback because it's all preliminary. But our first question is trying to figure out what's normal. So how often do these refrozen melt ponds occur? How long do they last? And when do they occur? Don't really know. So we're looking at that with the model and the observations that we have on hand. And then are these even important? Almost like a philosophical question. Do they last a day? Or do they do any impact? Like, do they change the surface albedo or the absorbed shortwave radiation? Don't know. We're going to find out, hopefully. And then if they are important, can these events be realistically simulated? So what's causing them? What leads to their occurrence? Are these due to storm events? Are these due to cold snaps? These are the things I'm really excited to dig into. So the data we're using, first off, again, I'm going to emphasize that this is preliminary. So I'm just digging into this for the first time. I wanted to use the tuned Community Earth System Model version 2 runs that Jen K and others put together. And this is tuned in such a way that the CI state is more realistic with observations of coverage and thickness. And for this analysis, I only used 10 ensemble members for this period. It's not exactly the same as the Mosaic time period of 2020, but you'll see that this is still an interesting comparison to make. And then we're using observations that are both quantitative and qualitative. So from the transect data that Radiance described, SkySat mode sentinel imagery, just to get a sense of when melt ponds were present versus when they were not, and then snow depth measurements and albedo measurements from Mosaic. Now, refrozen pond events, we have to define them somehow, and I'm open to ideas on changing this definition, but this is just to start with, just to, figure out a way to quantify them that in a way that would be consistent between the model and observations. So first off, this definition begins with melt ponds being at least 5% coverage, so like having 5% of the ice area covered in melt ponds. And if there's a reduction, there must be at least a 5% reduction and rebound back to that initial value. And the sensitivity of going back to that initial value, I've been playing around with it, and it's not too sensitive, but still something to explore and definitely open to suggestions on that. Some other criteria I imposed, especially looking at the model data, is I'm looking at grid cells that have at least 50% sea ice concentration year-round, so I can ignore the crazy variability along the ice edge and in the marginal ice zone. I'm only looking at effective ponds, so these are ones that are radiatively active or open to the atmosphere, and that matches well with the observations, but I am curious about looking at subnivean ponds next. So these are ponds that can be covered in snow or refrozen and covered in snow, both in the real world and in the model. I do want to emphasize that these refrozen pond events are not the same thing as summer snowfall events, although there's a lot of snowfall that occurs at the same time as these refrozen pond events. And that's an example I'm showing here. This is the pond fraction on the y-axis over days of year. And the dark blue is the pond fraction. And you can see it decreases, and this dashed line is showing instances of snowfall. And they do overlap. Oftentimes, there's often a connection there, but not always. Okay, so how about I get to some results? I think that's what's next. Yes, so this question about what's normal. So these are results from CSM2, the tuned simulations. And what's interesting is that the date, so the average date for these occurring in the model is in July, in the middle of the summer, but there is a range, so from early July to early August, but that still is a little surprising to me because I would have expected more during the shoulder seasons, like early melt season or late melt season, not smack in the middle. The frequency in the model is very low, so these don't occur all that often. There are more refrozen pond events on ice that sticks around longer, so I guess that makes sense. But I still would have expected more events, so that was surprising to me. And then the duration of these ponds being refrozen, that was also kind of interesting because there's no clear spatial pattern in this figure on the right. This is the number of days. There are some splotches where they last longer and splotches where they're short-lived. And I'm wondering if there's a connection to some of the weather events that are driving these. That's something that I'm excited to dig into and figure out what's going on. Now, what happens during these events? So what's actually changing when ponds freeze? So this is the change in the pond coverage on the left. And in some instances, you get a decrease in pond coverage by as much as 25, 30%, which is substantial. But on average, it's about 12% decrease, which is still important. That makes an impact. Another surprising thing to me, maybe all of this is a surprise to me, but with how little snow accumulation is happening during these refrozen events. So this is the snow depth change when ponds refreeze. And on average, it's only 4 millimeters, which seems really, really small to me. But a little bit of snow goes a long way in boosting the albedo, but I still would have expected more snow accumulation. And then on the right, how do these these variables factor into the albedo change? So overall, we have a net increase in albedo by 0.05. That's something. But there are regions where it's a bit higher, and that has to do with there being more pond coverage decreasing more and more snow accumulation happening. So it seems like when those happen in tandem, it's really good for boosting the albedo. But overall, it doesn't give a massive albedo boost. So to figure out whether or not these are important, it's a philosophical question. I wasn't really sure how to go about this. So I started looking at the absorbed shortwave radiation during the entire summer versus what happens during these events. And to do this, I just calculated a simple correlation between melt ponds, albedo, downwelling shortwave radiation with the absorbed shortwave radiation for the entire summer in the upper plots and just during these events in the lower plots. So during summer, it's almost like a sanity check. If you have more melt ponds, you have more shortwave, absorbed shortwave radiation. So that's good, that's positively correlated. You have more, or if you have a higher albedo, you have less absorbed shortwave radiation. And then of course, what's happening in the upper atmosphere, if there are clouds, if there are no clouds, that's really going to dictate how much absorbed shortwave radiation is occurring within the ice. So when we look at refreezing events, it's a little bit of a different story. The correlations are much weaker for both melt pond coverage and albedo with the absorbed shortwave radiation. And that was really curious to me, but then it started making a little bit more sense when I saw how much stronger the correlation was with the downwelling shortwave radiation. And I think this has everything to do with clouds. It's something I want to look at next, but this is what I think is what's happening in the model. So when these events occur, this is an example of one, is you get a decrease in downwelling shortwave radiation due to there being more clouds. So that influences how much radiation you have available to absorb by the surface. So even though we're getting these boosts in albedo, it's as if it's getting masked by cloud cover. So instead of thinking that these refrozen pond events happen during clear skies and it's going to have a big albedo effect, maybe it's more like this. It's just cloudy the whole time and it doesn't really do much. So stay tuned. That's something we're looking at, but it is a curiosity to see if this is something that happens in the model and happens in real life. We don't know. That's something to explore. So how do these results compare with the observations, and how do they fit within the context of one another? Because the observations are from 1 year and the model results are from 10 ensemble members in 10 years, or no, yeah, 10 years, sorry, trying to do math this early. So the observations that I'm using are from the transect data, which Radian's described before, is these repeat surveys of snow and melt pond coverage. This is an example of what that looks like. This is just a profile of the melt ponds and the snow on top from different times of year. We're also looking at the albedo changes during these refrozen pond events and doing a comparison with what the model simulates. So there's a lot of information here. I'll just try to walk through it simply. On the left is the observations, and the middle column is for the mosaic location for Lake 4, that's the summer melt season. Lake 5 was the freeze-up season, which is further north towards the North Pole, in the yellow. And the very far right column is just a Pan-Arctic average from the model. It's the same results that you've seen before. But there are some 3 key things that I want to point out with this comparison. One is the number of events. There are much fewer events in the CSM2 tuned simulations, much fewer than what we observed on Mosaic. And the timing of them are very different than what we observed. So that midpoint, this average in the middle of the melt season, seems kind of odd versus towards the shoulder seasons. And that's something I want to look at a bit more closely. This could be an error on my part, but I don't think so. It's suspicious. And then one of the big things is the difference in snow accumulation that happens during these events. The model has very little snow accumulation, and I double checked just to make sure I didn't get the magnitude wrong with my calculations. But no, this is legit. There was a lot more snow during this Lake 4 period. We just couldn't measure it, but definitely a lot more than 1 millimeter. So this points to some questions of, is the model simulating these events realistically, or they're compensating effects, or, just so many questions to dig into. But it's kind of suspicious to see that the season's different, the amount of snowfall's different, and there are much fewer events occurring overall. Okay, to summarize these preliminary results, take it with a grain of salt, but the tuned ice runs show that there are fewer refrozen pond events and less snow accumulation than our mosaic observations. It's still kind of a small sample size, so I'm going to look at more ensemble members. I'm going to look at the same period as the mosaic observations. I'm also going to take a closer look at this event duration and how that's playing out across the Pan-Arctic, and if there's any sort of clues there of its linkages with types of weather events, and then also the seasonal timing. So just to get a better handle on what's a bias versus what might be realistic. And this idea of, if you have these albedo boosts, do they matter? Are clouds masking these events? Is this realistic? I don't know, but I'm really curious, and I'm hoping we'll find out in a couple months. Yes, okay. So again, I would love to hear some suggestions or ideas on this work, because it's all quite preliminary. And there were some questions about melt ponds, and I love chatting about melt ponds, so please reach out anytime. It would be fun to chat more about these topics. I do want to expand this to the Pan-Arctic scale, and that's a little difficult to do because remote sensing observations of melt ponds are quite limited, and especially if these cloud covers are masking these events, it's going to be really hard to know whether or not there's some sort of relationship there with the albedo boost. So a lot of work to do in terms of scaling up to the Pan-Arctic. And lastly, I did look at the CSM2 large ensemble, so not the change simulation. And I've only looked at 6 ensemble members for 6 years, so take that with a grain of salt too. But they had even fewer refreezing events and even less snow accumulation. So I'm wondering if this is real. We're going to look at this a bit more, but does it suggest that even though you can tune a model to get a more representative mean ice state, does that change the sensitivity of the interaction between the atmosphere and the sea ice? Don't know, hope to find out. Okay, thanks for listening, and I will leave this picture of a refrozen pond with a beautiful frost flower. Thanks.
Question. So Dave has a question.
I have a ton of questions, but I'll try to limit it to one for you. So the refreezing is the one part in the model that I've never been that comfortable with. I mean, we basically have this sort of simple thing that says, well, as the snow depth gets thicker, then the fraction of snow covers up and some of the ponds go away. It's all just sort of snow based. So what I'm wondering is, I mean, is there something about the temperature? Is there something else that we're missing in that we should be taking into account? Or is it, in this case, you seem to suggest that it is just about the snowfall? I mean, you know.
Yeah, that's a really great question, Dave. I think looking at the temperature is going to be so important, and that's something I ran out of time for. Because it seems like it's more than just how much snow that lands on top of the melt ponds, especially during those midsummer events that can be a little more shorter lived or don't last as long. So yeah, I would love to chat with you more about that to understand what the biases are that you're aware of and how that feeds into how long these events last and how often they occur.
Yeah, thanks.
So there's multiple questions in the room, and Rudra has a question in the chat. So maybe we'll have his first. Rudra, if you're able to unmute and ask it, go for it. Otherwise, Melinda can just hopefully read it and answer it.
I can ask the question. Thanks, Marika. Great talk, Melinda. Great to see you virtually. I have a quick question. I wonder, have you looked into how the size distribution of the melt ponds look like in a climate model and reality, and whether they match up or not? Thank you.
Yeah, that's a cool question. So I did a comparison with Marika and many others on looking at the melt pond fraction for CSM2 large ensemble, not the tuned ice run, compared to the mosaic observations. And there was a bias on there being too many melt ponds present because the ice was much thinner in the model than the observations. So it had a bias of about 10 to 20%, depending on the time of the melt season. So that might factor into it. But in terms of the size, like geometry, the model, I don't know if the model has that information, but it does have the depth. And I'd have to re-look at that. We didn't for the paper that we worked on last year, but that'd be something cool to look into and see how that fits into the ice thickness distribution in particular. So did that answer your question?
Yeah, that does.
Okay, good.
Alice?
I was just gonna ask, my first question, you kind of addressed this in conclusions, is you looked at the period 2000 to 2009 and the tuned ice. And I was wondering if you looked into the future, if you'd see more events, but it looks like you looked at the large ensemble, which maybe is kind of like looking into the future because it's too thin of ice. And that maybe didn't help. So I guess I was wondering if the phase of the precipitation, if you've looked at the phase of precipitation or something like that, since I know Ellen's going next, but her previous paper was about that it drizzles too much, and if that might be something that's affecting it. And if I'm correct, Dave, I don't know if I can't remember, but when it drizzles onto ice, does that go into a melt pond or does it just go into the ocean? Or
It goes into the melt ponds.
Okay.
But there's a funny little piece to that, is that on land, if it's cold enough in the atmosphere, they actually turn that rain into snow accumulation. Only on land, but not over the sea ice. And so maybe we could up the snowfall.
Yeah.
More snow is better, right? Is that the thing? But yeah, that's a fantastic thought, Alice. I think looking at the rainfall and snowfall is definitely a direction that we should be going with this, because maybe the rainfall does something to the heat content. I know there's not heat structure information with the melt ponds. I really wish there were, but it'd be interesting to see if rainfall plays a role in that.
So we're going to have to quickly ask questions, okay? I don't want to cut off discussion, but so David, and then we'll have Ed, and then we'll need to move on.
Yeah, on this rainfall question, so this May event, how sure are we that was actually melt and not rain? And would that change how you think about that event?
I'm willing to bet 25 cents that it was
meltwater than rainfall, because on those initial surveys, when we were taking ice drill hole measurements, there would be a 10 centimeter lid, 20 centimeter void of meltwater. We tasted it. And then there would be ice underneath. And that could not just be rainfall accumulation, given how extensive these subnivean ponds were during that mid-June survey that we did. In fact, we would drill holes to measure the ice thickness, and they would keep draining for 15, 20 minutes afterwards. So it was extensive melt that contributed to that.
Great. So Ed, if you want to unmute and ask your question.
Hi, Melinda. Great talk. Yeah, I think you mentioned briefly kind of thinking about the timing of the events, right? And whether that's one of the reasons you don't see many in the model. And I was just basically very surprised at how in observations you had already so much ponded surface by late May. Normally I think of this as, from like mid-June onwards. But that's a time of the year that you can still have quite a bit of temperature variability, right? You can still have some pretty cold events in late May, early June. And then sort of from mid-June on to mid-August, you're kind of stuck at 0 Celsius, right? At the surface. Like it's really hard to get a big temperature anomaly at the surface in the middle of summer. Compared to maybe more like closer to the shoulder season. So I wonder if that's one of the reasons why, like maybe the model's just not making that many melt ponds in May, so you never get a chance of a cold, like early summer or late spring event to make all that refreezing. So that's kind of a question / comment. The other thing I was thinking about, did you ever measure, I guess you could call it melt pond water temperature? Kind of like an SST, but for the melt pond. Are they always stuck pretty close to like freezing, or can they warm quite a bit above that?
Oh, okay. Great comments. I can't wait to dig into the data and explore that more. We do have some measurements of the melt ponds from their freeze-up period. And they do vary in temperature during that time of year in particular, especially if they are permeable, connected to the seawater below, because then they have some salt in them, which can change the vertical profile of the temperature. I'd have to look back at that to see what it looks like, but I don't think it would be the same vertical temperature profile that we'd see in the early melt season, because that's primarily fresh water versus saline water, so you may have a smaller gradient. And it's shallower in the early melt season. I was trying to be quick. Okay. Did that answer your question?
Everybody wants melt ponds. It's almost like snow or albedo. Anyway. Okay. Yeah. Thanks a lot, Melinda. That was great. So we should move on. So I think Ellen is online, and hopefully, Ellen, you can share your screen.
I am. Can you hear me? Okay.
Yes, I can hear you.
Wonderful. All right, let's see if this screen share works.
It looks like it's coming up.
Okay, great. Do you see just my one slide?
Yeah, that looks great.
Oh, awesome. All right. Well, thank you so much for the opportunity to present. I'm sad I can't be there in person this time. But for those that don't know me, I'm Ellen McElhatton, and I'm currently a postdoc working with Tristan Lequier at the University of Wisconsin-Madison. And the question that I'm trying to answer with the work here, and much like Melinda, this is very preliminary, what I'm going to show. We're trying to answer the question, Arctic near surface air temperature is warmer in CESM2. Is this a good thing? And so this work really has just stemmed out of conversations that I've had from presenting a paper that Tristan and I did in collaboration with Jen Kay back in 2020, looking at the Arctic mean state in CESM2. And just briefly, what we did there was we compared the 800 years of pre-industrial control runs for CESM1 and CESM2 to really look at how the Arctic environment changed kind of on a large scale. And what our general points were, and one of these I think Alice mentioned, we found that the Arctic is much cloudier, it's warmer, and indeed rainier. than it was in CESM1, just in this very pre-industrial control Arctic mean state. And so one of those findings, the warmer, was one that folks really kind of latched onto and were excited to hear more about. And so here is a figure from that paper, and you can see across the top row is November, December, January, so the winter months. You have CESM on the left, CESM2 in the center, and then the difference here on the right. And you can really see right off these temperatures in CESM1, these are Arctic surface temperatures, have increased 6 degrees on average across the Arctic. And you can see it's even larger in some regions, northern Alaska, across these islands here. Even in May, June, July, which saw the lowest amount of averaged Arctic warming, so just 2 degrees Kelvin over the Arctic, you still get a lot warmer surface temperatures in the Arctic in CESM1, or sorry, in CESM2. And so that brought up the question, when I presented this, somebody asked very astutely, is the warmer Arctic in CESM2 more realistic? And I didn't have an answer to that right away, and I spent a little time trying to answer that satisfactorily, and it's taken me down a little bit of a rabbit hole, but it's been interesting, and I hope you guys will enjoy the journey with me. So what I decided to do to answer that question was get my hands on as many near surface air temperature observations as I could find. And so far, what I've gotten is 147 ground-based stations, and we have quite a few from Met Norway. You can see down here in the kind of teal color. We have GCNet across Greenland here, as well as Summit Station with the ice caps data. Environment Canada has quite a lot of Arctic stations we've been able to get data from, and some of these data sets are more than 100 years long. And so we've also, in addition, at the suggestion of Don Perovich, added 85 Arctic buoys. And so these buoys are part of the CRREL Dartmouth Mass Balance Buoy Program, but they also collected near surface air temperature across the Arctic Sea. And so to get an idea of how I use the station data, we'll take an example of one ground-based station. And so my requirement to be included in the study was a minimum of 5 years of data. And what I take from each station is the monthly mean near surface air temperature for whatever the lifetime of that station is. And then from the models from CESM 1 and 2, I use the grid box containing the station, so only that single grid box, and I take the corresponding years from each member of the two large ensembles, CESM1's large ensemble and CESM2's large ensemble. And so what that looks like when you just take the whole time series here for this particular station, I ran from 1985 to 2020. You can't see a lot, when you look at the whole thing, but if we zoom in a little, we can start to get an idea of how these two models look relative to the observations. And so what you can see kind of right off, CESM1 is in red with the ensemble mean in the dark line, and CESM2 is in blue. And you can kind of see right off that CESM1 is too cold in winter, mostly, and a little bit too warm in summer. Sometimes CESM2 is too warm in winter. And so you can kind of start to look at a little bit of these. And up here in the legend, I also have the annual average temperatures for each of these data sets. And so you can see on average at this station, CESM1 is about 261.2 and CESM2 is 4.5 degrees warmer on average at this place. And it happens for this particular station, that's a good thing. So this surface station is on average 264, which is closer to that CESM2. So if I then collapse that into the annual average, we can get a better idea of what of how this looks. And you can really see that relative to this station between these particular years, CESM1 is too cold in the winter, too warm in the summer, and CESM2 does a really nice job of matching the amplitude from winter to summer as well as the values in each month. And so great, for this one particular station, CESM2 is doing a good job. That's fine. But what I want to do is compare the statistics across all the stations. And so to do this, what I've decided to do is take the monthly average temperature of the station as a reference and compare that to every single ensemble member year and month. And so this is just one example ensemble member year here and I take that difference. So for February, we would get that difference between those two lines. And so if I collect that data for all of these stations, what we get is this temperature anomaly histogram here. And so what you can see right away with these, this data, and so we end up getting quite a few data points. For this, you get about 1.4 million for CESM1, 3.7 million for CESM2. So you start to get fairly good statistics on these. CESM2 anomalies are fairly well centered around 0. The peak is slightly below 0. But CESM1 anomalies are definitely skewed colder relative to that station data. You can see that fairly well here. If we then overlay the observations on top, because again, we have just that reference of the average for each month, and now we're comparing the year-to-year variability for the observations, we get an idea kind of what the spread is there. And the distribution is narrower, which we would expect because we only have one realization of our actual planet compared to the 80 ensemble members we're looking at with CESM2. But you can see CESM2 does a really good job capturing kind of the character of that distribution there. And if you recall from that very first slide that I showed, the winter months, November, December, January, saw the really large increase in temperature across the Arctic, the biggest change in that Arctic mean state temperature. And so if we then take a look at only the winter months relative to the station data, we can see that CESM2 is quite different than CSM1, and CSM2 really hits it spot on. You look at that peak, it's right at 0. It's really centered around that for the anomaly. Of course, you're going to get some stations that are warmer, some that are colder, but relative to CESM1, which is really biased quite a bit colder in these winter months. And so if we again overlay those observations on top, you can see that CESM2 might be skewed a little bit too warm in some places, some amount. But overall, I would say that this is fairly conclusive that for these 147 stations, CESM2's representation of 2-meter air temperature is much closer to observation. So this is great. Well done, CESM2 modeling folks. But so that's wonderful for the land. But what I've newly added just in the last month or so is looking at these buoy data over the sea ice. So how does CESM2 do over the sea ice? And so the buoys that we have, they're much shorter lived. We are not going to have these, 100-year data sets. What we have are 85 that meet the minimum that I set of 2 months of usable data. And so only 58 make it to 6 months, and only 19 end up making it to 12 months or more. And so the comparisons that we do here, and also I'm sure I don't need to say it to everybody in this room, but buoys are not stationary. They move. And so comparing them to the models took a little bit more thought in how I wanted to do that. I still wanted to use the monthly mean values. But in order to get a monthly mean value from CESM to compare to the observations, what I did was track the daily location of the buoy as it moved through the CESM grid. And I took a weighted average of all of the grid boxes it moved through in that month, weighting it by the amount of days it spent in each grid box. So if it lingered in one place, it would be weighted more towards that place. And so this is an example of one station of what you would get in that, that movement. This is one of the longer lived buoys. It lasted for about a year. And you can see the buoy data here in black. CESM2 is in blue again, CESM1 in red. And much like the land stations, you see CESM is warmer throughout the year than CESM, or CESM2 is warmer than CESM1, as usual. And the surface station, the buoy is even a little bit warmer than that, closer to CESM2. And so even though now we don't have a reference that's multi-year, we still use what data we have as the reference, and we compare each of the ensemble members again to that. And what we get when we collect all those 85 buoys is this, which I was really heartened to see when it first showed up. I wasn't really sure what to expect, but we have, again, here quite a large peak right at 0. So with CESM2 and the CESM1, just a little bit colder. And so this corroborates what we saw at the land-based station. So across all of these buoys, we're seeing a more accurate representation of the near surface air temperature. And again, this is all the months. And so if we have a look at winter only, same story again, CESM2 is closer to that 0 line for the temperature anomalies than the CESM1. So the buoys show a nice consistent story with the ground-based stations. In general, CESM2's representation of Arctic monthly 2-meter air temperature is closer than observed. And just as a little side note, I don't include the buoys with the land-based stations because since I have so few data months here, it only ends up being about 2% of the land-based data when you throw it in there. So looking at it by itself, it's really nice to see that it comes up with the same story. And so a few more quantitative statistics for those that are interested to get an idea of kind of where in the spectrum of temperatures the two models are doing better or worse. You can have a look here. This is the same data, just presented in a little bit of a different way. We have the reference monthly 2-meter temperatures across the x-axis, CESM1's representation across the y-axis. And you can see here all those different data points. And it actually doesn't do too bad up in the higher temperatures. But the lower that you go, the colder that you get, CESM1 just does worse and worse and worse. And the overall bias that you have in CESM1 is about -3 Kelvin. And so this is for all months. And in CESM2, on the other hand, you get a much, it follows along that 1-to-1 line much closer, and you end up pretty much removing the bias there, with that 3 Kelvin cold bias. And if we take a look at these same plots, but for the buoys, we get a similar story here, a lot less data to fill in, but you can see that cold bias is still around 3 Kelvin for CESM1 for these buoys, and it's been reduced to less than 1 Kelvin in CESM2. And similarly, it struggles when we get to those cold places and does better where it's warmer. So conclusions, I think it's fair to say, I tend to be timid in making, grandiose statements, but the warmer temperatures seem to be an improvement in CESM2 based on the stations we've looked at so far. So what's up next with this project? I'm adding stations in Alaska. I've got quite a few of those, and I've got a question for the audience on the next slide. So I'll show some of those results that I just got last week. And so I'm also going to add the Promise Greenland station. So I have that data. I haven't added them yet. You'll see we have a bit of an overpopulation in Norway stations, which I will thin. But I've done sensitivity studies so far, and I'm not worried about that. It doesn't really matter which stations I include. We get the same answer. And there is this kind of notable lack of data over here on the Russian side of the Arctic. And so if anyone in the audience happens to know of available Russian 2-meter air temperature, I'd love to add that to the study as well. I haven't had any luck in my searches so far finding any. But a fresh result and a puzzle. I have these Alaska stations here. So somebody, kind person, Leah at the University of Alaska Fairbanks Climate Office, put me in touch with this data. So I have 65 ground-based stations in northern Alaska. And I'll just cut right to it for the winter results, winter only. CESM is still too cold. So you can see this histogram peaks, far below 0 line. So it's too cold relative to the observations. But now in this area, CESM2 is distinctly warmer. In winter months. This isn't true across all seasons, but here in the winter. And because it's winter, it's not related to absorbed shortwave. I know that. I've had a look at downwelling long wave, which is certainly larger in CESM2 than it is in CESM1, but not more so than anywhere else in the Arctic, really. And so I'm curious if anybody has run across changes in surface characteristics or circulation changes that might explain some of this in the work that they've done that's unique to northern Alaska. So with that, those kind of two audience questions, Russian data or Alaska suggestions, I will leave it there.
Thank you, Ellen. It's very interesting.
Oh,
So
good.
Patricia has a question or comment in the room.
Yeah. Hi, Ellen. That was a great talk. And
Hey, Patricia, good to see you.
Good to see you. I actually have multiple questions, but
Okay.
I will start with one. I'm wondering if you, so specifically for the sea ice buoy part of your talk, have you looked at if, because I'm assuming the buoy was in, like each of the buoy was on sea ice. Have you looked in if that grid cell was also sea ice covered?
That is a very good question. And I've collected that data because they don't always stay in sea ice. I guess they float a bit. And when I look at the individual stations that are kind of near the marginal zone, there's more variability across the model. Certainly you can tell, you know, the variability of the members gets a lot bigger. I've collected that data, but I have not plotted it up specifically yet, but I have that as an option. So I think that's kind of next on the docket for sure. It's a very interesting question.
I guess what I'm thinking is that, are you getting warmer temperatures in CSM2 for the wrong reasons because the sea ice is too thin and not extensive enough? And so I wonder if you could, like, this is, you know, just a suggestion, but maybe looking at the CSM2 tuned runs that Melinda just talked about. Is more realistic because you still have the CSM2 physics. And so is it that the warmer temperature is just because we have less sea ice, or is it because the physics of the atmosphere and everything has changed?
Absolutely. I actually made a note when I saw that in her talk. I think that adding those to the study will be really a good idea. And I could, at least in the interim, cut out all the stations that are anywhere near open water and just see how those look difference-wise. Yeah, no, that's a great suggestion. Thank you, Trisha.
So I think, Ed, I saw that you had a hand up.
I did, but it's very much kind of what Patricia alluded to, right? That if CSM2 has the right temperature, why does it have the wrong sea ice or too thin sea ice?
Right.
I did include there is Russian station data I've worked with a little bit at a NOAA website that I've added on the chat.
Oh, great.
And then,
thanks.
Then the other comment is I wonder if you've used ERA 5 also to compare. Well, I guess you could validate ERA 5 with your station data, but like I'm thinking about the vertical structure of the improvement in CSM2 or the temperature profile. Was this mostly confined to the surface of the boundary layer, or do you see, you know, like if you look into the free troposphere, how would that temperature structure look like?
Absolutely. I'm really interested in that. And that's actually the next step. I want to not just ERA 5, but I want to take a look, basically reproduce this study for all of the reanalyses, kind of to look at who's doing better and why. But from that, I really like that suggestion of taking it that step further and looking at the temperature structure. Because yeah, right now, all I have is 2 meter. And that's all that I've looked at so far. So thanks, Ed.
Thanks.
David?
Yeah, this is, I guess, more of a comment, but I think it's also worth commenting that those buoys are not at 2 meter air temperature. And so especially under very stable conditions, right, the buoy is at most 1 meter off the snow surface, probably even lower than that. And so it might be interesting to compare, right, what is the sort of implied temperature accounting for that that it's not actually a 2 meter air temperature.
I was going to make just sort of a similar comment from the model side, in that it's a diagnostic variable. We don't actually solve for the 2 meter air temperature in the model. It's just relying on this sort of boundary layer stability idea, and so I don't know that it's exactly apples to apples, you know, right?
Yeah. So I think, so you have several suggestions in the chat for data sets. So
I love it. Thank you.
But I think we should move on because we are definitely running late. So the next talk up is Chris Wyland-Powell. And if you want to try to share your screen. And I don't know about other people, but my Wi-Fi kicked me out
Yeah.
briefly.
Yeah.
It looked like a lot of people were leaving companion
we all
mode and
got
joining
kicked
back
out.
in.
Oh, no.
I could join back in, but yeah,
I
the
haven't
Wi-Fi
tried
seemed
it.
to go down. Edgy-Roam and the guest.
All of them.
Yeah.
I like restarted my computer. I was like, this will fix it.
I'm now on Edgy-Roam and
I'm on Edgy-Roam again and it seems to be working, but. So we had a good distribution of in-person and remote talks because the in-person people.
Yeah,
got kicked
yeah,
out.
yeah, right.
Yes, if you film this, you can do it for us. So, maybe that. Okay.
Sorry.
Did you send your?
Yeah, it's Chrome sharing permissions, but it's not working.
I think I just need to restart Chrome, so I'll just need 1 minute. Unless, does Joanna want to go now whilst I sort this out? Is that,
Sure.
Does that work?
That works.
Okay, yeah.
That's
so-
okay. Sorry.
Sure.
Okay.
You're ready to
No worries.
go, John.
Yeah,
Um,
Jonah's ready.
Should I
so-
go into presenter mode before I share? Is that the?
No. Share first.
This is good. I'll use all the expertise in this room.
The entire screen.
Yeah, do your
Entire
entire
screen?
screen,
Yeah.
that's usually better. And then you kind of hide your window.
Do I do the
Good.
entire? Sorry, entire screen.
Yes.
Okay. Allow. This.
Yep.
And now, can I use presenter? Sorry,
Yeah.
I like
You
my
can do-
presenter
You can do
mode.
presenter mode, yeah.
Oh yeah, I can always check. And
Looks good.
well,
Except that's your last slide, no.
You can see your presenters.
yeah, I can't see.
Google Meet-
It's okay. I don't have
Google
that
Meet
many.
doesn't allow you.
Okay,
Because Google's the worst.
Yeah, because Google.
that's okay.
Yeah.
Okay, it's 3:27. Great. I'm Jonah. I'm a graduate student here at CU, and I work with Jen K. Today, I'm really pretty stoked to go after Ellen because she introduced a lot of important things that I'll be talking about, so it'll make this easier. But I'll be talking about long wave radiation and specifically looking at processes that control how long wave radiation emerges at different points of the year. And I'll get into what kind of this idea of emergence means later on. But first, we're interested in Arctic climate change. Can I make this go away? Oh no, I'm sorry. That was the wrong button to press. Okay, if we're interested in Arctic climate change and detecting it from space, we have to start at the Arctic surface. And that's because Arctic climate change is this surface-dominated and surface-driven process. And so what I'm just showing here is these two kind of key indicators of Arctic climate change at the surface. The first being our sea ice concentration. I'm looking at observations from NSIDC here, and on the right being surface temperature from the Berkeley Earth surface temperature data set. And to just briefly go over these plots, we have our month of the year on the x-axis, our latitude in the Arctic on the y-axis. And so we're seeing seasonal sea ice loss that's beginning at the southern sea ice edge and proceeding north is the sea ice retreats. And then we can also see that growth back is slowed in the kind of refreeze up season. And our surface temperature is kind of complementary when we think about different times of the year, is that there is warming throughout the year, but most of it is occurring from kind of the fall through the winter and into the spring. So now I'm going to add these variables that I'm interested in, which are shortwave radiation and longwave radiation, more longwave radiation from Ceres. And here, what we're trying to show is that our sea ice loss is driving this increase in absorbed shortwave radiation. We see this really clear spatio-temporal correlation that's occurring during the melt season that, of course, we're not seeing in the fall because there isn't solar insolation. And on the long wave side, we're seeing a similar, very kind of familiar patterns between our surface temperature trends and our outgoing long wave radiation trends. And this is, again, just telling us that the outgoing long wave radiation that we're observing is really related to warming at the surface and the kind of more efficient radiating of heat from the Arctic surface. And we're interested for each of these kind of variables, can we attribute these with these observations? Can we attribute them to kind of human caused changes? or could they plausibly be internal variability? And so this will just be kind of a short literature review to arrive at our variable. So in terms of sea ice, yes, these are just 2 studies, but there are multiple studies that have used a really long and robust sea ice record to say that both in terms of extreme events and decadal changes, sea ice loss is outside of kind of what we'd expect from internal variability. This is also true for surface temperature. But now we're going to our kind of short and long wave broadband radiation fields, which are not quite as long and have only kind of recently been looked at from this context. There's some really great work by Anne Sled and Tristan Lecuyer that recently came out looking at the shortwave side and found that in the series record, at least the clear sky changes have, they said, emerged from our internal variability. And this kind of leads us to where kind of this niche that this work is filling, which is that there really isn't a comprehensive study that's looking at changes in outgoing long wave radiation seasonally and evaluating them in the context of internal climate variability. And so this really motivates our research questions, which are, when do we expect this outgoing long wave radiation, or OLR, to emerge from internal climate variability? And what are differences between months of the year, given these really strong seasonal cycles in the Arctic? What are they telling us about the critical climate processes that control long wave radiation? Because if we think about the Arctic and its nature changing, of course, we know we're losing sea ice and there's albedo feedback, but how well is that compensated by this increase in outgoing long wave radiation? How is kind of the net radiation budget of the Arctic changing? So I've talked about emergence, time to emergence, and I just want to go through and make sure that we know exactly what we're talking about. And we can think about this given that we're at a CSM meeting in terms of climate model experiments. So in terms of internal climate variability, these are fluctuations that just have to do with kind of the chaotic nature of the climate system. And we simulate it by taking a single climate model, so with known physics, and we're going to start it in slightly different initial conditions and let it evolve into the future. And that's what we're looking in this blue line, is I think 35 or 40 runs of this unforced climate model. So it has constant pre-industrial forcing. And we can see that all of these 40 simulations, they're kind of moving up and down due to internal variability, but over the course of these 50 years that we're looking at, there's not actually consistent change. Whereas if we took those basically same simulations and now we apply an aggressive RCP 8.5 scenario, we're now increasing our carbon dioxide in a somewhat reasonable way, we see that there is still scatter, but also there's a trend in our outgoing long wave radiation. So when we think about emergence and time to emergence, we think about, for each of these lines, what's the trend in our outgoing long wave radiation after 10 years, after 20 years, after 30 years. And that's what we're doing on the right side here. So this is telling us a 95% confidence interval on the trends that we see in our unforced and forced experiments. And so this is telling us that if we're in an unforced climate, there's no change in our carbon dioxide or other forcers. If we're measuring for 10 years, we might see a really large increase in outgoing long wave radiation or a large decrease, but the longer we measure, the more apparent it becomes that there's really no change. Whereas if we're in a forced climate, again, we might still measure a really large decrease in outgoing long wave radiation, but eventually we'll see that we kind of leave this blue envelope of internal variability. And that's exactly what kind of emergence is that we're somewhere in this red envelope. We're one of these kind of realizations in the forced climate. And at some point, our trend is going to be distinguishable from these kind of internal variability trends. But we also know that this is going to be uncertain because we also have internal variability in what's happening. Something else important to note that we can get from the large ensemble is the forced response. And so kind of as I showed, is that all of these models are evolving differently due to internal variability. And if we average them all together, what we get is kind of remove that internal variability. And the model is just, the forced response is just telling us what is the response to the forcing that we've applied. So how does outgoing long wave radiation change when we add this CO2 ramp? And so that's kind of the value of the forced response. And so what I can do with the large ensemble is calculate the forced response for all these 4 variables that we were looking at earlier to try and put our observations of Arctic change, both at the surface and the top of the atmosphere, in the kind of broader context of what the model says is the response to forcing. And so that's exactly what we're looking at here. This was that figure from before. We're looking at our observed changes. And again, this is the forced response from the model, telling us how kind of the physics of the model respond to this forcing in the absence of internal variability. And so just kind of first order comparison, all of these variables are looking very similar. And this is just telling us that what we've observed, even though it's a single realization and not this kind of aggregated response, looks very, very similar to how the climate in CSM1 responds to this RCP 8.5 forcing. And so this is largely telling us that this model is looking like a really excellent tool to do this study with. But we want to ask, we have these observed changes, we have this forced response. How do we explicitly quantify if changes in outgoing long-wave radiation have emerged from internal variability? And this is where we can lean on some work that's kind of been developed in this kind of area of time to emergence. And this is what I'm going to kind of explain briefly now. So we can think about what are factors that make a trend emerge more or less quickly from internal climate variability. The first factor is just having a large trend. So if we're thinking about that blue envelope that our observations need to kind of pop out of, having a large trend means that we'll quickly exit that envelope. But also, if the internal variability of our pre-industrial climate is low, we'll also kind of shrink that envelope of internal variability such that even a small trend will emerge from it. And there's two terms that kind of go into the size of that envelope. The first being this amplitude of internal fluctuations. So in our unforced climate, how much is our long wave radiation just varying due to internal variability? But also, what is the duration or memory of those fluctuations? So if we have a fluctuation that's persisting over several years, it'll look a lot like a trend and make it kind of harder for us to distinguish a true forced response as exceeding internal climate variability. And so there's a nice mathematical framework that puts all these together. And so we have our time to emergence, and we have this expression here. But effectively, we see that the large trend is going to decrease our time to emergence. Things are going to happen more quickly. Whereas if the internal variability is large, it's going to be harder to distinguish our observed trend from internal climate variability. So what I'm going to do here, given that we have 40 members of this large ensemble, is going to go through each member, and I can calculate these internal variability characteristics from the pre-industrial control simulation. And then I take the trends from each member, and I can figure out when they emerge from internal climate variability. And so I'll do that for each month of the year. But also, since we have 40 ensemble members, I can kind of treat this time to emergence as the inherently uncertain quantity that it is and represent it as a confidence interval. And so that's what we're looking at. Again, we're back at our months of the year and our annual average. And these confidence intervals are telling us from the CSM1 large ensemble, how long do we need to observe for until we've observed something that is really confidently different from internal climate variability. And so the big takeaway from this plot is just that there's a really large seasonal cycle in this time to emergence. And specifically, we see kind of the earliest time to emergence occurring in September and in the fall. And if we go to April, it's a very different story. You'd have to measure for, on average, more than 40 years to see this really distinguishable change in the long wave behavior in the Arctic. Also, this gray line here is indicating the length of our observational record. And so this is telling us that it's overlapping with the confidence intervals in just about all months of the year. So we could plausibly have detected one of these changes occurring. But also, if we look, this line is only going to inch up year after year as our record gets longer. So it's becoming more and more likely that these changes are going to emerge in the fall. And in terms of the annual average, it's actually more likely than not at this point. And something else that we can do is this quantifies our uncertainty in this time to emergence. So even though we have this seasonal cycle, we can also see that there's a lot of uncertainty in terms of when these changes would have emerged. And we're going to ask, we had those three terms that went in. We had the strength of our forced trends, as well as the internal variability. So what of these factors, how are they going to explain this seasonal cycle that we're looking at here? And we'll start by looking at the forced trends here. So these are our changes in outgoing long wave radiation. We're using a similar 95% confidence interval from the large ensemble. And I'm also adding our series observations in here just to show that the model, again, is a good tool for this task. So similar to this time to emergence, we see a seasonal cycle in terms of how quickly outgoing long wave radiation is increasing. Across all months, the mean is increasing. The Arctic is warming across all months. But specifically in the winter, we're seeing the largest increases in our outgoing long wave radiation. And in the summer, we're seeing the smallest increases in the outgoing long wave radiation. But if we remember, the earliest time to emergence was in September. And so if internal variability were constant across these months, we would expect to see the largest changes in September and not kind of later in the fall. And so this is telling us that the forced changes in our outgoing long wave radiation alone cannot explain this seasonal cycle of time to emergence that we're looking at. So now we're going to ask kind of for all those months, what are the characteristics of the internal variability that I calculated from the pre-industrial control simulation? And so that's what we're looking at here. We have the first term, this magnitude of internal variability, and the second term, this correlation time of internal variability. And the real kind of culprit here is this first term, the magnitude of internal variability. We have much lower internal variability in the summer and in the fall when we're having melt, and the surface temperature of the ocean is really tied to that melting point of water, or melting point of ice. And even when the ice is gone, kind of as was mentioned, there's so much thermal inertia in the ocean, is that our emission temperatures are going to be really stable and the internal variability is low. Whereas in the winter, we have this ice-covered surface that's often well below zero, and there's not anything kind of holding on to our surface temperatures. This separate term of internal variability, there are a few months that are different. I'm happy to talk about that separately, but this is not the factor that's determining that seasonal cycle that we were looking at. So this is our culprit here. Finally, and this is a great reason that Ellen was before me, is that this is just one model. And Ellen just said that CSM1 is not as good as CSM2. So let's run the same results with CSM2. And in this case, we can't use the CSM2 large ensemble because it has a different forcing. It's not making an apples to apples comparison, because we really want to tease apart what part of the physics are going to lead to differences in the model. So we're using another ensemble that Marika ran, which is CSM2 with CMIP5 forcing. And so in this case, our ensembles have different physics but identical forcing, and so we can make a comparison with them. The error bars here are just so we can make a size-aware comparison between one ensemble of 10 members and another of 40. So in gray, again, this was just the CSM1 large ensembles behavior that we kind of evaluated before. And in blue is the CSM2 with CMIP5 forcing. And all you need to note here is that during the fall, where we saw that really early time to emergence, that's different, statistically different in CSM2. So there's something about the physics of the model that's changed, and it's kind of, we're losing a little bit of that strong seasonal contrast. And I don't think I have time to show it, but that we kind of trace this not to actually something happening in the fall, and not to have something that's directly affecting the outgoing long wave radiation, but actually to the short wave radiation during the melt season. And this makes sense, hopefully, to the model developers, because the big difference between these models has to do with the representation of sea ice and clouds during the melt season. And so this is modifying the shortwave energy budget in the melt season, and it's resulting in basically larger changes in the fall in CSM1 that cause these earlier times to emergence. So just to summarize, we calculated the time to emergence of Arctic outgoing long wave radiation using the CSM1 large ensemble, and we also were able to quantify uncertainty in this time to emergence. That again is from this inherent irreducible internal variability. Also, we were able to trace monthly differences in time to emergence due to seasonally varying force change in internal climate variability that was largely related to conditions at the surface. And then finally, by comparing our two models, we showed that these fall changes in CSM1 were emerging earlier than in CSM2, and that's related to how clouds and sea ice in these models are prescribed, or not prescribed, but the physics of the clouds in the sea ice. And yeah, that's it.
Thanks, Jonas. So any questions? They're in the room or online?
I guess I have a quick one. I mean, you've done the CSM2 with CMIP5 forcing, and that's good. So you can sort of ascribe things to physics or model. But I mean, you could still do it with the full CSM2 lens ensemble as well. I mean, it just gives you more data points, no?
Yeah, I'd be hesitant to compare the CSM1 large ensemble with the CSM2 when trying to make we're interested in these processes, and when you mix the forcing, it just becomes kind of another beast to handle. But you could definitely do that. You could compare it with the CSM2 with CMET5 forcing. I'm more into kind of changing one knob at a time.
Sure.
Yeah.
Are you able to, Ed, go ahead.
Hi, Jonah. Nice talk. I just had a quick question regarding your equation on slide 15, the time of emergence equation.
Okay.
There's a symbol, there's a letter S, and maybe I missed it, but I can't remember.
Oh, yeah. Also, sorry, the slide numbers are clearly out of order, but okay. S is effectively the number of standard deviations. So that's describing the confidence interval that you're using. So in this case, we use S is 2. We're effectively saying the time to emergence is when we're outside 95% of internal variability.
Okay, nice. And I also want to ask, so one way I've thought about this, how to quantify when you're, this time to emergence, and I've seen a little bit of literature, is to simply say that, when the difference in your means, so, the mean of your forced runs compared to the mean of your unforced runs, when that difference equals the standard deviation of internal variability, we call it, like signal to noise ratio, above 1. And I wonder if you calculated that, like if you'd get much different results.
Okay, so you said you're comparing means instead of looking at effectively like a simulated trend.
Right. And I guess you need
Yeah.
the full symbol for that, but it's just I just mentioned it because I've seen it in the literature.
Yeah, so that's a really great question, and I haven't done that. Something that requires is a model that does a really good job matching the observed mean state, and that's where this model is really good in terms of how it responds to the forcing, but kind of as Ellen presented earlier, the mean state temperature, and so in that case, the mean state long wave radiation is not, I wouldn't say, yeah, that would be my hesitancy of using that metric, is that the models are often going to struggle with the mean state, even if they're getting kind of the physics and the response correct.
Thanks.
Thank you.
All right, well, I think we should move on to Chris's talk. Are you able to?
Yep, I restarted and.
All right. So once Jonah stops sharing.
Yeah.
Let's see if that works. It looks like it's coming up.
Great.
All right, great.
Cool, yeah, thank you. So I'm Chris Wyden-Powell. I'll be talking today about large-scale climate modes as drivers of low-frequency regional Arctic sea ice variability, and this is work I've done with my advisor, Alexander Young. So just to briefly motivate this work, I'm sure we're all aware that internal variability is very important, and specifically in the summer Arctic sea ice, the areas which have the highest amount of internal variability, as you can see in the figure in the top right, are these areas around the shelf seas. And these are also where there's the most rapid decline in sea ice, as well as the areas which are most important for the navigability of shipping from the Arctic. And just to, as an example of shipping, the figure on the bottom right shows with the length of the purple lines, the length of the season each year when ships can pass between the Atlantic and Pacific. And that, although there is an increasing trend in the length of the season, it's highly variable year to year. Another reason we're interested in internal variability is the fact that in the medium term, it dominates the scenario and model uncertainty when we're looking at the total projection uncertainty, especially for the marginal and shelf seas in summer. So this talk is mainly about the low frequency variability. And so for that, I'm referring to variability with periods in excess of 2 years. And this typically accounts for around 1/3 or 1/4 of the total internal variability. But this is a really uncertain quantity, and it varies considerably depending on which global climate models you look at, what time period, what region of the Arctic as well. But safe to say that low frequency variability is generally smaller than interannual variability. So on the shorter time periods, there is some amount of predictability, but that's generally limited until the spring. As you can see in the figure in the top right here, so there's the spring predictability barrier. But we're really looking at the longer time periods. So these very long time periods, we have some amount of predictability which may emerge, such as that related to the interdecadal Pacific Oscillation. And the figure on the right here shows that over time, over a decade or two, like the phase of the IPO can influence the trajectory of Arctic sea ice. And so what we're trying to look at here is identify whether there are modes of climate variability that affect Arctic sea ice concentration anomalies at lead times of around 3 to 20 years, to kind of fill in the gap between these two areas of predictability. So the data sets I'll be looking at sea ice concentration using CMP6 historical runs for GCMs, which also have data output from the Climate Variability Diagnostics Package, CVDP. And when we use that criteria, there are 42 GCMs that we're looking at, which have at least 3 members, and 8 which have at least 30 members. And then for the CVDP variables, there are 14 different modes of variability that I'll look at. And each of these, I can use a seasonal average. So in effect, we have 56 input variables to try and predict these sea ice concentration anomalies. And to break this down a bit more, we're going to be looking at 7 regions of the Arctic separately, and for the time period of 1941 to 2014. For each region, we try and isolate the low frequency variability by just looking at the 2-year low pass filtered data. So that tries to remove all the interannual variability. And when we look at the CVDP variables, these are detrended and standardized, but they're not low pass filtered. So we could apply this to real world data as predictors. So the methods here, effectively what we're trying to do is regress these 56 input features of climate mode variability and predict one value of the sea ice concentration anomaly for every year. So we're going to do this using a few different structures of a neural network. But effectively, we're always going to be having the input of these 56 variables and trying to output for one sea ice concentration anomaly variable that we're interested in. And so we train a model for each region and for each month of the year and at one lag time individually. When we're doing our training, we split with 75, 15, and 10% of the members for training, validation, and testing. And we can do this either within a single GCM or a large ensemble. And that way it's relatively simple. We just take the first 75% of the members and use that for training. And in addition to this, I'm going to look at the multimodal large ensemble, where we either take all of GCMs which have at least 3 ensemble members, then we use the first ensemble member from each GCM for training, or we can use the 8 GCMs which have at least 30 members, and then we can use the 23 first ensemble members for training, and then any members we have at the end past the 30 we're using for testing. And so the difference between these two multimodal large ensemble experiments is the fact that we have a lot more training data when we select for these much larger ensembles. And effectively, we have nearly 14,000 training years compared with 3,000 when we use this larger selection. So to try and unpick a bit more what's going on with how we are able to produce prediction, using a machine learning model. There are 4 different configurations that we'll be looking at initially, just to look at the relationships. So model 1 and 2 are both these very simple models, which you take your 56 input variables and you have your 1 output. And the only thing that is different between these 2 models is that model 1 uses a linear activation function and model 2 uses a nonlinear ReLU activation function. So in effect, these are both simple models, but use all of these 56 variables independently to reduce our prediction, because one uses a linear relationship and one allows nonlinearities to the system. Model 3 and 4 are now more complicated neural networks, and this allows these 56 variables to have effects on each other, basically, as you progress through the neural network. And again, the difference between model 3 and 4 is the fact that we have a linear or nonlinear activation function. So hopefully, using these 4 different models, we can determine whether linearity or nonlinearity is important, and whether there are interdependencies between these input variables. And so on the next slide, I'll show you some more detail for more GCMs, but just so you have an idea of what I'll be showing. Each of these 4 models will be shown with validation R-squared value. So how well does this our training data manage to predict our validation data set at different lead times? And this black dashed line is the persistence. And this is our measure of how good our prediction is. So we want our model to exceed persistence and be a good fit. And generally, we find that around 5-year lead time is when there's the biggest gap between this persistence and our model. And that's what we call the predictive skill in this case. So although we've done these relatively complicated different machine learning methods, we actually find that a simple linear model is the best in most situations. So that's good, because we can just use a simple model, which is very easy to understand. Model 1 and 3 both use these linear activation functions. Model 1 treats all of the variables as independently, model 3 doesn't. So this shows that as long as you use a linear activation function, we can treat the climate modes independently. Model 2 generally is the worst, and this is the simple configuration in the fact that treats all of the input variables independently, but this uses a nonlinear activation function. So in a way, adding nonlinearities to a simple model doesn't really give us any benefit. Model 4 is maybe the more interesting one in that it is quite a complicated model. It allows the variables to interact with each other and uses nonlinearities. But unless we have these really large ensembles, and I'm particularly thinking of the multi-model large ensemble with 30+ members, usually this does much worse than models 1 and 3. But there is the potential that if we did have an even larger ensemble, then perhaps it could exceed the skill of the simple linear model, but we just don't have enough data to verify that. So I already said that around 5-year lag time is when we have the best predictive skill in general. And then this figure here is just showing the predictive skill for 13 GCMs and the 2 multi-model large ensembles. And overall, we can see that generally the best predictive skill occurs in the late summer and fall. But there is a lot of variability between these GCMs. So what we do subsequently is we're focusing on the WWG in August, as this has the most number of GCMs which have a high predictive skill. Unfortunately, CSM2 doesn't do great for the WWG, but the Beaufort's is really good. So there's something to hold on to. So now we have this linear model that we're using. We can very easily understand what these different modes of variability are doing to influence our CIS concentration anomalies. So here for the WWG in August, the figure here shows that each of these modes of variability, if we have a +1 standard deviation anomaly for these modes of variability, what is the effect on this regional Arctic CIS concentration anomaly? So the two modes that immediately jump out, well, this isn't really a mode, but the global average surface temperature is very strongly correlated, negatively correlated with the CIS concentration anomalies, and that kind of intuitively makes sense. But this has this predictive skill persists for quite a long time, from up to around 50 years as a lead time. The other main mode of variability, which is important, is the NINO 3.4 index, which has a positive correlation with the CIS concentration anomalies. Most of these other modes of variability, either there's not much agreement between the GCMs, so if the GCM doesn't think that these modes of variability are important, then the line corresponding to that GCM will not appear on the figure. And so most of these other modes, it's not very certain, either if there's not very much agreement between the GCMs, or if there's not much agreement in the sign or the magnitude between them. And now just to kind of summarize this across all of the 7 regions we looked at, in general, again, so what I showed before was the WWG in August, so that's that kind of orangey color. And now we're adding in these other regions as well. And then on the x-axis, we have the GCMs and the 3+ ensemble member multimodal large ensemble. So again, we find that the global average surface temperature is strongly negatively correlated across all of these regions, and it's very consistent across all of these different GCMs. And similarly with the NINO 3.4 index, although there is more of an influence in the regions of the Arctic which border the Pacific, as you might expect, this still is a robust signal across these different GCMs. And then again, there are some disagreements between the GCMs or between different modes of variability. But in general, if there is one particular sign represented for the influence of one mode of variability, that's generally consistent across the different GCMs, which improves our confidence that this is actually a real effect. So now, what I want to do now is to bring together all of the 42 GCMs, which include together by using the test members from the multimodal large ensemble with the 3+ ensemble members. And so this brings together, if we look at the largest ensemble we have here, we have Canis M5 with 65 members. And so the last 63 we're using as test members. And so what this shows is how well each of these GCM's ensemble members agree with the overall multimodal large ensemble model, which is used from all of this pooled group of climate models together. And then if there's a high validation R² value in this figure, that means that these GCMs agree very well with the general consensus with CM6. So one of the take-home points here is that there is a large amount of variation between the different ensemble members within a GCM. And if we only have a few ensemble members from each GCM to compare, then we're not necessarily going to be able to diagnose whether the GCM itself is actually a good representative of these links between the climate modes and the CIS concentration anomalies that are generally present in CM6 GCMs. And this also has implications for observations, because if we just have one realization of reality, then again, we're just kind of picking one of these realizations from a GCM. So these are the limitations for determining whether the model, the GCMs, are able to diagnose these links between the modes of variability and CS concentration anomalies. And with that, I'll conclude. I do have some more slides which focus on CSM2 if you want to hear more about that, but otherwise I'll just go through the conclusions here. So I've shown that a simple linear model best captures climate mode variability and the effect on Arctic sea ice concentration anomalies. The dominant mode of variability, we found that the global average surface temperature is strongly negatively correlated with sea ice concentration anomalies as in across regions and GCMs. And the Nino 3.4 index is the next most important, which is strongly positively correlated. For other modes of variability which have some regional or GCM dependence, so they're not as certain, but generally they have the same sign across GCM and regions. And then finally, the CSM2 lens does exhibit highly predictable properties. However, it has high persistence, and so that reduces the predictability skill that we can calculate relative to persistence. And so that's why, especially in the WWG, we weren't able to use this to show the modes of variability.
So Ed has a hand up and then Christine. So Ed, go ahead.
Hi, Chris. Thanks for the talk. Those are some pretty amazing results. And so I just want to confirm, is this sea ice concentration or extent right for each region, not just volume?
Yes, so this is the sea ice concentration averaged over these regions, and then it's like detrended, low pass filtered after that.
Okay. And you're not using any future information for these climate variability modes, right? Like you're not sort of playing the game. If I know what my future ENSO's doing, how much for my sea ice?
No.
Okay.
So you could imagine that it's like in the present day, you're given these 14 modes of variability at seasonal resolution from the year 2022, 2023, whatever. And then you're looking to 20 years into the future, how much predictive skill can you obtain just with that data and nothing else? But you're looking at low pass filtered sea ice concentration. That's what you're trying to predict. So it's not, we get worse results if we try and look at the raw sea ice concentration that way.
Right. Well, that's where my amazement comes from, because like, you know, even with perfect models, I've never really seen results that show predictability of sea ice concentration or sea ice area beyond 3, 4, 5 years. Okay, maybe in the North Atlantic in winter, like Steve Yeager's work shows pretty long, and maybe that's more like low frequency because he was forecasting decadal trends. But yeah, pretty amazed. And the other thing too, how much of your lead time zero, like if you're just trying to reconstruct your sea ice time series using those climate variability modes at lead time zero, like how much can you, how well can you reconstruct it basically?
Well, effectively, lead time zero is 2 years on the figures I've been showing because of the 2-year low pass filtered sea ice concentration. So if you kind of use that as your 0 point, the highest you can get is around 0.6 or 0.7 as an R squared value. But that value, those are relatively rare. It's more like 0.3 or 0.4.
Right. So you imagine that you're already missing that bit of skill from the get-go. So you can imagine if there's a way to recover that skill for future forecasts. But anyway, I'm probably going to email you because this is really pretty fascinating. Thanks.
Thank you.
Christine?
Yeah, I agree. That was an amazing amount of work. I sure took a lot of effort. A lot of stuff. Have you considered looking at modes of variability interacting with each other? Because often they dampen or amplify, and they could actually change the character of the response depending on how the modes. I know that's probably a lot more work to do that.
Yeah.
But it's something to consider.
So something that we tried to account for that with so I showed 4 different machine learning model configurations.
Yeah.
And so when we have like the 2 hidden layers in our machine learning neural network, we do allow each of the 56 variables to sort of interact with each other because they can both feed into the same neuron. So in a way, we are able to account for that, and we found that unless you have a really, really large ensemble, it's still not as good as treating those modes independently. But there definitely is, and I'm sure they are quite interconnected. So there is like, there's just a limitation of the data that I think that there are probably ways, I can think of a few ways around that, but at least with the setup that I've been looking at, I don't think we can really account for that with the limited data.
Yeah, no, that I understand. It's, reality is different than model
Yeah.
work, so I completely get it. Yeah, okay, that's so, great to judge.
Yeah, David?
Yeah, it's a very interesting talk. I was wondering if you took your best predictor and actually tried applying it to observations, what do you think you would find for the observational record?
Yeah. So I have done a little bit of this, and it's kind of all over the place, to be honest. There are some variables which are very strongly correlated in the models and the observations, and some which just don't agree. The temperature and 3.4 index broadly are in agreement with the observations and the models, but the issue is there's just so little data with the observations that kind of averaging over different regions or different months of the year, and to kind of arrive at a similar kind of level of, well, what is correlated with what. And I'm still kind of working on that to figure out a way to more kind of robustly show that, but it's hard to really verify at all with the observations. But I think in general, there's at least some suggestions that the 2 most important modes of the temperature and the 3.4 index, generally the observations agree to some extent with the GCMs.
Jonah?
You're talking about how the single models or the smaller ensembles weren't as valuable. How many, I guess equivalently ensembles or model years do you need to kind of reasonably be able to infer these relationships?
Yeah, so I can just go back to this slide. So basically, I stopped at the smallest large ensemble that I used was 16 members. And you can see here it's just kind of very noisy. And if you wanted to, you could train with 1 member and validate with 1 member, and you're probably going to get a pretty bad result. And if you redid that with a different member, you'd get probably quite a different result. So I don't know, kind of qualitatively, around 30 members seems to be the point where you get kind of this more or less monotonic decline in validation with lead time, which I think is a way to kind of see if we've got enough training data to kind of get a coherent picture. But yeah, I'd say maybe 30 members is just like a guess as to how large an ensemble you might need to use.
Great, well, thank you. And let's thank all the speakers. Really interesting talks. So we are going to convene now. We're just 25 minutes late. So, but that was because there were such great questions. And I do feel like that's kind of what the working group meeting is about, is like discussing our stat science. So thanks for all the wonderful questions as well as the wonderful talks. So we're going to reconvene tomorrow morning at 9 a.m. Mountain Time. So hopefully those of you online can join us again tomorrow, and hopefully those of you in the room as well. And for those of you in the room, I think, you know, some of us are going to go down to the southern sun. So please join us. And yeah, and we can talk more science or skiing or whatever else over a drink. So thanks, everyone.
It's Stout Month.
It is
It is
Stout Month.
All right, take care, everyone.